Hello everyone, and welcome to the very first section of our Python for Beginners course. Are you excited to start this journey? Drop a comment below. In this quick lecture, we're going to answer a fundamental question. What exactly is Python? Simply put, Python is a high-level, interpreted programming language. Let's break down what each of those terms means, as it gives you a great understanding of Python's nature. First, high-level. This means that when you write Python code, you are writing it in a way that is very close to human language, like plain English, and far away from the machine language of ones and zeros that the computer actually understands. This makes Python incredibly easy to read, write, and maintain. Second, interpreted. Unlike some languages like C or C++, which require a separate step called compilation before they can run, Python code is executed line by line by an interpreter program. What does this mean for you? It means you can run your code immediately after writing it, which speeds up the development and testing process immensely. Now, let's talk about some of Python's other key characteristics. Dynamically typed. You don't have to explicitly declare the type of a variable, like integer, string, etc., when you create it. Python figures it out for you at runtime. This adds flexibility. 2. General purpose. Python isn't limited to one area. You can use it for web development, data analysis, artificial intelligence, scripting, and much more. It's truly a versatile language. 3. Open source. Python is free to use and distribute, even for commercial purposes. This has fostered a huge, supportive community that contributes to its development and creates an enormous library of resources. To summarize, Python is a friendly, flexible, and powerful language that makes programming accessible to everyone. That wraps up our overview of what is Python. Next up, in Lecture 1.2, we'll dive into the question, why should you choose to learn Python? See you there. Welcome back. In our last lecture, we defined Python as a high-level, interpreted, and general-purpose language. Now, let's tackle the most important question for you, the beginner. Why should you choose Python over other programming languages? The first and biggest reason is its simplicity and readability. Python's syntax is designed to be highly intuitive, often mimicking standard English. This means you can write fewer lines of code to accomplish the same task compared to languages like Java or C#. This focus on clear code makes it an excellent first language for anyone getting into programming, and it significantly reduces the time it takes to learn and debug. The second reason is its incredible versatility. As I briefly touched upon, Python's application range is vast. You can use Python for web development with frameworks like Django and Flask, data science and analytics, machine learning and AI, which is currently driving massive demand, automation and scripting for daily tasks, and even simple game development. Learning Python opens the door to almost every technical field. Third, Python boasts a massive and ever-growing ecosystem and community. This means that for almost any problem you want to solve, from drawing a chart to connecting to a database, there's likely a pre-built piece of code called a library or package that you can use. This saves you countless hours of coding from scratch. The community is also very active, providing constant support and documentation. Finally, learning Python translates directly into career opportunities. So, to summarize, Python is easy to learn, versatile enough for any project, has a rich ecosystem of tools, and offers career opportunities. You can use this language to start your coding journey. Next, in Section 2, we'll move on to getting our hands dirty by setting up our software environment, starting with Lecture 2.1. Introduction. See you there. Welcome to Section 2 of our course, Software Setup and Your First Python Script. This is where we transition from theory to practice, so get ready to set up your coding environment. The main goal of this section is twofold. First, to install the Python interpreter itself, and second, to install a powerful text editor where we will write our code. The tool I will instruct is Visual Studio Code, or VS Code. It is a popular, free, and lightweight code editor. VS Code is cross-platform, meaning it works on Mac OS, Windows, and Linux. This ensures that no matter what operating system you are running, you will have a consistent environment for learning. Because installation steps vary slightly depending on your operating system, maybe I will provide separate lectures for some platforms. Immediately following this introduction, we will begin with 2.2. Option 1. Environment Setup for Mac OS. This will cover installing Python and setting up VS Code on Mac OS. If you are on Windows or Linux, and I have the related videos, you can skip the Mac OS video and jump to the one that matches your machine, Windows 10 or Ubuntu Linux. Once your environment is set up, we will move quickly to writing our very first Python program, and then cover two essential fundamentals, comments and Python indentation. So, identify your operating system and get ready. The next lecture will be specific to macOS Monterey version 12.7.6. Are you excited to set up and code? See you in the next lecture that matches your machine. First, you need to access this address. Next, you hover your mouse over here, right here on Downloads. A view appears, and it appears with a download button suited to your OS. I am saying the gray button. You need to click this button to download. After download, you open the file. Okay, after opening the file, we will see a window like this. And now you see two checkboxes below, right? Mark both. After marking, you choose this option to download. Not the below one. Let's choose this one. You have now successfully installed Python, right? Now we are going to install VS Code. You access this page and maybe you will also see a download button suited to your OS. Like this. In this case my OS is Mac OS, so it shows me this one. Okay, you click on the download button and install it yourself. You've installed the VS Code successfully, right? And you can open the app like this, right? Now we are installing some extensions on VS Code. First, you open Terminal. Next, you run this command. And you run this command. I want to make sure, so I choose this version. After installing Python, we need to install VS Code, so you access this page. Here are many options, and I think you should choose this option. After downloading, we are installing it. Now you need to cd to the folder which contains the file just downloaded. Maybe your file is in the downloads. And maybe this command will cd to the downloads folder. After cd, you run this command. You've installed the VS Code successfully, right? And you can open the app like this, right? Now we are installing some extensions on VS Code. Welcome back. Have you successfully installed Python and set up VS Code on your machine? In this lecture, we're going to write and run our very first Python program. This is a big moment. Let's start in VS Code. Step 1. Create a new file. You can do this by going to File, New File. I'm going to call mine hello.py. The .py extension is crucial. It tells the operating system and VS Code that this is a Python source code file. Then you click this blue line. I create a folder to contain the file. You click on the Create File button to create the file. Step 2. Write code. Now we're ready to write some code. As is tradition in programming, our first program will simply print the message hello, world, to the screen. Type the following single line of code. Print, hello world. In this line, print is a built-in function in Python. Functions are blocks of code designed to perform a specific task. And the text inside the parentheses, hello, world, is the data we want that function to act upon, which is called an argument. Step 3. Make sure you save your file again after typing the code. Step 4. Now let's run it. In VS Code, open the integrated terminal. Before opening terminal, I will open the folder for the VS Code first. To open terminal, you go to the top menu, Terminal, and selecting New Terminal. To run the file, you type the command Python3 followed by the name of your file, hello.py, and press Enter. There it is. Hello world. You have successfully written and executed your very first Python program. Congratulations. This simple program demonstrates the basic structure of Python code. A file with a .py extension containing statements. In this case, one call to the print function. In our next lecture, 2.4, Comments, we will cover how to add explanatory notes to your code that the Python interpreter ignores. See you there. Welcome back. In our last lecture, we successfully ran our first Python program. Today, we're going to cover a fundamental concept: comments. I don't recommend you to use them. A legendary programmer will not have a single comment in his code, right? A comment is a line of text that the Python interpreter completely ignores when running your program. Its purpose is to provide information. 1. Single-line comments. In Python, we create a single-line comment by starting the line with the hash symbol or #, hashtag. Notice how I can put the comment on its own line, or I can put it immediately after a line of code to explain that specific line. When you run this file, the interpreter skips everything after the hashtag and just executes the print function. Let's quickly run it again. See? The comments are strictly for us. 2. Multi-line comments, docstrings. Sometimes you need a block of text to explain a function or a complex part of your script. While Python doesn't have a specific multi-line comment syntax, we typically use docstrings for this purpose. Docstrings are strings enclosed in 3 single quotes or 3 double quotes. They are often used right after a function or class definition to provide documentation. Since these strings are not assigned to a variable, the interpreter effectively ignores them, allowing them to function as multi-line comments. To recap, use the hash symbol for quick, one-line notes, and use triple quotes for longer blocks of documentation. Now that we know how to write code and note it in our next lecture, 2.5, Python indentation. See you then. Welcome back. We're wrapping up our setup section with a lecture on arguably the single most important syntactic rule in Python: indentation. In most programming languages, curly braces are used to define blocks of code, like the body of a function or a loop. In Python, we use indentation for this purpose. It is mandatory, not optional. What is indentation? Indentation refers to the spaces or tabs placed at the beginning of a line of code. In Python, when you start a new block of code, you must indent it. You can use 4 spaces for each level of indentation. Fortunately, modern editors like VS Code usually handle this automatically for you. Here, the two print statements that say, "Welcome, administrator," and "access granted," are part of the if block because they are indented. The final print, "program continues," is not indented, so it runs regardless of the if condition. When we run this, if is admin is true, all three lines run. If is admin is false, only the last line runs. Python uses the indent to determine the scope of the block. The critical rule. If you did not indent like this, it will raise an immediate error called an indentation error. So, remember, indentation is not style in Python. It is syntax. When you see a line ending in a colon, like after if, for, or def, you know the next logical line must be indented to start a new block. That concludes our setup section. You now have your environment ready, you can run your first script, you know how to comment your code, and you understand the importance of Python indentation. I'll see you in lecture 3.1 of the next section. Hello and welcome to section 3 of our course. We've completed our setup and gotten a taste of running our first script. Now, we move on to the fundamental building blocks of all programming languages. Data types. What are data types? In simple terms, a data type is a classification that specifies which type of value a variable has and what kind of mathematical, relational, or logical operations can be applied to it. Think of it like a container that not only holds something but also dictates what you can do with what's inside. When you write a program, you work with different kinds of information: numbers, text, dates, true, false values, and more complex collections of data. Python needs to know what kind of information it's dealing with to store and manipulate it correctly. Section 3 Overview. In this section, we will cover the simple, fundamental data types before diving into the complex sequence types later in the course. Here is a quick look at what we'll master. Numeric types, lecture 3.2 and 3.3. This includes whole numbers, integers, numbers with decimal points, floats, and special numeric forms like complex numbers. Boolean types, lecture 3.4. These are the simplest type, representing just two values, true or false. They are essential for flow control and decision-making in code. We will also learn how to change data from one type to another using type conversion functions and discuss the rules for naming variables, known as identifiers. Understanding data types is non-negotiable. If you try to perform a mathematical operation on text, Python will throw an error. A strong grasp of these types will save you countless headaches as you build more complex programs. We'll kick off the core content of this section immediately in our next lecture, 3.2. Numeric types, where we'll explore integers and floating point numbers in depth. I'll see you there. Welcome back. In our study of data types, we are starting with the most common and fundamental type, numeric types. These types are used to store numbers, whether they are whole numbers or numbers with decimal points. Python has three primary numeric types, but we'll focus on the two: int for integers and float for floating point numbers. Let's jump into VS Code and see these in action. 1. The integer type int. An integer or int is a whole number, positive or negative, without a decimal point. One helpful built-in function we can use to confirm the type of any variable is the type function. Let's print the type of our student count variable. See how Python confirms that student count is of class int. A powerful feature of Python is that its integers have unlimited size. They can grow as large as your computer's memory allows, which is a major difference from many other programming languages that have size limits on their integer types. 2. The floating point type, float. A floating point number, or float, is a number, positive or negative, that contains a fractional part, typically represented with a single decimal point. Let's check the type of temperature. This confirms the type is float. Notice the last example, bank_balance equals 1000.00. Even though the value is technically a whole number, the presence of the decimal point, .00, makes Python treat it as a float. 3. Basic arithmetic. You can perform all standard arithmetic operations on these numbers. Notice something important here. Even though 7 and 2 are integers, the division operator always produces a float result in Python. If you specifically want the whole number part of the division, you use the floor division operator 2/. This operator throws away the decimal part, giving you an int result. So, to summarize, int for whole numbers which are unlimited in size and float for decimals. Keep them straight as they form the foundation for all quantitative work in Python. Our next lecture, 3.3, Complex, Binary, and Hexadecimal Types. I'll see you there. Welcome back. In our last lecture, we covered the standard numeric types, integers and floating point numbers. Today, we're going to explore some of Python's more specialized numeric types and representations, complex numbers, and the use of binary and hexadecimal formats. One. Complex numbers. Complex. A complex number is a number that comprises a real part and an imaginary part. In mathematics, the imaginary part is represented by I. In Python, we use j to denote the imaginary part. Here, 5 is the real part and 3j is the imaginary part. Python uses the complex data type to store and perform mathematical operations on these numbers, which is particularly useful in electrical engineering and scientific computing. 2. Binary, octal, and hexadecimal representations. While Python stores all numbers internally in binary, base 2, we usually work with them in decimal, base 10. However, Python allows us to represent numbers using other bases directly in our code. This is common when dealing with low-level systems, security, and memory addresses. Binary representation, base 2. To write a number in binary format, we prefix the digits with 0b. The number 0b1010 is interpreted by Python as the decimal number 10. The 0b simply tells Python how to read the digits that follow. Hexadecimal representation, base 16. To write a number in hexadecimal format, we prefix the digits with 0x. Hexadecimal uses digits 0 to 9 and letters A to F to represent values up to 15. The number 0xa is also interpreted as the decimal number 10. Note that Python also supports octal base 8 using the 0 prefix, but it is much less common than binary and hex. We go to built-in conversion functions. Python provides simple functions to convert between these formats. The bin function returns the binary string representation. The hex function returns the hexadecimal string representation. The int function can convert a string in any base back to a decimal integer. To summarize, Python handles specialized numbers like complex using j. For low-level representation, you can use the 0b prefix for binary and 0x for hexadecimal. Now that we've finished with the numeric types, we move on to one of the simplest yet most vital data types for programming logic, the Boolean type. I'll see you in lecture 3.4. Welcome back. We've spent time covering the different ways Python handles numbers. Now, we are moving on to the simplest, yet arguably the most powerful data type in all of programming, the Boolean type. A Boolean value, or bool type in Python, represents one of only two possible states, true or false. These values are the foundation of decision-making and flow control in every computer program. In Python, these two values must start with a capital letter, true and false. Remember, if you type true with a lowercase t, Python will treat it as an undefined variable, not a Boolean value. You rarely create a Boolean value directly like we just did. Instead, they are generated automatically when you use relational operators, which are operators that compare two values. Let's see some examples of how these comparisons work. Every time you use a relational operator, Python evaluates the statement and returns a Boolean, either true or false. 3. The power of Booleans, flow control. The real power of Booleans comes when we use them to control the flow of our program. This is done primarily with the if statement we introduced earlier. Because the comparison user age is greater than or equal to 18 evaluates to false, the code executes the else block. Booleans are the literal gatekeepers of your code. To summarize, the Boolean type is the simplest but most essential data type, representing the two possible logical states. It is created using comparison operators and is used to drive every decision in your program. In our next lecture, 3.5, Type Conversion Functions, we will learn how to manually change data from one type to another, like converting a number into text, or vice versa. See you then. Welcome back. We've seen several Python data types. But what if you have data of one type, like a number, and you need to treat it as a different type, like text? This is where type conversion functions come in. This ability to explicitly change a data type is called typecasting. In many programs, especially when taking input from a user, data comes in as a string, but you need to convert it to a number to do math. This is a critical skill. The int function is used to convert a value into an integer. It's important to note, when converting a float to an int, Python doesn't round. It simply truncates the decimal part. Also, if you try to convert a string that contains a decimal or non-numeric characters, Python will raise a value error. 2. Converting to float. The float function converts a value into a floating point number. This is useful if you need to ensure a number is treated with decimal precision for future calculations. 3. Converting to string. The street function is essential for converting any value, be it numbers, booleans, or something else, into text. This is most often needed when you want to concatenate or join a number with other text. Once the number 30 is converted to a string 30, we can safely join it with other text. 4. Converting to Boolean. The bool function converts a value into its Boolean equivalent. The rule is very simple. 0 and empty values are converted to false. Non-zero and non-empty values are converted to true. This understanding of truthiness is very powerful for writing concise if statements. To summarize, Python provides built-in functions like int, float, str, and bool for explicit type conversion, allowing you to manipulate your data correctly. That covers our type conversion functions. In our next lecture, 3.6, Identifiers, see you there.
Welcome back. In this final lecture of our data type section, we are going to cover the essential rules for naming variables, functions, classes, and other objects in Python. These names are collectively called identifiers. Choosing good, descriptive names is a hallmark of a good developer, but first, you must know the strict rules Python enforces. 1. The strict rules. There are 4 non-negotiable rules for creating an identifier in Python. If you break these rules, your code will fail with a syntax error. Rule 1. Start with a letter or underscore. An identifier must start with a letter, capital A to capital Z or lowercase a to lowercase c, or an underscore. It cannot start with a number. Rule 2. Cannot contain special characters. An identifier can only contain letters, numbers, and the underscore. You cannot use spaces, dashes, exclamation points, or any other special characters. Rule 3. Case-sensitive. Python is completely case-sensitive. This means that identifiers with the same spelling but different capitalization are treated as entirely separate names. Rule 4. Cannot be a Python keyword. You cannot use any of Python's reserved keywords, like if, for, while, print, class, def, true, false, etc., as an identifier. These words already have special meaning to the Python interpreter. If you try to use a keyword, Python will raise a syntax error. Two, style convention, PEP8. While the first 4 points were mandatory, the final point is a convention recommended by PEP8, which is Python Style Guide. It's important for readability. For variables and function names, the widely accepted standard is snake case, all lowercase letters, with words separated by underscores. Mastering these rules ensures you don't run into annoying syntax errors, and following the style guide makes your code is readable and professional. This concludes our section on data types. We covered numbers, booleans, and how to name them. Next up, we move to a new section, Section 4, Sequence Types. I'll see you in Lecture 4.1. Hello, and welcome to Section 4, Sequence Types. We've laid the groundwork by covering single data values, the numbers and booleans, and now we're ready to move on to the first great challenge and huge asset of Python, collections of data. 1. What is a sequence? A sequence is a collection of items where each item is stored in a specific order, and each item can be accessed by its position or index. Think of a sequence like a train. Every car is connected in a line, and you can point to the first car, the second car, and so on. Unlike a single int or float, a sequence allows us to group related pieces of data together. Two, types we will cover. In this large and critical section, we will learn the 3 most important built-in sequence types: strings, lists, and tuples. We'll also cover sets and the incredibly important dictionary, which is a mapping type but often taught alongside sequences. We'll start with strings. A string is simply a sequence of characters used to store text. We'll learn how to create them, access individual characters using slicing, and modify them using various string methods. Next, we'll move to the list. Lists are incredibly flexible and are used to store multiple items of potentially different data types, and they are fully modifiable. Finally, we'll study the tuple, which is similar to a list but has a crucial difference. It is immutable, meaning it cannot be changed after creation. We'll compare lists and tuples to know when to use each. As we explore these types, we will consistently use 3 key concepts: indexing to access a single item, slicing to access a range of items, and understanding mutability, the ability to change data, versus immutability, the inability to change data. You should learn these sequence types. They are the tools you will use to manage almost all the data in every program you write. We'll start right away with the most common sequence you already use: text. Join me in the next lecture for point 2, Create a String, where we'll dive into the world of text manipulation.
Welcome back. We are kicking off our deep dive into sequence types by starting with the most familiar one, the string. A string is simply a sequence of characters, and it is Python's data type for handling text. 1. How to create a string. In Python, the fundamental rule for creating a string is that you must enclose the text in quotes. Python is flexible and allows 3 main ways to do this: single quotes, double quotes, and triple quotes. About single and double quotes, the most common ways are using single quotes or double quotes. They are generally interchangeable. Why have 2 options? They help when you need to include a quote character inside your string. For example, if you need a contraction like it's best to use double quotes on the outside. About triple quotes. Triple quotes are primarily used for creating strings that span multiple lines, like paragraphs or blocks of documentation. Two, strings are sequences. The key takeaway here is that a string is a sequence. This means 2 things. It is ordered, and we can access individual characters using an index. In Python, like many languages, indexing starts at 0. The first character is at index 0, the second at index 1, and so on. We use square brackets after the string variable name to access a character by its index. Python also supports negative indexing, which counts backward from the end of the string. The last character is always at index -1. This is a very convenient feature when you don't know the exact length of the string. Now that we know how to create a string and access a single character, in our next lecture for point 3, slicing a string, we'll learn how to extract a subset or range of characters from a string. I'll see you there.
Welcome back. In our last lecture, we learned how to access a single character in a string using its index. In this lecture, we're going to learn an extremely useful technique called slicing, which allows you to extract a subset or range of characters from a string. One, the basic slice syntax. Slicing allows you to get a part of the sequence, not just one element. The syntax for slicing is very straightforward, using square brackets and the colon operator. String name open bracket start colon end close bracket. Let's use the string programming for our examples. 2. The golden rule of slicing. When you use slicing, the sequence starts at the start index and goes up to, but does not include, the end index. Notice that we started at O, index 2, and stopped just before our index 5. 3. Omitting start and end values. You can simplify the slice syntax by omitting the start or end index. Omitting the end index. If you leave the end index blank, Python will slice from the start index all the way to the end of the string. Omitting the start index. If you leave the start index blank, Python will slice from the beginning of the string up to the end index. Omitting both, the copy leaving both blank creates a copy of the entire string. 4. Slicing with negative indices. We can also use negative indices, which work great for pulling subsets from the end of a string. To summarize, string slicing is a powerful tool to extract parts of a string using the sub start colon end notation. The key rule is that the end index is non-inclusive. This is just the start. In our next lecture, 4.4, Steps in Slicing, I will introduce a third optional component to the slice syntax that allows us to skip characters. See you there. Welcome back. We've already learned the basic string slice syntax, sub start, colon, end. In this lecture, we're going to unlock the final, powerful component of the slicing operator, the step argument. One, the full slice syntax. The full syntax for slicing includes a third value, separated by another colon, called step. String names sub start, colon, end, colon step. The step argument tells Python how many characters to skip after retrieving each character. By default, the step value is 1, meaning we retrieve every character in the range. Let's use our previous example string, programming. 2. Positive step values. If we set the step value to 2, Python will jump 2 characters for every character it selects. Notice that when we omit the start and end indices, the step applies to the entire string. We can also combine the step with a specific range. Three, negative step values. The most common and useful application of the step argument is setting it to -1. A negative step tells Python to move backward through the sequence. If we use this with empty start and end indices, we reverse the entire string. When using a negative step, you also need to adjust your start and end indices. The start index should be greater than the end index for the slice to work in reverse order. To summarize, the third argument in slicing, step, controls how many characters to skip. A positive step moves forward, and a negative step, especially -1, is the Pythonic way to quickly and easily reverse a string. That completes our indexing and slicing strings. Next up, we'll move on to manipulating text with some useful built-in string methods, starting with how to clean up extra whitespace in Lecture 4.5. Strip the spaces. See you there.
Welcome back. We've learned how to read and extract subsets of text using indexing and slicing. Now, we begin exploring string methods, built-in functions that perform actions directly on a string object. We start with 3 essential methods used for data cleaning, the strip methods. One, the problem whitespace. A very common issue when accepting user input or reading data from files is extra whitespace. Spaces, tabs, or new lines attached to the beginning or end of a string. This can cause problems when trying to compare strings or use them in lookups. Let's look at an example. 2. The strip method. The strip method is your primary tool for cleaning up this whitespace. It removes any leading, beginning, and trailing end whitespace characters. Notice that the space between Python and course is preserved. The strip method only targets whitespace at the edges. 3. The specific stripping methods. What if you only want to remove spaces from one side? Python provides 2 specific methods for this, lstrip and rstrip. Lstrip stands for left strip, and it removes only the white space from the left, beginning, side of the string. Our strip stands for right strip, and it removes only the white space from the right, trailing, side of the string. 4. Important concept, immutability. It is crucial to understand that strings in Python are immutable. This means that when you use a method like strip, you are not changing the original user input variable. Instead, the method creates and returns a new string with the changes. That's why we must assign the result to a new variable like clean input, or assign it back to the original variable like user input equals user input.strip. To summarize, the strip methods are fundamental for data cleanup, allowing you to remove unwanted leading and trailing whitespace, while lstrip and rstrip give you granular control over which end to clean. In our next lecture, 4.6, few more string methods, we will explore other essential string methods for tasks like changing case, checking content, and finding substrings. I'll see you there.
Welcome back. In our last lecture, we covered the essential strip methods for cleaning whitespace. Today, we're going to look at several other indispensable string methods for common text manipulation tasks, changing case, checking content, and finding substrings. 1. Case conversion methods. Python makes it very easy to change the case of text, which is important for standardizing data. The lower method converts all characters to lowercase. The upper method converts all characters to uppercase. The title method capitalizes the first letter of every word. Two, content checking methods. These methods are incredibly useful for validation. They all return a Boolean value, true or false. Starts with, checks if the string begins with a specified substring. Ends with, checks if the string ends with a specified substring. Is digit, checks if all characters in the string are digits, 0 to 9, and if the string is not empty. 3. Substring finding methods. The find method is used to locate the starting index of a substring within the string. Find returns the lowest index where the substring is found. If the substring is not found, it returns -1. Replace returns a new string with all occurrences of an old substring replaced by a new one. To summarize, these string methods give you powerful, concise tools for common text tasks, from formatting user names to validating file types. Always remember that they return a new string, they do not modify the original. That wraps up our study of the string sequence type. Next, we move on to the second and arguably most versatile sequence type in Python, the list. Join me in lecture 4.7. Create a list. See you there. Welcome back. We've learned strings, which are sequences of characters. Now, we move on to Python's powerful and flexible sequence type, the list. 1. What is a list? A list is an ordered collection of items. Unlike a string, a list has two key features that make it special. Mutable. Lists can be changed after they are created. You can add, remove, or modify elements. Heterogeneous. A single list can hold elements of different data types, integers, strings, floats, and even other lists, all at the same time. 2. How to create a list. To create a list, you enclose its elements in square brackets and separate the elements with commas. A. Empty list and mixed data. You can start with an empty list or create one with diverse elements. B. List of lists, nested lists. Because a list can contain any type of object, it can even contain other lists. This creates what's sometimes called a nested list or a matrix. 3. Accessing elements, indexing. Just like strings, lists are ordered sequences, so we use zero-based indexing and square brackets to access elements. We can also use negative indexing, where -1 refers to the last element. 4. Accessing nested elements. To access an element inside a nested list, you use two sets of square brackets. The first bracket gets the inner list and the second gets the element inside that inner list. To summarize, the list is the flexible container in Python created using square brackets. It is both ordered, accessible by index, and fully changeable. Knowing how to create a list is step 1. Next, we will cover the list's most powerful feature, its mutability, by learning how to add and remove elements in Lecture 4.8. See you there. Welcome back. The defining characteristic of a list is its mutability, the ability to change it after creation. In this lecture, we will learn the essential methods for adding elements to a list and removing them. 1. Adding elements. Python provides 3 primary methods for adding items to a list: append, insert, and extend. Let's start with a list of names. A. Appending, append. The append method adds a single element to the end of the list. This is the most common way to add items. B. Inserting, insert. The insert method allows you to add a single element at a specific index. It takes 2 arguments, the index position and the item itself. C. Extending, extend. The extend method is used to add all the elements from another list or any iterable to the current list. 2. Removing elements. You have several ways to remove elements, depending on whether you know the item's value or its index. A. Removing by value, remove. The remove method removes the first occurrence of a specified value from a list. If the item is not found, it will raise a value error. B. Removing by index, pop. The pop method removes the element at a specified index and returns that element. If no index is specified, it removes and returns the last item. The pop method is useful when you need to use the removed item later, such as when implementing a stack data structure. C. Removing a range, del keyword. The del keyword, short for delete, is a general Python statement used to delete objects, including removing elements from a list by index or by slice. To summarize, use append for the end, insert for a specific spot, and extend to merge lists. Use remove to delete by value, pop to delete by index and retrieve the item, and the del keyword to remove by index or slice. We've covered the core manipulation methods. In our next lecture, 4.09, few more list functions, we will explore other essential list methods for sorting, counting, and finding elements. See you there. Welcome back. In our last lecture, we learned how to add and remove elements from a list. Today, we'll cover the remaining essential built-in list methods that help us analyze, order, and count items within our lists. 1. Ordering and reversing lists. These methods allow you to change the sequential order of elements in the list. Let's define a list of numbers. A. Sorting sort. The sort method reorders the list elements in ascending order, from smallest to largest. Crucially, this method modifies the list in place, meaning it changes the original list directly and does not return a new one. B. Reversing, reverse. The reverse method simply reverses the current order of the elements in the list. Like sort, it also modifies the list in place. 2. Finding and counting elements. These methods help you locate and quantify items. Let's use a list of names to demonstrate counting and finding. A. Counting, count. The count method returns the number of times a specified element appears in the list. B. Finding index, index. The index method returns the index of the first occurrence of a specified element. If the specified element is not found in the list, the index method will raise a value error. 3. Clearing the list, clear. Finally, the clear method removes all elements from the list, making it an empty list. To summarize, use sort and reverse for reordering, count to check frequency, and index to find the position of the first occurrence of an element. Remember that lists are mutable, so sort and reverse change the original list directly. We've now learned the list data type. Next, we move on to its sibling sequence, the tuple. Join me in Lecture 0410. Tuple to learn about this sequence. See you there. Welcome back. We've spent a lot of time on the list, Python's extremely flexible and mutable sequence. Now, we introduce the tuple. 1. What is a tuple? The difference. A tuple shares two key characteristics with a list. It is an ordered sequence. Items have a fixed position, accessible by index. It can hold heterogeneous data types, mixed types like strings, integers, etc. However, the major difference, and the entire purpose of the tuple, is that it is immutable. For list, mutable, and parentheses for tuple, immutable. 2. How to create a tuple. Tuples are created using parentheses, in contrast to the square brackets used for lists. A. Creating a tuple with one element. The comma trick. A common pitfall for beginners is creating a tuple with a single element. If you use parentheses alone, Python treats it as a grouped expression. To make a single element tuple, you must include a trailing comma. B. Tuple packing, parentheses optional. Interestingly, the parentheses are often optional when creating a tuple. The items separated by commas are what defines it as a tuple. This is called tuple packing. 3. Accessing elements. Since a tuple is an ordered sequence, accessing elements is identical to how you access elements in a list or string, using zero-based indexing and square brackets. 4. Demonstrating immutability. Now for the crucial point. If you try to change, append, or remove an element, Python throws a type error. This immutability is why tuples are often used for data that should remain constant throughout the program, such as coordinates or configuration settings. Understanding the nature of the tuple is step 1. In our next lecture, 04.11, Use a tuple, we will look at powerful ways to unpack and use tuples in real-world scenarios, leveraging their inherent structure. See you there. Welcome back. In our previous lecture, we introduced the tuple and its core feature, immutability. Today, we will explore practical ways to utilize tuples, specifically focusing on tuple unpacking and using them for function returns. 1. Tuple unpacking. Tuple unpacking is one of the elegant and useful features in Python. It allows you to assign elements of a tuple directly to multiple variables in a single line. This feature is also commonly used for swapping variable values efficiently without needing a temporary variable. 2. Multiple return values from functions. In Python, functions can technically only return one object. However, by packaging multiple values inside a tuple, the function can effectively return multiple items, which can then be unpacked by the caller. Three. Tuples as dictionary keys. A crucial point about dictionaries is that their keys must be immutable. Since tuples are immutable, they can be used as dictionary keys, which lists cannot. This is ideal for composite keys, such as geographical coordinates. The immutability of the tuple guarantees that the key's hash value remains constant. To summarize, tuples are vital for clean code through unpacking, for handling multiple return values from functions efficiently, and for creating reliable, composite keys in dictionaries due to their immutability. Next up, we will explicitly compare the two main sequence types in Python. Join me in Lecture 04.12. List to tuple to see how these types relate and differ. Welcome back. We've learned about lists, mutable, and tuples, immutable. Now, let's explore how to easily convert data between these two essential sequence types using Python's built-in functions. 1. Converting list to tuple. To convert a list into a tuple, we use the built-in tuple function. This is necessary when you want to ensure the data cannot be changed afterwards, like securing configuration data. 2. Converting tuple to list. Conversely, if you have a tuple and need to modify its contents by adding or removing items, you must first convert it to a list using the built-in list function. 3. Mutability in action. Now that the data is in a list, we can use any of the list methods we learned before, such as append or remove. Once all modifications are done, you can convert it back to an immutable tuple if needed, for safety or performance benefits. To summarize, use the list function to gain mutability for modification, and the tuple function to lock down data for safety or use as dictionary keys. We've learned how to use both lists and tuples. In our next lecture, 04.13, List versus tuple, we will directly compare them to help you decide which one to choose in any given scenario. See you there. Welcome back. We've dedicated time to learning both lists and tuples. Now, it's time for the ultimate showdown, list versus tuple. We'll compare their core differences, syntax, and when to use each one. 1. Mutability versus immutability. The single most important distinction is that lists are mutable, meaning you can change them after creation. Tuples are immutable, meaning their elements are fixed forever. Let's demonstrate. We can easily modify a list element. However, attempting the same operation on a tuple results in an error. 2. Syntax and creation. Lists are created using square brackets. Tuples use parentheses. Both support indexing and slicing in the same way. 3. When to use which, use a list when you need a sequence that will change. Data being collected, dynamic shopping carts, or structures like queues and stacks. Use a tuple when the data must remain constant, coordinates, database records, or composite dictionary keys. To summarize, lists are flexible and dynamic, while tuples are fast, safe, and reliable for fixed data. Choose list for change. Choose tuple for permanence. That concludes our coverage of lists and tuples. Up next, we move on to another sequence type, the set. Join me in Lecture 04.14. Set type. Welcome to a new sequence type, the set. Sets are primarily used to store multiple unique items in a single variable. In this lecture, we'll learn how to create and modify sets and understand their key characteristics. 1. Creating a set. Sets are created using curly braces, much like dictionaries, but they only contain values, not key-value pairs. Crucially, sets automatically discard any duplicate values. An important note, to create an empty set, you must use the set function, as empty curly braces create an empty dictionary. 2. Adding elements to a set. Since sets are mutable, you can add new items using the add method for a single item, or the update method to add multiple items from another iterable, like a list or tuple. 3. Removing elements from a set. You can remove elements using the remove method or the discard method. The difference is critical. Remove will raise an error if the item is not found, while discard will not. To summarize, sets are defined by curly braces, enforce uniqueness, and lack order. Use add or update to add items, and choose between remove or discard for removal based on whether you want to handle potential errors. In our next lecture, 04.15, Frozen Set, we will look at an immutable version of the set, useful when you need a fixed collection of unique items. See you there. Welcome back. In our last lecture, we explored the mutable set type. Now, we introduce its immutable counterpart, the frozen set. This special type combines the uniqueness of a set with the safety of immutability, similar to how tuples relate to lists. 1. Creating a frozen set. You create a frozen set using the built-in frozen set function, passing any iterable, like a list, tuple, or an existing set, as an argument. Like regular sets, the frozen set automatically removes duplicates upon creation, and the order of elements is not guaranteed. 2. Immutability in action. Because frozen sets are immutable, they do not have methods that change their content, such as add, remove, or discard. Attempting to use them will result in an attribute error. 3. Primary use case. Dictionary keys. The main reason for the existence of frozen sets is that they are hashable due to their immutability. This makes them suitable for use as keys in dictionaries or as elements within a regular set, which mutable sets cannot do. To summarize, use the frozen set function to create a fixed collection of unique items. Its immutability ensures safety and allows it to be used as a key in mapping data structures. We have covered lists, tuples, sets, and frozen sets. Up next, we'll explore another built-in sequence that generates numbers, the range type. Join me in Lecture 04-16. Range type. Welcome back. In this lecture, we explore the range type, a special immutable sequence primarily used to generate sequences of numbers for iteration, particularly in for loops. It is highly efficient because it doesn't store all numbers in memory. 1. Range syntax. The range function takes up to 3 arguments: stop, start, and step. The most common form is providing just the stop value. If you only provide the stop argument, the sequence starts from 0 and goes up to but not including the stop number. Providing both start and stop defines the starting point, but still excludes the stop value. The optional step argument controls the increment or decrement between numbers in the sequence. 2. Using range for indexing. The range type is extremely useful when you need to access elements of a list or other sequence by index. To summarize, the range type is an immutable sequence that generates numbers on demand, making it memory efficient. It is indispensable for defining loop boundaries and generating indices. In our next lecture, 04.17, Bytes and Byte Array, we will examine binary sequence types used for handling raw binary data, like images or network packets. See you there. Welcome back. In the digital world, data isn't just text, it's also raw binary data, like images, audio, or network packets. Python provides 2 sequence types for handling this, bytes and byte array. We will explore how to create them and the crucial difference between them. 1. Creating bytes and byte array. Both types can be created by prefixing a string literal with b, or by using their respective constructor functions. Crucially, they store sequences of integers ranging from 0 to 255. The byte's literal starts with b. Note that when you index a byte's object, it returns the integer value of that byte, not a single character string. The byte array is created using the constructor function. We typically use the encode method on a regular string before passing it. 2. Mutability difference. Since bytes are immutable, you cannot change individual elements. Byte array, being mutable, allows you to change the value of any byte by assigning a new integer between 0 and 255. If you try to change a byte's object, Python will raise a type error. To summarize, use bytes for fixed, binary data, and byte array when you need to modify the binary data in place, such as manipulating a buffer or receiving stream data. We've learned the core sequential collection types. Next, we revisit the dictionary type in detail, focusing on its structure and use cases. Join me in Lecture 04.18, Dictionary. Welcome back. We now move to the dictionary type, one of the most powerful and flexible data structures in Python. Dictionaries store data in key-value pairs, which allows for extremely fast data retrieval. 1. Creating a dictionary. Dictionaries are created using curly braces and separating keys from values using a colon. The keys must be unique and immutable, while the values can be of any type and can be duplicated. 2. Accessing elements. Instead of using numerical indices like lists, you access dictionary values by referring to their key, enclosed in square brackets. If the key does not exist, this method raises a key error. Alternatively, you can use the get method, which returns none or a specified default value if the key is not found, making it safer. 3. Modifying elements. Dictionaries are mutable. To change a value, you simply access the key and assign a new value. If the key does not exist, this action adds a new key value pair to the dictionary. To summarize, dictionaries use keys for lightning-fast retrieval, are mutable for easy modification, and are ideal for modeling real-world objects where data points have descriptive labels. In our next lecture, 04.19, Immutability, we will delve deeper into the concept of immutability and why it is a core feature in Python's design. See you there. Welcome back. We've seen concepts like lists being mutable and tuples being immutable. Now, let's dedicate a lecture to truly understanding immutability, a fundamental concept in Python that impacts data safety, hashing, and performance. 1. Core definition and identity. An immutable object is one whose value cannot change. If you appear to change an immutable object, you are actually creating a brand new object in memory and reassigning the variable to point to it. For mutable objects like a list, its memory address, or ID, remains the same even after modification. For immutable objects like a string or tuple, any operation that modifies it results in a new object with a new memory ID. 2. Why immutability matters. The key reason is hashing. Only immutable objects can be hashed, meaning they have a constant hash value. This makes them eligible for use as dictionary keys or elements in a set, both of which require constant hash values for fast lookup. Since a list can change, its hash value would change, breaking the lookup structure of dictionaries and sets. To summarize, mutable types can be modified in place. Immutable types cannot be modified and are required for dictionary keys and set members due to their consistent hashability. Our next lecture 04.20, Datatypes patient use case. Welcome back. We've learned the core Python data types: numbers, strings, lists, tuples, sets, and dictionaries. Now, it's time to see how they fit together to model real-world data in a use case, specifically focusing on patient clinical data. 1. Defining patient data structure. We will model a single patient using a dictionary, as it allows us to use descriptive keys like name and age. We'll use strings for the ID and name, and an integer for the age. Next, we add the patient's vitals and medication history, which requires sequence types. 2. Using lists and tuples. Vitals, like heart rate and blood pressure, are measured over time and change frequently. We'll use a list to store these records, reflecting mutability. Notice that each individual reading is stored as a tuple, guaranteeing that the blood pressure and heart rate pair remains fixed and consistent. 3. Using sets for unique data. Allergies must be unique. A patient cannot have the same allergy listed twice. Therefore, a set is the perfect type to store this information, ensuring data integrity. To summarize, we modeled complex data by strategically choosing data types: dictionary for structure, lists for mutable history, tuples for fixed data points, and sets for unique constraints. We will continue exploring application-based data modeling in our next lecture, focusing on how lists and dictionaries interact. Join me in Lecture 04.21, Map of Lists Use Case. Welcome back. In our last lecture, we used different data types to model patient information. Now, we will focus on a common and important data structure known as a map of lists, which means a dictionary where every key maps to a list of values. 1. Defining the structure. This structure is ideal for tracking categorized data, like inventory or sales, where you have a unique category key and multiple items belonging to that category. We will use it here to track different types of fruits. 2. Accessing and iterating data. Accessing data involves two steps. First, retrieve the list using the dictionary key, and second, access the item inside that list using its index. You can easily iterate through both the categories and the items within each category. 3. Modifying the map of lists. Since both the dictionary and the inner lists are mutable, we can add, remove, or modify items easily. We can also add a new category key with its own empty list, ready for data. To summarize, the map of lists structure provides a flexible and logical way to group and manage related sets of data, leveraging the key-based organization of a dictionary and the ordered, mutable nature of lists. This concludes our sequence types. We now move on to Chapter 5, Special Types. Join me in Lecture 05.01, None Type. Welcome to Chapter 5, Special Types. We begin this chapter by exploring none, a unique constant in Python used to represent the absence of a value. Understanding none is crucial for handling defaults and function return values. 1. Definition and type. None is a single value, a constant defined by Python. It is not zero, it is not an empty string, and it is not false. It belongs to its own data type, none type. 2. None in functions. By default, if a function does not have an explicit return statement, Python automatically returns none. None is often used as a default value for optional function arguments, allowing the code to later check if a value was actually passed by the user. 3. Comparison with none. When checking if a variable is none, the preferred and most robust method is to use the identity operator, is. To summarize, none is Python's way of saying no value here. Use it for initializing variables, defining default arguments, and checking the return status of functions that don't explicitly return data. In our next lecture, 05.02, Escape chars, we will learn how to deal with special characters within strings that are usually difficult to represent directly, like quotes or new lines. See you there. Welcome back. When working with strings in Python, you often encounter situations where you need to include special characters, such as quotes or new lines, that normally terminate the string. This is where escape characters come in, allowing you to insert these literal symbols using a backslash. 1. Escaping quotes. A common use case is inserting a quote inside a string that is defined by the same type of quote. We use a backslash to tell Python to treat the quote literally. 2. Common escape sequences. Besides quotes, Python supports several common escape sequences for formatting and special characters. The backslash n inserts a new line and backslash t inserts a horizontal tab space. 3. The raw string. When dealing with file paths, especially on Windows, or when using regular expressions, Python's default interpretation of backslashes can lead to errors, as you saw with the truncated Unicode escape. The solution is the raw string. By prefixing the string with r, we instruct Python to treat every backslash literally, resolving the Unicode error and correctly representing the file path. To summarize, use the backslash to escape characters and insert special formatting. Use raw strings when you need to treat backslashes as literal characters, particularly for file paths or complex patterns, to avoid unexpected syntax errors. In our next lecture, 05-03, Constants, we will discuss how to define and use constants in Python, a concept important for writing clean and maintainable code. See you there! Welcome back. In many programming languages, a constant is a variable whose value cannot be changed after assignment. However, Python does not have true, built-in constants. Instead, it relies on strict naming conventions and developer discipline to define values that should remain fixed. 1. The Python convention. To signify that a variable should be treated as a constant, Python programmers use a naming convention known as screaming snake case. This means using all capital letters, with underscores separating words. When another programmer sees a variable named like this, they understand that its value should not be modified during the program's execution. 2. Constants versus variables. It is important to remember that this is only a convention. Python will not prevent you from reassigning a constant's value. This means the enforcement is purely voluntary and relies on developer discipline. Always respect the screaming snake case convention to maintain code clarity and integrity. 3. A good practice. For large projects, it is a good practice to define all constants in a single, dedicated file, often named constants.py. This centralized location makes them easy to manage and import across your entire codebase. To summarize, use screaming snake case for constants to communicate intent to other developers. Although Python permits changes, maintaining the value ensures the integrity of your fixed settings. We have defined constants using convention. In our next lecture, 05.04, del keyword, we will learn how to permanently delete references to objects and objects themselves from Python's memory. See you there! Welcome back. The del keyword is a powerful but often misunderstood tool in Python. It stands for delete, and its primary purpose is to remove names or references from the program's scope. This often leads to the deletion of the underlying object from memory. 1. Deleting a variable reference. When you use del on a variable, you are deleting the name that points to the object, not necessarily the object itself. Once the name is deleted, trying to access it will result in a name error. If the object has no more references pointing to it after the deletion, Python's garbage collector will automatically remove the object from memory. 2. Deleting items from sequences. The del keyword is one of the standard ways to remove elements from mutable sequence types, such as lists and dictionaries, using either an index or a key. To summarize, the del keyword is used to remove a name from the current namespace. When used on sequences, it removes elements based on index or key. If the underlying object has no more references, it is marked for garbage collection. This completes our look at individual special types. Our next lecture, 0505, Data Type Summary. See you there. Congratulations! We have now completed our comprehensive study of Python's core data types. This final lecture of the chapter will summarize something we have learned, providing you with a mini sheet to choose the right type for your data. Let's look at the big picture. The most critical attributes to remember are mutability, can it change, and order, is it indexed? Note that while dictionaries preserve insertion order in modern Python, they are technically accessed by key, not by numerical index. When deciding which type to use, categorize them by their behavior. Use these when your data needs to be modified, extended, or updated frequently. Use these for fixed data constants, dictionary keys, or when you need to ensure data safety. Finally, remember the special utility types we covered in this chapter. You now possess the building blocks of Python. The next step is learning how to manipulate these blocks using operators. We are now moving to Chapter 6, Operators and Operands. We will start with Lecture 0601, Arithmetic Operators. See you there. Welcome to Chapter 6, Operators and Operands. In this chapter, we will learn how to manipulate data. We start with arithmetic operators, which are symbols used to perform mathematical operations like addition, subtraction, multiplication, and division. 1. Basic operations. Python supports the standard 4 operations. A key thing to note is that the division operator, the /, always returns a float, even if the result is a whole number. 2. Modulus and floor division. Often you need integer results or remainders. The floor division operator, /, rounds the result down to the nearest whole number. The modulus operator, %, gives you the remainder. 3. Exponentiation. Finally, to raise a number to a power, Python uses the double asterisk operator. Do not use the caret symbol, as that performs a bitwise operation. To summarize, Python provides a complete set of arithmetic operators. Remember that / is for float division, / is for integer division, and * is for exponents. Now that we can perform math, we need to learn how to store the results back into variables. Join me in Lecture 06.02, Assignment Operators. Welcome back. We know how to calculate values, but calculations are useless if we don't save the results. Assignment operators are used to assign values to variables. Beyond the basic equals sign, Python offers compound operators to perform an operation and assignment in one step. 1. The basic assignment. The single equals sign is the fundamental assignment operator. It takes the value on the right and stores it in the variable on the left. 2. Compound assignment operators. Python allows you to combine an arithmetic operation with assignment. For example, plus equals adds a value to the variable and updates the variable with the new result. This shorthand works for all arithmetic operators: subtraction, multiplication, division, and even modulus. To summarize, compound assignment operators make your code cleaner and easier to read. Instead of writing x equals x plus 1, you can simply write x plus equals 1. Now that we can change values, we need to know how to compare them. Join me in Lecture 06.03, Comparison Operators. Welcome back. Comparison operators, or relational operators, are essential for control flow. They allow your program to make decisions by comparing two operands. Crucially, the result of any comparison operation is always a Boolean value, either true or false. 1. Equality and inequality. The most frequent comparison is checking if two values are equal, using the double equal sign, and checking if they are not equal, using the exclamation mark followed by the equal sign. 2. Greater than and less than. We use the familiar mathematical symbols for checking magnitude, including the combined operators for greater than or equal to and less than or equal to. Python is unique in allowing comparison chaining, which is a concise way to check if a value falls within a range. 3. Comparison with different types. You can compare different numeric types without issue, as Python handles the type conversion. String comparisons are based on alphabetical order, derived from the Unicode value of the characters. To summarize, comparison operators are the workhorse for logic, always yielding a Boolean result. Be mindful of the difference between the assignment operator, single equals, and the equality comparison operator, double equals. We can now compare single values. Our next lecture, 06.04, Logical Operators. See you there. Welcome back. Logical operators are the heart of decision-making in any programming language. They allow you to combine multiple comparison results or reverse a Boolean value. Python uses the keywords and, or, and not for these operations. 1. The AND operator. The AND operator returns true only if both operands, the left side and the right side, are true. If either is false, the entire expression is false. 2. The OR operator. The OR operator is more forgiving. It returns true if at least one of the operands is true. It only returns false if both operands are false. 3. The not operator. The not operator is a unary operator, meaning it only takes one operand. It simply reverses the logical state of its operand, turning true into false and false into true. To summarize, logical operators are one piece of the puzzle for building complex logical conditions. Remember that and requires strict compliance, while or allows for flexibility. We have learned the fundamental operators. In our next lecture, 06 to 05, Operators BMI Use Case. We will now put our knowledge of arithmetic and logical operators to work with a practical example, calculating the body mass index, or BMI. The BMI is calculated by taking weight in kilograms divided by the square of height in meters. 1. Arithmetic calculation. First, we define our inputs for weight and height. Then, we calculate the BMI using the division operator and the exponentiation operator. 2. Logical classification. Now we use comparison and logical operators to determine the category. The normal weight range is generally between 18.5 and less than 25. We use the AND operator to check both boundary conditions. We can similarly check for other categories, like if the person is underweight, which uses the less than operator. To summarize, we combined arithmetic operators for calculation and comparison operators with the AND logical operator to classify the result, demonstrating a real-world application of the concepts in this chapter. This concludes our chapter on operators and operands. We now move to Chapter 7, Input and Output Functions. Join me in Lecture 07-01, Introduction. Welcome to Chapter 7, Input and Output Functions. Up until now, our programs have used hard-coded data. However, real-world applications need to interact with users or external systems. Input and output functions are the way our program communicates with the outside world. 1. What is output? Output is the data generated by the program that is delivered to the user or an external destination, such as a monitor, printer, or file. In Python, the most fundamental output function is the print function. 2. What is input? Input is the data received by the program from the user or an external source, typically through a keyboard, a mouse, or a file. The primary function for receiving keyboard input in Python is the input function. 3. The standard I/O streams. These I/O functions rely on 3 standard streams inherited from the operating system: standard input, typically the keyboard; standard output, typically the screen or console; and standard error, which is used for error messages and is also typically displayed on the screen. Understanding these 2 core mechanisms, input and output, is vital for building interactive programs. In the next few lectures, we will look at each function. First, we will go to output. Join me in Lecture 07-02, Print. Welcome back. The print function is the most common way to generate output in Python. It takes 0 or more expressions, converts them to text, and writes them to a stream, usually the console. 1. Printing multiple objects. You can pass multiple objects separated by commas to the print function. By default, it automatically separates these objects with a single space. 2. The sep parameter. The optional sep parameter stands for separator. It allows you to specify a custom string that will be inserted between the objects being printed instead of the default space. 3. The end parameter. By default, the print function adds a new line character, \n, at the end of the output. The end parameter allows you to replace this new line with any other string, which is useful for printing things on a single line. Notice how loading and complete appear on the same line because we set end to an empty string in the first print call. To summarize, the print function is highly flexible. Master the sep and end parameters to control the formatting of your output precisely. Controlling the output text may be done alongside string formatting. Our next lecture 0703. Print and string formatting. Welcome back. When using the print function, you may need to embed the values of variables directly into a descriptive string. This is where string formatting comes in. While Python has several methods, we will focus on the modern and highly recommended approach, f-strings. 1. The f-string method. Introduced in Python 3.6, f-strings, or formatted string literals, are prefixed with the letter f. They allow you to place variable names or even full expressions directly inside curly braces within the string. 2. Formatting data types. F-strings also allow fine-grained control over how variables are displayed, especially useful for numbers. You use a colon followed by a format specifier inside the curly braces. To control the number of decimal places for a float, use a period followed by the desired precision, and then the letter F. You can easily format numbers as percentages by multiplying by 100 and using the %sign format specifier. To summarize, you may use f-strings for clear, readable, and efficient string formatting in modern Python. They simplify embedding variables and allow precise control over data representation. We have learned generating output. Now, let us turn to input. Our next lecture 0704. Input. Welcome back. While the print function sends information out, the input function is responsible for bringing data into the program. It pauses the program execution, waits for the user to type something and press enter, and then returns the data. 1. Basic input and prompt. The input function takes one optional argument, the prompt string. This string is displayed to the user before the program pauses, telling the user what to enter. 2. Crucial concept, string return type. This is a single important rule. The input function always returns data as a string, regardless of what the user types. If the user types a number, it is still stored as a string. 3. Typecasting. If you intend to use the input for arithmetic operations, you must explicitly convert the returned string to a numeric type, like an integer or float, using typecasting functions. To summarize, the input function is our connection to the user, but remember its output is strictly a string. Always apply typecasting if you need to treat the user's input as a number. We have learned how to take a single input. Our next lecture, 0705. Reading multiple inputs. Welcome back. While reading one input at a time is simple, it is often inefficient if you need many variables. This lecture shows you standard Python techniques for reading multiple values, separated by spaces or commas, from a single line of user input. 1. Using input and split. The core technique involves two steps. First, use the input function to read the entire line as a single string. Second, use the string's split method. By default, split breaks the string into a list of substrings wherever it finds white space. We can then assign these list elements directly to multiple variables in one line. 2. Converting types using map. Since split returns strings, we still need type conversion for numbers. Using a separate conversion line for each variable is repetitive. Instead, we use the map function, which applies a function like int to every item in the list returned by split. This single line is a way to read multiple numbers from one line of input. To summarize, combining input, split, and map is the most effective method for handling multiple inputs simultaneously, especially when those inputs need to be converted to numerical types. We now have the tools for input and output. Our next lecture, 0706. Grocery Checkout System. Welcome to our final use case for the input and output section, building a simple grocery checkout system. We will use the input function to receive data, typecasting and arithmetic operators for calculation, and print, with f-strings for clear output. 1. Define prices and get input. We start by setting fixed prices for two items. Then, we use the efficient map function to read two quantities from the user on a single line, converting them immediately to integers. 2. Perform calculations. We calculate the subtotal using multiplication and addition. We also define a tax rate and apply it to find the final total cost using multiplication. 3. Handle payment and change. We ask the user how much money they are paying, ensuring we convert the input to a float, and then use subtraction to calculate the change. To summarize, this simple system demonstrates the synergy between reading user input, performing calculations with operators, and presenting clear results using f-string formatting. This is the foundation of almost every practical program. Congratulations! This concludes our chapter on input and output. We now begin Section 8, More Programs 1. Our next lecture 0801. Read and display student details. Welcome to Section 8, More Programs 1. This section focuses on applying the fundamental concepts we have learned, including variables, data types, operators, and I/O functions, through practical exercises. Our first task is to read and display student details. 1. Receiving student input. We will ask the user for the student's name, age, and GPA separately. Remember the rule: input always returns a string. We must use typecasting for age, which is an integer, and GPA, which is a floating point number. If you forget the float casting for the GPA, it would prevent later operations or accurate display. 2. Displaying formatted output. We now use f-strings to present the stored information clearly. We will also apply formatting to the GPA to ensure it only shows 2 decimal places, an example requirement for academic scores. To summarize, this program applies typecasting when reading numerical input and demonstrates how to use f-strings for clear, controlled output, like setting decimal precision for the GPA. Our next lecture, 0802. Average of 3 numbers. Welcome back to our application section. Our next exercise is calculating the average of 3 numbers provided by the user. This task is for demonstrating the input reading technique combined with basic arithmetic operators. 1. Reading multiple numerical inputs. We will use a way to handle multiple numerical inputs on a single line, the combination of input, split, and map. We map the input directly to the float type to ensure accuracy, regardless of whether the user enters integers or decimals. 2. Calculating the average. The average is the sum of the numbers divided by the count of the numbers. It is crucial to use parentheses to ensure the addition is completed before the division, respecting the operator precedence rules. 3. Displaying formatted results. Since the division may result in a long float, we will use f-string formatting to display the average rounded to 2 decimal places for better readability. To summarize, this exercise applies reading multi-number input, using parentheses for correct operator precedence, and employing float formatting for clean output. Our next lecture, 0803. Area of a circle. Welcome back. Our third program in this section is calculating the area of a circle. The area formula is pi times radius squared. This exercise introduces the concept of importing external modules to access high-precision constants like pi. 1. Importing the math module. Before we can use the value of pi, we must import Python's built-in math module using the import keyword. Once imported, we can access the constant pi using the syntax math.py. 2. Getting input and calculation. We ask the user for the radius and immediately cast it to a float. Then, we apply the area formula using multiplication and the exponentiation operator. 3. Displaying formatted area. The area is likely a long decimal number. We use an f-string to display the final result, rounding it to 4 decimal places, which is standard practice for scientific calculations. To summarize, this exercise combines I/O and arithmetic with a critical new skill of using the import statement to access Python's vast library of built-in functions and constants. We just got a taste of the math module. Our next lecture, 0804. Using the math module. Welcome back. In our last lecture, we briefly introduced the math module for accessing Pi. Now, we will explore some of the powerful mathematical functions provided by this module, which may be used for engineering, scientific, and financial calculations. 1. Square root. The math sqrt function calculates the square root of a non-negative number. It always returns a float. 2. Power. While you can use the double asterisk operator for exponentiation, the math.pow function is also available. It takes 2 arguments, the base and the exponent, and also returns a float. 3. Rounding functions. The math module provides explicit ways to round numbers up or down. Math.floor returns the largest integer less than or equal to x. Math.ceil returns the smallest integer greater than or equal to x. To summarize, always remember to import the math module before using its functions. These tools provide precise and reliable methods for handling complex mathematical requirements. This concludes our section on programs. We now move to Chapter 9, Flow Control Statements, where we will learn how to make our programs smart enough to make decisions and repeat tasks. Join me in Lecture 09-01. Introduction. Welcome to Section 9, Flow Control Statements. Up until now, our programs have executed sequentially, meaning one line after the other. Flow control statements give your program the power to make decisions and repeat actions, moving beyond simple, linear execution. This is what makes programs flexible. 1. Sequential flow. This is the default mode. Instructions are executed in the exact order they appear, from top to bottom. Every program we have written so far has followed sequential flow. 2. Conditional flow. This allows the program to execute a specific block of code only if a certain condition is true. It is the program's way of asking a question, like, if the user is logged in, then show the profile page. This is handled by if, elif, and else statements. 3. Iterative flow. This allows the program to repeat a block of code multiple times. This is perfect for tasks like processing every item in a list or running a process until a condition is met. This may be handled by for and while loops. To summarize, understanding these 3 types of flow control, sequential, conditional, and iterative, is important. We will now learn the first type of flow control, conditionals. Our next lecture 09-02. If-else syntax. See you there. Welcome back. We begin our exploration of conditional flow with a fundamental if statement, which allows a program to decide whether or not to execute a block of code. We then introduce the else statement, which provides an alternative path if the if condition is false. 1. The if statement. The if keyword is followed by a condition, which must be a Boolean expression that evaluates to true or false. The line ends with a colon, and the code to be executed must be indented. 2. Indentation is crucial. Unlike many other languages that use curly braces, Python relies entirely on indentation, typically 4 spaces, to define a block of code. All lines belonging to the if block should be indented by the same amount. 3. The else statement. The optional else block provides a guaranteed path of execution if the if condition turns out to be false. Only one block, either if or else, will ever execute. To summarize, the if-else structure allows for binary decisions. You may use comparison operators for the condition, and remember that indentation is not optional. It is fundamental Python syntax. Now that we know the syntax, our next lecture 0903. Find even or odd number. Welcome back. In this exercise, we combine our knowledge of the modulus operator and the if-else statement to solve a classic programming problem, determining if a number is even or odd. This is a fundamental application of conditional logic. 1. Reading and preparing input. We first ask the user for a number. Since we need to perform arithmetic, we immediately cast the input string to an integer using the int function. 2. The modulus condition. A number is even if it is perfectly divisible by 2, meaning the remainder is 0. We use the modulus operator, the %sign, to find the remainder. Our condition will check if the number modulus 2 equals 0. 3. Applying if-else logic. We use an if-else block. If the condition number modulus 2 equals 0 is true, we print that the number is even. Otherwise, the else block executes, telling us the number is odd. To summarize, the modulus operator may be applied for checking divisibility. This exercise shows how a simple Boolean result from a comparison is used to branch the program flow, making a fundamental decision. We have seen binary decisions with if-else. What if we have more than 2 possibilities? Our next lecture 0904. If-else ladder. Welcome back. While the basic if-else statement handles binary decisions, real-world logic often involves multiple possible outcomes, such as assigning a letter grade based on a score. The if-else ladder, or multi-way branching, may handle these scenarios. 1. The elif keyword. The elif statement is short for else if. It allows you to check a new condition only if the previous if or elif conditions were false. You can have any number of elif statements between the initial if and the final, optional else. 2. Flow and exclusivity. The conditions in the ladder are checked strictly from top to bottom. As soon as a condition is found to be true, its corresponding block is executed, and the entire rest of the ladder is skipped. Only one block will ever execute. Because the first condition was true, the program immediately exits the entire conditional structure, ignoring the later, technically true, elif condition. 3. The final else. The else clause, placed at the end, is optional but highly recommended. It acts as the final catch-all, executing only if all previous if and elif conditions failed to be true. To summarize, the if-elif-else ladder may be for sequential decision-making. Order matters, as the program only executes the first true condition it encounters and then skips the rest. Now that we know how to handle multiple conditions, our next lecture 0905, Handle 0. Welcome back. Good programming practice requires anticipating errors. One of many errors is the division by zero error. In this lecture, we will use the if-else statement to perform basic input validation, ensuring our program doesn't crash if the user enters 0 as a divisor. 1. Reading inputs. We need two numbers, a numerator and a denominator. Both are read as strings and immediately converted to floats to allow for decimal division. 2. The conditional check. We place the division logic inside an if statement. The condition checks if the denominator is not equal to 0. If this condition is true, we can safely proceed with the calculation. 3. Handling the error case. If the denominator is equal to 0, the if condition is false and the else block executes. Instead of crashing, the program gracefully prints a warning message to the user, explaining the problem. This simple structure protects your program from a runtime crash. To summarize, you should validate input where potential errors exist, especially for division. You may use an if-else structure to specifically check for and handle the invalid case. We have now learned conditional flow. Next, we move to the second type of flow control, iterative flow. Our next lecture 0906, while syntax. Welcome back. We are now going to iterative flow, which allows us to repeat code. The first structure is the while loop. It executes a block of code repeatedly as long as a specified condition remains true. 1. The syntax and flow. The while keyword is followed by a Boolean condition and a colon. The code block below it is indented. The program checks the condition. If true, it executes the block. It then returns to the top and checks the condition again. This loop continues until the condition evaluates to false. Two, controlling the loop. While loop may require a mechanism inside the loop body to eventually make the condition false. We call this the update statement. In our example, the line incrementing count ensures the condition count less than 3 eventually fails. 3. Infinite loops. If you forget or accidentally omit the update statement, the condition may never become false. This creates an infinite loop, causing your program to run forever, or until the system stops it. For example, if we removed the line count equals count plus 1, the program would constantly print loop iteration 0. To summarize, the while loop is excellent for repeating actions when you do not know the exact number of iterations beforehand, such as continually asking the user for input until they enter a valid response. Our next lecture 0906 07. Display numbers from 1 to 20. Welcome back. Let's put the while loop syntax into immediate practice. Our goal is to print all numbers starting from 1 up to and including 20. This exercise clearly demonstrates the three parts of a while loop: initialization, the condition, and the update. 1. Initialization. We need a counter variable to track our current number. Since we start at 1, we initialize the variable count to 1 before the loop begins. 2. The loop condition. We want to include 20. Therefore, the loop must continue while the current value of count is less than or equal to 20. If we used only less than 20, the loop would stop at 19. 3. The loop body and update. Inside the loop, we first print the current value of count. Immediately after, we use the increment update statement, count equals count plus 1, to prepare for the next iteration. Forgetting this line leads to an infinite loop, repeating the number 1 forever. To summarize, iterative programs should be careful definition of the start, end, and step size. This pattern is foundational for many sequence generations using the while loop. Our next lecture 0908. Odd numbers between given numbers. See you there. Welcome back. This exercise will apply something we've learned related to flow control. Our goal is to ask the user for a starting number and an ending number, and then print only the odd numbers within that range. This requires both the while loop for iteration and the if statement for decision-making. 1. Reading and initializing inputs. We read the start and end numbers from the user. Since the end number defines our loop condition and the start number acts as our initial counter, we assign the start input to our control variable, which we will call current_number. Two. Combining while and if. The while loop runs as long as current_number is less than or equal to the end value. Inside the loop, the if statement checks for the odd condition, if the number modulus 2 is not equal to 0. Three. Analyzing the flow. Notice the indentation. The if statement and the increment line are both inside the while loop. However, the print statement is only inside the if block. This ensures that the number is increment every time, but only printed when the odd condition is met. To summarize, combining loops and conditions is a programming pattern that you may use regularly in the future. The while loop controls the repetition, and the if statement controls which data points are selected or acted upon during that repetition. We have seen the while loop. Next, we explore the for loop, which is often easier to use when iterating over a known sequence. Join me in lectures 0909 for syntax. Welcome back. While the while loop is great for repeating actions based on a condition, the for loop is the preferred method in Python for iterating over a sequence of items, such as a list of names or a defined range of numbers. For predetermined ranges, it is simpler than while. 1. The basic for loop structure. The for loop automatically manages the counter and termination. You simply tell it to execute the code block for every item in a sequence. Python handles the rest. 2. Iterating with range. Maybe you need to loop a specific number of times. Instead of manually creating a list of numbers, Python provides the built-in range function. This function generates a sequence of numbers, which the for loop iterates over. Three, the step parameter. The third, optional argument in the range function is the step size, which determines the increment or decrement between numbers. This allows you to count by twos, or even count backwards. To summarize, the for loop simplifies iteration over sequences. The range function, it lets you easily define the start, end, and step for numerical loops. Our next lecture 09-10. Using for loop. See you there. Welcome back. In this short practical exercise, we will immediately apply the syntax of the for loop and the range function we just learned. The goal is to generate simple number sequences, demonstrating how easily the for loop handles a fixed number of iterations. 1. Simple range. When you provide only one argument to range, it is treated as the stop value. The loop starts by default at 0 and goes up to, but does not include, the stop value. We will print the numbers 0, 1, 2. 2. Custom start and end. Here, we specify both the starting point and the stopping point. We want to print numbers from 5 to 8, so our range function must stop at 9 to include 8. 3. Using the step parameter. We can use the third argument to define a step size. Let's print the odd numbers from 1 to 10 by setting the step to 2. 4. Counting backwards. The step can also be negative. To count down from 5 to 1, we set the start to 5, the stop to 0 to include 1, and the step to -1. To summarize, the for loop combined with the flexible range function is a readable way to iterate a fixed number of times in Python. Now that we can loop through numbers, let's use the for loop to process data collections. Our next lecture 09.11. Product of numbers in a list. Welcome back. You can apply loops to process collections of data, such as lists. Our goal in this exercise is to find the product, or the result of multiplying all numbers stored in a list. This requires setting up an accumulator variable and iterating through the list using a for loop. 1. Initialization and accumulator. We start with our list of numbers. Crucially, we must initialize a variable called the accumulator to hold our running product. Unlike calculating a sum where the accumulator starts at 0 for a product, the accumulator must start at 1 so that the first multiplication yields the correct result. 2. Iterating and updating. We use the for loop to iterate directly over the list. In each iteration, the loop variable, which we call number, takes the value of the next list element. Inside the loop, we multiply the current value of product by number and store the result back into product. Three. Final output. After the loop completes all iterations, the product variable holds the final result, which we display using an f string. To summarize, for this pattern, you need to correctly initialize the product accumulator to 1. The for loop then systematically updates this accumulator with the result of multiplying the current value by the next list item. Our next lecture 09.12. Multiplication table of a given number. See you there. Welcome back. This lecture is related to generating a multiplication table. Our goal is to ask the user for a number and then print that number multiplied by every integer from 1 up to 10. This requires combining user input, the for loop, and f-string formatting. 1. Receiving input and initialization. We need to get the number from the user for which we are generating the table. We immediately cast this input to an integer. A multiplication table may run from 1 to 10. In this lecture, we will use the range function. 2. The for loop structure. To loop from 1 to 10, we use range 1, 11. The loop variable, which we call I, will take the values 1, 2, 3, and so on up to 10. 3. Calculation and formatting output. Inside the loop, we calculate the result of the multiplication, n times I. We use an f-string to display the entire equation clearly, showing the original number, the multiplier, and the result. To summarize, this exercise applies simple arithmetic inside a structure for loop, combined with careful range definition, can quickly generate detailed, repetitive output, like a multiplication table. We have now learned standard looping. Our next lecture 09.13. Break. See you there. Welcome back. Sometimes, we need to stop a loop prematurely, even if its main condition is still true. The break statement is used to achieve this. It gives you an immediate exit from the innermost containing loop. 1. Break syntax and flow. The break statement may be used inside an if statement within a loop. When Python encounters break, it skips the rest of the loop's current iteration, ignores the loop's main condition, and moves execution to the first line of code immediately following the loop. 2. Practical use case, searching. You may apply break to search for a specific item in a large collection. Once the item is found, there is no need to continue looping through the remaining data, so we break to save time and resources. 3. Comparison with loop condition. If the loop was defined as for I in range 1 to 10, it would normally run 9 times. However, because of the break at I equals 5, the loop only runs 5 times. The break takes precedence over the loop's inherent termination condition. To summarize, the break statement is a powerful tool for efficiency and handling conditions that require immediate termination of a repetitive task. While break stops the loop entirely, sometimes we only want to skip the current item and move to the next. Our next lecture 09.14. Continue. Welcome back. While the break statement immediately terminates a loop, the continue statement serves a different purpose. It skips only the remaining instructions in the current iteration of the loop and immediately proceeds to the next iteration. You may apply it to skip certain data points. 1. Continue syntax and flow. Similar to break, continue is typically placed inside an if statement within a loop. When Python executes continue, it ignores any code that follows it inside the loop body for that specific iteration, and then immediately goes back to check the loop's condition and start the next iteration. 2. Practical use case. Data filtering. You may apply continue to filter out invalid or unwanted inputs. In this example, we only want to process positive numbers and skip 0 and negative numbers. Three, continue versus break. Remember the key difference. Break stops the loop entirely, executing the code after the loop. Continue only stops the current step and forces the loop to proceed to the next element or iteration. To summarize, you may use continue when you want to bypass the main logic for a particular item but need the loop to keep processing the remaining items in the sequence. Our next lecture 09.15. Assert. See you there. Welcome back. The assert statement. It is a debugging aid used to test assumptions about the state of your program. If the assumption is false, Python immediately halts execution and raises an assertion error. 1. Assert syntax. The assert statement takes at least one argument, a condition that must be true. Optionally, it can take a second argument, which is a message string displayed if the condition is false. 2. Handling a failed assertion. If the condition is false, the assertion fails. The program stops, and Python raises an assertion error. This is intentional. It signals that something unexpected and critical happened, requiring developer attention. Three, assert versus if. A if statement may be used for checking expected conditions and handling them gracefully, for example, printing an error message to a user. Assert is strictly for developer use. It validates internal assumptions and should never be used for user input validation because it is designed to crash the program when something is fundamentally wrong. To summarize, use assert to confirm conditions that your code must have to function correctly. It acts as a safety net during development and testing. We have learned the fundamental flow control statements. Our next lecture 09.16. More programs, remove duplicates in list. See you there. Welcome back. We are now moving into programs that combine something we've learned. Our first problem is removing duplicate elements from a list. We will achieve this using a for loop and conditional logic without relying on advanced data structures like sets. 1. Setup and initialization. We start with a list containing duplicate numbers. We must create an empty list, which we'll call unique_list, to store the elements that pass our uniqueness check. This empty list is the key to tracking items we have already processed. 2. Iteration and condition. We use a for loop to check every element in the original data_list. Inside the loop, the if statement performs the check. Is the current number not in the unique_list already? The not in operator is perfect for this type of membership check. 3. Result display and analysis. The final unique list is now ready. The crucial logic here is that the unique underscore list grows with unique items, and the not in check uses this growing list as a historical record to decide whether to admit the current number. To summarize, removing duplicates by manually checking for membership in a secondary list is a classic looping pattern. It is a demonstration of using a loop to get a filtered collection of data. Our next lecture 0917. More programs, count vowels in a word. See you there. Welcome back. In this exercise, we will apply flow control to text processing. Our goal is to write a program that accepts a word from the user and counts how many vowels it contains. This involves iterating over a string and using membership operators. 1. Initialization. First, we define the word we want to analyze. Then, we define a string containing all possible vowels, both lowercase and uppercase, to act as our reference. Finally, we initialize a counter variable to 0. 2. Iteration and checking. We loop through every character in the word. Inside the loop, we check if the current character exists within our vowels reference string using the in operator. If it does, we increment our counter. 3. Displaying the result. Once the loop finishes checking every character, the count variable holds the total number of vowels found. To summarize, this pattern of iterating, checking membership, and incrementing a counter is an approach for analyzing the content of strings in Python. Our next lecture 0918. More programs, handle employee details. See you there. Welcome to our final program for the flow control section. We will combine loops, user input, and lists to create a basic system for collecting and displaying details for multiple employees. 1. Setup and control loop. We create a master list, employee underscore data, to hold all records. We use a while true loop to repeatedly ask for input, providing an option for the user to break the loop when data entry is complete. 2. Collecting data. If the loop continues, we prompt the user for the employee's name and salary. We convert the salary to an integer, then package this data into a new list structure, representing a single employee record. 3. Displaying collected data. After the while loop breaks, we use a separate for loop to iterate through the main employee underscore data list. For each record, we neatly print the collected name and salary. To summarize, this program uses a while loop for unknown iteration counts, like repeated input, and then uses a for loop to process the structured data collected in a list. This concludes our section on flow control statements. Our next section is 10 more programs 2, starting with lecture 10.01. Reverse a string. Welcome to Section 10. More programs too. We start with a string manipulation technique, reversing a string. 1. Reviewing string slicing. Recall that string slicing uses the format square bracket start colon and colon step square bracket. We use the first two arguments to extract substrings. The third argument, step, controls the direction and size of the jump. 2. Reversing with step -1. To reverse an entire string, we use the special slicing syntax, ::-1. The first two arguments, start and end, are omitted, which defaults them to the beginning and the end of the string, respectively. By setting the step to -1, Python iterates through the string backwards. 3. The traditional approach. For comparison, achieving the same result using a traditional for loop is much more verbose. It requires initializing an empty string and concatenating characters from the original string in reverse order. While functional, it is less readable than slicing. To summarize, string slicing with the step of -1 is a practice for reversing strings in Python. It's concise, readable, and faster than manually writing a loop. Our next lecture 10.02. Reverse using split and join. See you there. Welcome back. In the previous lecture, we used string slicing to reverse the characters of a string. Here, we explore another method that uses three core tools: the string method split, the list slicing technique, and the string method join. This method may be used when the string is composed of separate words. 1. Splitting the string. First, we need to convert the string into a list of individual characters. We do this by calling the list constructor directly on the string. This breaks the string into its constituent characters, each becoming a separate element in a new list. 2. Reversing the list. Once we have the characters in a list, we can use the same slicing technique we learned previously, the ::-1, to reverse the order of the items in the list. 3. Joining the characters. The final step is to convert the list of reverse characters back into a single string. We use the join method, specifying an empty string as the delimiter. The empty delimiter ensures no spaces or other characters are inserted between the rejoined letters. To summarize, the split reverse join pattern is slightly more complex than direct slicing, but it provides a flexible framework that is crucial when you need to perform other list operations, like sorting or filtering, before putting the string back together. Now that we can reverse characters, let's look at reversing the order of words in a sentence, not the characters themselves. Join me in Lecture 10.03. Reverse the words in a string. Welcome back. We've learned how to reverse characters. Now, let's reverse the order of words in a sentence. This is a crucial distinction. We want the first word to become the last, and the last word to become the first. This is a job for the string split, list slicing, and string join methods. 1. Splitting the sentence into words. We start with a sentence. To treat words as individual elements, we use the string's split method. When called without arguments, split automatically uses spaces as delimiters and returns a list of words. 2. Reversing the word list. Once the sentence is a list of words, we can use the quick and clean slicing technique, ::-1, to reverse the order of those words in the list. 3. Joining the words back. The last step is combining the words back into a single string. This time, we must use a space character as the delimiter inside the join method to ensure that the words in the resulting sentence are separated correctly. To summarize, the key takeaway is recognizing that the split method converts a sentence into a list of words, allowing us to use list tools like slicing to reorder the words before finally reassembling the sentence with join. Our next lecture 10.04. Reverse the characters in the words. See you there. Welcome back. This program is in test of your string and list manipulation skills. Our goal is to take a sentence, reverse the characters within each word, just like we did with slicing, but keep the original order of the words in the sentence. This requires a 3-step process: split, process with a loop, and join. 1. Split and setup. We start by defining our sentence. The first step is to use the split method to break the sentence into a list of individual words. We also initialize an empty list processed_words to store our reversed words. 2. The loop and slicing. We iterate through the list of words using a for loop. Inside the loop, for each individual word, we apply the slicing technique, ::1, to reverse its characters. This reversed word is then appended to our processed_words list. 3. Reassembling the sentence. Finally, we use the join method with a space delimiter to turn the list of reversed words back into a complete sentence. The resulting string has the word order preserved, but the internal characters of each word are backwards. To summarize, the pattern of separating, processing elements individually, and then reassembling is fundamental to many complex data manipulation tasks. Our next lecture 10.05. Remove duplicate chars. See you there. Welcome back. Our next program focuses on data cleanup within strings, removing duplicate characters. This is an exercise that reinforces our understanding of iteration and the in-membership operator. We will iterate through a string and build a new result string, only adding characters that haven't been seen before. 1. Initialization and setup. We start with our input string, which contains repeated characters. The core of this solution is the empty string, unique_chars, which will serve as both our result and our historical record of characters already added. 2. Iteration and conditional check. We use a for loop to process every character in the input string. Inside the loop, we use the conditional if character not in unique characters. If this condition is true, it means we have encountered this character for the first time, and we should append it to our result string. 3. The alternative sets. While the manual loop is great for practice, there's a way to remove duplicates is by converting the string to a set. Sets automatically store only unique elements. We then join the unique elements back into a string, though this method does not preserve the original order. To summarize, the manual looping method is crucial for preserving the order of first appearance. It is a fundamental pattern for building a filtered collection by checking against the collection itself. Our next lecture 10.06. Count the characters. See you there. Welcome back. Our next program is focused on frequency analysis, counting how many times each character appears in a given string. This task is suited for using a dictionary, where each unique character will be a key, and its count will be the value. 1. Initialization with the dictionary. We start with our input string. There's a way to track counts, which is by initializing an empty dictionary. This dictionary, char_counts, will map characters to their numerical frequencies. 2. Iteration and counting logic. We loop through every character in the input string. For each character, we use the dictionary's get method. About this method, it safely retrieves the current count, and if the character is not found, it conveniently returns 0. We then add 1 to this value and update the dictionary. 3. Result and analysis. After the loop completes, the dictionary contains the final frequency of every character. Notice how the dictionary automatically handles case sensitivity. For example, a lowercase s is treated separately from an uppercase s unless you convert the entire string to one case first. To summarize, character counting is a skill for text analysis, and the dictionary get method is a readable way to implement this frequency counting logic in Python. Our next lecture 10.07. Print right-angled triangle. See you there. Welcome back. This program is to print a right-angled triangle pattern made of asterisks. 1. Understanding nested loops for patterns. Pattern printing requires 2 loops. The outer loop controls the number of rows, or the height of the pattern. The inner loop controls the number of elements, or the width, printed in each specific row. 2. The right-angled logic. For a right-angled triangle, the number of asterisks printed in any row must equal the current row number plus 1. Since the outer loop variable I goes from 0 to 4, the inner loop needs to run from 0 up to, but not including I plus 1. 3. Analyzing the output. When I is 0, the inner loop runs once. When I is 1, the inner loop runs twice. This continuous growth ensures the staircase shape of the right-angled triangle is formed. Notice the use of the end argument in the inner print statement to prevent a new line until the row is finished. To summarize, the fundamental principle of pattern printing is that the inner loop's range is dynamically dependent on the current iteration of the outer loop. For a right-angled triangle, the inner loop runs I plus 1 times. Our next lecture 10.08. Print pyramid pattern. See you there. Welcome back. Building on the right-angled triangle, we now face the challenge of creating a symmetric pyramid pattern. This is more work because it requires 3 distinct steps inside our outer loop: printing leading spaces for alignment, printing the pattern elements, and then moving to the next line. 1. Outer loop and space calculation. As always, the outer loop controls the rows. For a pyramid, the number of leading spaces needed decreases with each row. If the total height is 5, the first row needs 4 spaces. The number of spaces is always equal to the total height minus the current row index, -1. 2. Printing the elements. The number of asterisks increases in each row. The number of elements in a symmetric pyramid follows the pattern: 1, 3, 5, 7, and so on. This is equivalent to 2 times the row index I plus 1. We use a second inner loop to print the correct number of elements. 3. Analyzing the flow. When I is 0, we print 4 spaces and 1 asterisk. When I is 1, we print 3 spaces and 3 asterisks. This continuous adjustment between spaces and elements is what creates the perfect centered pyramid shape. To summarize, the pyramid pattern is solved by decoupling the printing process into loops dedicated purely to spaces for alignment and loops dedicated purely to the pattern elements. We created a pyramid. Our next lecture 10.09. Find substrings in a given string. See you there. Welcome back. This is our final program for this section, and this problem is about finding every possible contiguous substring within a given string. This requires us to use nested loops to control both the starting and ending positions of the slice. 1. Setup and outer loop. We start with our input string. The outer loop, using variable I, iterates from the start index 0 up to the end of the string. This loop defines the starting index for every potential substring. 2. Inner loop and slicing. The inner loop, using variable j, defines the ending index. This loop must start one position after I and continue to the length of the string plus 1. Why plus 1? Because string slicing is exclusive of the end index, and we want to include the last character. We then use string slicing to extract the substring. 3. Trace and output. Let us trace the first iteration. When I is 0, the inner loop j runs for 1, 2, and 3. This yields the substrings UB and ABC. When I is 1, the inner loop j runs for 2 and 3, yielding B and BC, and so on. To summarize, finding substrings is all about defining the correct start and end indices dynamically using nested loops and then leveraging Python's string slicing. Congratulations on completing section 10. Okay, we are going to next section 11. Command line arguments. The first lecture is 11.01. Introduction. See you there. Welcome to section 11, Command Line Arguments. So far, our Python programs have relied only on the input function to get data. However, real-world scripts may need to receive initial configuration or data directly when the program starts, without having to wait for the user to type something. 1. What is the command line? The command line, or terminal, is a text-based interface used to execute programs and manage files. When you run a Python script from the command line, you type Python 3 followed by the file name. 2. Defining arguments. Command line arguments are simply the additional pieces of information you pass to your program after the file name. They allow external systems or users to instantly configure the script. For example, here we are passing the words hello and world as arguments. 3. The sys module. In Python, these command line arguments are accessed using the built-in sys module. Specifically, we use sys.argv, which stands for argument vector. The sys.argv variable is a list that contains all the command line tokens. To summarize, you may use command line arguments to make Python scripts more flexible. The key tool for accessing them is the sys.argv list. Our next lecture 11.02. Command line arguments. See you there. Welcome back. In this lecture, we will demonstrate how to read and interpret the command line arguments using the sys.argv list. Understanding the structure of this list is the first critical step in processing external data. 1. The structure of sys.argv. When a Python script is executed with arguments, the sys.argv variable is populated as a standard Python list of strings. The key point is that the element at index 0 is always the name of the script itself, and the actual user-provided arguments start from index 1. 2. Accessing arguments and length. Since sys.argv is a list, we can use standard list operations on it. We can get the total count of arguments, including the script name, using the len function. We can also access any individual argument using its index, like accessing sys.argv at index 1 for the first user argument. Three. Iterating through arguments. To process all the actual user arguments, we use a for loop that specifically slices the list, starting from index 1 up to the end. This ensures we skip the script name and only deal with the passed-in data. To summarize, think of sys.argv as a list of strings where the script name is always the first item. Remember to check the length of the list before trying to access any arguments to prevent an index error. Our next lecture 11.03. Command line arguments in VS Code. See you there. Welcome back. While running command line arguments from the terminal is straightforward, developers often use an integrated development environment like VS Code for convenience and debugging. Running scripts within VS Code's debugger requires a special configuration to pass those arguments. 1. Creating launched.json. To control how VS Code runs your script, you need a configuration file named launch.json. To generate this file, you may follow my following steps. 2. Adding the args parameter. Inside the launch.json file, locate the configuration block for running Python. To pass arguments, you must add an array property named args. This array holds the arguments exactly as they would appear after the script name in the terminal. Remember, the program file name is automatically handled by the system and does not need to be included in the args list. 3. Execution and sys.argv. When you run your script using the VS Code debugger with this configuration, sys.argv at index 1 will be argument 1, sys.argv at index 2 will be 100, and so on. This effectively bypasses the need to type arguments every time in the terminal, especially when debugging. To summarize, the launched.json file provides a repeatable way to inject command line arguments into your Python script. Our next lecture 11.04. Product of command line arguments. See you there. Welcome to our final program for the command line arguments section. We will now write a utility script that accepts an unknown number of integers as command line arguments and calculates their product. This combines something we've learned about sys.argv, iteration, and data type conversion. 1. Initialization and data access. We must first import the sys module. We initialize a variable product to 1, as multiplying by 0 would always result in 0. Next, we check if any arguments were provided, as our script must have input to work. Two, iteration and type conversion. This is the crucial step. We loop over the sys.argv list, starting from index 1. Remember, all command line arguments are received as strings. We must convert each argument to an integer using the int function before we can perform multiplication. Three, final result. After the loop completes, the product variable holds the result of multiplying all the input numbers. We print the final value to the console. To summarize, this program is an example about command line processing. You access arguments via sys.argv, loop over the data starting at index 1, and always remember to convert the arguments from strings to the required numeric type. This concludes our section on command line arguments. Our next section 12. Functions. Our next lecture 12.01. Introduction. See you there. Welcome to Section 12. Functions. This is the important tool in clean code programming. Functions allow us to organize large blocks of code, make our programs easier to read, and reuse code. 1. What is a function? Simply put, a function is a named, organized block of code designed to perform a specific task. Think of it as a small, specialized machine. You give it input, it does its job, and sometimes it gives back a result. 2. The DRY principle. The main advantage of functions is adhering to the DRY principle. Don't repeat yourself. If you have the same 3 lines of code performing a calculation in 10 different places in your script, you should encapsulate those 3 lines into a single function. This makes your code smaller and much easier to maintain. 3. Benefits of functions. Beyond reuse, functions improve code readability by organizing the logic into descriptive names. They also provide modularity, meaning you can easily update the logic inside one function without affecting the rest of the program, provided the inputs and outputs remain the same. To summarize, think of functions as the building blocks of any complex program. They are essential for turning a long, messy script into a clean, well-structured, and professional application. Our next lecture 12.02. First function. See you there. Welcome back. Having grasped the importance of functions, let's now look at the essential Python syntax for defining and running one. There are two main parts: the definition, which tells Python what the function does, and the call, which executes the function's code. 1. Defining the function. All function definitions in Python start with the keyword def, followed by the function's name, a pair of parentheses, and finally, a colon. The code block within the function is indented. The parentheses hold the parameters, which are the inputs the function expects. Here, we define a simple function that expects a name parameter. Two, calling the function. Defining a function does not execute it. To run the code inside the function, you must call it by using its name followed by parentheses. The values you pass during the call, such as the string Alice here, are known as arguments. These arguments are mapped to the parameters defined in the function signature. Three, functions without parameters. A function does not necessarily need input. You can define a function with empty parentheses if it performs a standalone task, such as simply displaying a fixed message or reading a configuration file. To summarize, the function definition using the def keyword sets up the logic, and the function call executes that logic. The parameters act as placeholders for the data, or arguments, that the function needs to perform its task. Our next lecture 12.03. Returning a result. See you there. Welcome back. In the previous lecture, our function only printed its result, but it did not provide the result back to the main program. For a function to be useful in calculations, it must use the return statement. The return statement is how a function sends a value back to the place where it was called. 1. Using the return statement. To return a result, we use the return keyword followed by the value or variable we want to pass back. Once the return statement is executed, the function immediately stops executing, and the value is sent back to the caller. Two, capturing and reusing the result. When calling a function that returns a value, you must assign the function call to a variable. This variable captures the return value. Once captured, the result can be used in further computations, which is the primary reason for using functions for calculation. Three, the default return value. What happens if a function finishes without encountering a return statement? In Python, all functions implicitly return the special value, none. If you call a function that only prints and assign it to a variable, that variable will hold none. To summarize, use return to make your functions true computational tools. Always capture the function call in a variable to make use of the return data. We know how to return one result. Our next lecture 12.04. Return multiple values. See you there. Welcome back. While many programming languages restrict a function to returning only a single object, Python has a powerful and elegant way to return multiple values simultaneously. This is achieved by having the function automatically package all the return values into a tuple. 1. Returning comma-separated values. Inside the function, you simply list the values or variables you want to return, separated by commas. Python automatically wraps these comma-separated values into a single tuple object before returning it. 2. Capturing the tuple result. When you call this function and assign it to a single variable, that variable will contain the entire tuple. We can then access individual values using the standard tuple indexing, starting at 0. 3. Unpacking the values. There is a way to handle multiple returns is through tuple unpacking. By assigning the function call to multiple variables, the same number as the return values, Python automatically unpacks the tuple, assigning each value to its respective variable. To summarize, returning multiple values is a powerful feature that simplifies code when a single operation naturally produces several related results. You may use tuple unpacking for clean and readable code when capturing multiple returns. Our next lecture 12.05. Local and global variables. See you there. Welcome back. When dealing with functions, it's crucial to understand where variables live. This concept is called variable scope. In Python, variables are either local, meaning they exist only inside a function, or global, meaning they exist throughout the entire program. Understanding this prevents one of the most common coding errors. 1. Global variables. A variable defined outside any function, usually at the top level of the script, is a global variable. It can be accessed and read by any function in the program. Here, global_value is accessible everywhere. 2. Local variables. A variable defined inside a function is a local variable. It is created when the function is called and destroyed when the function finishes. Local variables cannot be accessed from outside the function. Trying to read local_value from the global scope will result in a name error. Three. Scoping rule summary. Python follows the LEGB rule, local, enclosing, global, built-in. For now, the most important rule is, a function can always read a variable from the global scope, but it can never assign to or modify a global variable without explicit declaration, and it can never be read from the outside. To summarize, variables have boundaries. Local variables are temporary tools for the function's internal work, while global variables provide program-wide settings. Always remember to capture a function's result with return, instead of relying on modifying global variables. Our next lecture 12.06. Accessing global variable with the same name. See you there. Welcome back. In Python, it is entirely possible to define a local variable inside a function that has the exact same name as a global variable defined outside the function. The question is, which variable takes precedence? This concept is known as variable shadowing. 1. Local variable shadowing. Python's rule is simple. If a variable is assigned a value inside a function, it is assumed to be a local variable, regardless of whether a global variable with the same name exists. This local variable temporarily shadows, or hides the global one for the duration of the function's execution. Outside the function, the global variable remains unchanged. Two, using the global keyword. If you genuinely need to modify the global variable from within a function, you must explicitly declare your intention using the global keyword before referencing the variable. This tells Python not to create a new local variable, but to use and modify the existing global one. Three, good practice. While the global keyword exists, it is generally considered bad practice to rely on modifying global state from within a function. Functions should ideally communicate with the outside world through parameters and return values. Use the global keyword only when absolutely necessary, for instance, in single-file scripts or when dealing with complex system configurations. To summarize, Python is highly protective of global variables. Any assignment inside a function creates a new local variable unless you use the global keyword. Favor passing data via parameters and return values over relying on global state changes. Our next lecture 12.07. Assign function to a variable. See you there. Welcome back. We are now moving into more advanced concepts where functions are treated as objects, just like integers or strings. This is known as first-class functions. This means you can assign a function itself to a variable, which is incredibly useful for flexible and dynamic programming. 1. Functions as first-class objects. In Python, everything is an object, including functions. When you define a function, you're creating an object and assigning it to the function's name. We can prove this by simply printing the function's name without parentheses. It shows its type and memory location. 2. Assigning to a new variable. Because a function name is just a variable pointing to the function object, you can assign it to a new variable. Note that we use the function name add without parentheses. This new variable, alias_sum, becomes an alias for the original function. Three, executing the function via the alias. Now that the new variable points to the function object, you can call the function using the alias name, just as if it were the original function. The function executes the same code and returns the same result. To summarize, understanding that a function name is simply a reference to a function object is the first step toward advanced programming techniques. This concept is fundamental to the functional programming paradigm in Python. Our next lecture 12.08. Function inside another. See you there. Welcome back. Building on the idea that functions are objects, we now explore a powerful organizational feature, nested functions. This means defining one function entirely inside the body of another function. This is often used to hide helper functions that are only relevant to the outer function. 1. Defining the nested function. Inside the outer function, process_data, we define a helper function, clean_text. This inner function is local to process_data. It follows the exact same syntax, the def, keyword, a name, and an indented body. 2. Scope of the nested function. The inner function, clean_text, can only be called from inside the outer function. If you try to call clean_text from the global scope, you'll get a name error because it is a local object of the outer function. This protects the helper function from being misused externally. 3. Accessing outer variables. A key advantage is that the inner function can access variables defined in its enclosing or outer function, even if those variables were not passed as parameters. This creates what is known as a closure, which is a fundamental concept in advanced Python. To summarize, use nested functions for better code organization when a function needs complex helper logic that should not be visible or accessible to the rest of the program. Our next lecture 12.09. Function as parameter to another. See you there. Welcome back. Since functions are first-class objects in Python, just like variables or lists, they can be passed around. This means we can pass a function itself as an argument to another function. This capability is fundamental to writing highly flexible and abstract code. 1. Defining the helper functions. First, let's define two simple helper functions, add and subtract, that perform basic arithmetic. These are the functions we intend to pass as arguments later. 2. The higher-order function. Next, we define a higher-order function called do_calculation. This function takes three parameters, two numbers and a function itself, which we call operation. Inside this function, we simply execute the passed-in operation function, treating it like a normal callable object. 3. Dynamic execution. Now, we call do_calculation. In the first call, we pass the add function and the calculation performs addition. Crucially, notice we pass the name of the function without parentheses. In the second call, we pass the subtract function and the same higher-order function performs subtraction. This makes the calculation dynamic and reusable. To summarize, passing functions as parameters is a fundamental pattern for creating abstract and flexible code. It enables you to write one generic function that can perform many different actions based on the specific function you feed it. Our next lecture 12.10. Returning functions. See you there. Welcome back. We have seen that functions can be assigned to variables and passed as arguments. Now, we explore the third key aspect of first-class functions, the ability for one function to return another function as its result. This might sound abstract, but it's a powerful tool for building dynamic code generators. 1. Defining the outer and inner functions. We define an outer function, create_multiplier, which takes a factor. Inside it, we define a nested function, multiplier, which takes a number. The key step is that the outer function returns the inner function object itself, without calling it. Two, capturing and calling the return function. To use this, we first call the outer function, create_multiplier, which returns the function object. We capture this returned object in a variable, say, double_me. Now, double_me is an actual function that can be called with new arguments. Three, creating different function instances. We can call the outer function again with a different factor, say 5. This creates an entirely new function object, quintuple_me, which is permanently set to multiply by 5. This illustrates how one function can dynamically generate custom functions. To summarize, returning functions allows for function factories, a single outer function that creates many specialized, customized function objects. This advanced technique is crucial for writing clean, powerful, and reusable code structures in Python. Our next lecture 12.11. Pass any type. See you there. Welcome back. One of Python's greatest strengths, especially when writing functions, is its flexibility. Python is a dynamically typed language, meaning you do not have to declare the data type of a parameter when defining a function. This allows a single function to operate on integers, strings, lists, or any other object, provided the internal operations are valid for that type. 1. Defining a generic function. We define a simple function called double_value that takes one parameter, data. The operation inside the function, which is multiplication by 2, will behave differently depending on the type of data passed in. 2. Passing different types. Let's call the same double_value function with 3 different data types. For an integer, multiplication is arithmetic. For a string, multiplication is repetition. For a list, multiplication is also repetition, extending the list's elements. 3. Duck typing principle. This behavior is guided by Python's duck typing principle. If it walks like a duck and quacks like a duck, it's a duck. In programming terms, if the object passed to the function supports the operation defined inside the function, in this case, multiplication, then the function will execute successfully, regardless of the object's formal type. To summarize, Python's flexibility means you can write generic functions that work with diverse data types. Your function's success depends only on whether the passed object supports the operations you perform on it. Our next lecture 12.12. Recursion. See you there. Welcome back. We are now introducing a powerful and elegant programming technique called recursion. Recursion is a method where a function solves a problem by calling itself one or more times until a specific condition is met. Think of it like a set of Russian nesting dolls, where each doll is solved by looking at the smaller doll inside. 1. Definition of recursion. In simple terms, a function is recursive if it includes a call to itself in its own body. Recursion is often used to solve problems that can be broken down into smaller, identical subproblems, such as calculating factorials or traversing tree structures. 2. Essential components of recursion. To prevent a function from calling itself infinitely, which would crash the program, every recursive function must have two fundamental parts. First, the base case, which is the stopping condition. When this condition is met, the function stops calling itself and returns a result. Second, the recursive step, which is the part where the function calls itself with a slightly simpler or smaller input, moving toward the base case. Three, the danger of infinite recursion. If you forget to define a correct base case, or if the recursive step never reaches the base case, the function will call itself forever. This rapidly consumes memory on the system call stack, leading to a recursion error, which limits Python's recursion depth to typically around 1,000 calls. To summarize, recursion is an alternative to iteration for solving repetitive problems. The correct base case is non-negotiable. It is the safety brake that prevents your program from running indefinitely. Our next lecture 12-13. Recursion. See you there. Welcome back. In this lecture, we will put the theory of recursion into practice by implementing a classic recursive problem, calculating the factorial of a number. This will illustrate how the base case and the recursive step work together to solve the problem. 1. Defining the factorial problem. The factorial of a non-negative integer, n, denoted as an exclamation mark, is the product of all positive integers less than or equal to n. The formula is n factorial equals n times n minus 1 factorial. This definition is inherently recursive, which makes it perfect for a recursive function. 2. The base case and recursive step. For the factorial function, the base case is simple. The factorial of 0 or 1 is 1. This is where the recursion stops. The recursive step is the formula itself, the current number multiplied by the factorial of the next smaller number. Three, tracing the execution. Let's trace factorial of 3. First, factorial of 3 returns 3 times factorial of 2. Next, factorial of 2 returns 2 times factorial of 1. Finally, factorial of 1 hits the base case and returns 1. The results then multiply their way back up. 2 times 1 equals 2, and then 3 times 2 equals 6. The result is 6. To summarize, recursive solutions elegantly map to mathematical definitions like the factorial. They solve a problem by deferring the full calculation until the simplest case, the base case, is reached, then building the result back up. Our next lecture 12.14. Keyword arguments. See you there. Welcome back. Until now, we have used positional arguments, where the arguments passed to a function are matched to the parameters based purely on their order. Python also allows you to use keyword arguments, where you explicitly name the parameter for each argument. This significantly improves code readability. 1. Positional arguments versus keyword arguments. Let's define a function that takes 3 parameters: name, message, and repeat. In the traditional positional call, we must ensure Alice is first, hello is second, and 3 is third. With keyword arguments, we explicitly assign the value to the parameter name using the equal sign. Two, the order advantage. The key benefit of keyword arguments is that they can be supplied in any order you like. Python reads the name of the parameter and maps the argument accordingly, making the code much more readable, especially for functions with many parameters or when the meaning of the data is not immediately obvious. 3. Mixing positional and keyword arguments. You can mix both styles in a single function call, but you must follow one strict rule. All positional arguments must come before any keyword arguments. Once Python encounters a keyword argument, all subsequent arguments must also be keywords. To summarize, keyword arguments are highly recommended for clarity, especially when calling functions with many parameters. Always place positional arguments first when mixing the two styles. Our next lecture 12-15. Default arguments. See you there. Welcome back. In Python, we can assign a default value to a parameter in the function definition. This makes the argument optional when the function is called. If the caller provides a value for that parameter, the provided value is used. If the caller omits the value, the default value is automatically used instead. 1. Defining default arguments. To set a default value, simply use the assignment operator, the equal sign, after the parameter name in the function definition. Here, message and is underscore urgent have default values, but name does not, meaning name is still a required parameter. 2. Optional function calls. Since message and is underscore urgent have defaults, we can call the function in several ways. We can use the minimum required argument, which is name. We can override one of the defaults, or we can override both. 3. Rule. Required parameters first. There is a strict rule when defining functions. All parameters without default values must be defined first, followed by all parameters with default values. This is because Python matches positional arguments from left to right and must know which arguments are required. To summarize, default arguments make your functions easier to use by allowing callers to ignore parameters they're not interested in or they don't know what to put in. Remember the rule: required parameters must always be listed before optional, defaulted parameters. Our next lecture 12-16. BMI use case. See you there. Welcome to our use case lecture for functions. We will now consolidate our knowledge by writing a single function to calculate the body mass index, or BMI. This function will use parameters, a default argument, the power operator, and return multiple, clearly labeled results. 1. Function definition and default arguments. The BMI formula requires weight in kilograms and height in meters. We define our function, calculate underscore BMI, to take two required parameters, weight and height. We will also include an optional parameter, unit underscore system, with a default value of metric to allow for future conversion logic, although we won't implement the full conversion here. 2. Calculation and interpretation logic. First, we calculate the BMI using the formula, weight divided by height raised to the power of 2. Next, we use a simple if-else structure to interpret the result and assign a textual category to the category variable. 3. Returning multiple values. We want to return both the numerical BMI value, rounded to 2 decimal places, and the text category. We use Python's feature of returning comma-separated values, which are packaged into a tuple. 4. Function calls and unpacking. Finally, we call the function using tuple unpacking to neatly capture the two returned values into my_BMI and my_category. We also demonstrate a keyword argument call, explicitly setting the unit_system, even though we are using the default. To summarize, this BMI calculator demonstrates how functions centralize complex logic, make parameters optional with defaults, and efficiently deliver multiple results using tuple returns. Our next lecture 12-17. Args and Quargs. See you there. Welcome back. We are now covering Python's flexible function feature, the ability to accept an arbitrary or variable number of arguments. This is done using two special syntaxes, *args for positional arguments and *quargs for keyword arguments. These are essential for writing highly flexible, general-purpose functions. 1. Capturing positional arguments with *args. The asterisk, or star, before a parameter name, commonly named args, tells Python to collect all excess positional arguments into a single tuple. This means the function can be called with 0, 1, or 100 positional arguments, and they all end up inside the args tuple. When we call custom_sum, all the numbers are passed into the args tuple, which we can then iterate over or apply functions to, like the built-in sum function. 2. Capturing keyword arguments with *quargs. The double asterisk or double star before a parameter name, commonly named quargs, tells Python to collect all excess keyword arguments into a single dictionary. The parameter names become the dictionary keys, and the argument values become the dictionary values. In this example, user, ID, and status are all passed as keywords and captured inside the quargs dictionary. 3. The full parameter order. When defining a function with both required, default, *args and *quargs, you must adhere to a strict order. First, required positional arguments, then default arguments, then *args, and finally, *quargs. Violating this order results in a syntax error. To summarize, *args and *quargs are the tools for creating catch-all functions that don't need to know the exact number of arguments beforehand. This flexibility is widely used in library and framework design. Our next lecture 12-18. Passing optional sprums to other functions. See you there. Welcome to the final lecture of our function section. We just learned how *args and *quargs can collect an arbitrary number of arguments. Now, we will learn how to forward these collected arguments to another function. This is a crucial technique for writing wrapper functions and decorators. 1. Defining the target function. Let's start with a simple function, target_func, that takes two required parameters, a and b, and one default parameter, greeting. This is the function we want to call from inside our wrapper. 2. Creating the wrapper and forwarding. Now we define our wrapper_func. It uses *args and *quargs to catch every single argument passed to it. Crucially, when calling target_func inside, we use the same syntax, *args and *quargs, to unpack the collected tuple and dictionary back into individual positional and keyword arguments for the target function. 3. The execution flow. When we call wrapper_func, the arguments are neatly packaged up inside the wrapper, passed through the unpacking operators to target_func, which receives them exactly as if it had been called directly. This pattern enables us to add extra logic, like logging or validation, around an existing function without changing the original function's call signature. To summarize, the ability to both collect arguments into *args and *quargs and then unpack them again using the same symbols is essential for writing powerful, extensible Python functions, particularly for decorators, which maybe we will see very soon. We have completed the functions section. Next section is Lambdas, and next lecture is 13.01. Introduction. See you there. Welcome to a new section, focusing on more advanced and functional programming features in Python. We start with lambda functions. A lambda function is a small, anonymous function defined in a single line. They are often called anonymous because they don't have a formal name like functions defined with the def keyword. 1. Standard function versus lambda function. Compare a standard def function, like add_10, to its lambda equivalent. A standard function requires the def keyword, a name, parentheses for arguments, the return keyword, and a block of indented code. A lambda function uses the lambda keyword, followed by arguments, a colon, and the single expression to be returned. 2. The lambda syntax and structure. The syntax is simply the lambda keyword, followed by one or more arguments, separated by commas, a colon, and a single expression. The value of this expression is automatically returned, so you don't need the return keyword. 3. Assigning and calling a lambda. You can assign the lambda function object to a variable like my_lambda. Then you call the variable name with arguments just like a normal function. However, the primary use case for lambdas is passing them directly as arguments to higher-order functions like map and filter, which maybe we'll see soon. 4. Key limitations. Lambdas are limited to a single expression. You cannot include multiple statements, complex control flow like if-else blocks, or multiple lines of code. They are suited for simple, quick, one-off operations. To summarize, lambda functions provide a clean, concise way to define simple operations without formal function definitions. We will see their true power when we use them to streamline sorting and filtering operations. Our next lecture 13.02. Lambda, cube of a given number. See you there. Welcome back. Let's start practicing lambda functions by creating a simple anonymous function that calculates the cube of any given number. This exercise will reinforce the core lambda syntax. 1. Defining the lambda function. We assign our lambda to a variable called cube. The structure is lambda, followed by one argument, x, a colon, and the expression, which is x raised to the power of 3. Remember, the result of the expression is automatically returned. 2. Executing the lambda. We can now execute the lambda function by calling the variable name, cube, and passing in an argument. When we pass 5, it returns 125. When we pass 2, it returns 8. The syntax is clean and concise for this simple mathematical operation. 3. Comparison with standard function. Notice how much code the Lambda function saves compared to the traditional def function for the exact same logic. For simple, one-off operations, the Lambda function is the preferred, idiomatic Python approach. To summarize, we created a simple, single-argument Lambda. The Lambda keyword, followed by the argument and the expression, provides instant functionality without the boilerplate of a full function definition. Our next lecture 13.03. Lambda, even or odd. See you there. Welcome back. While Lambda functions are limited to a single expression, we can still perform simple conditional logic inside them using the ternary operator or the conditional expression. This allows us to check if a number is even or odd and return a corresponding string, all in one line. 1. The ternary operator syntax. This operator is Python's way of writing an if-else statement as a single expression, which is what a Lambda function requires. The structure is the value to return if the condition is true, followed by the if keyword, the condition itself, the else keyword, and finally, the value to return if the condition is false. 2. Defining the even or odd Lambda. We define check_parity. It takes one argument, number. The expression uses the ternary operator. If number modulus 2 equals 0, it returns even. Otherwise, it returns odd. This entire logic fits neatly into the single Lambda expression. 3. Testing the Lambda. When we call check_parity with 4, the condition is true and it returns even. When we call it with 7, the condition is false and it returns odd. This demonstrates how to pack conditional logic into the Lambda's single expression limit. To summarize, when you need a Lambda to return one of two values based on a simple test, you may use the ternary operator for the job. It maintains the Lambda's conciseness while providing necessary logic. Okay, our next lecture 13.04. Lambda, sum of two numbers. See you there. Welcome back. While our previous Lambdas only took one argument, a Lambda function can handle any number of arguments. In this short exercise, we will define a Lambda that takes two parameters and returns their sum, demonstrating the multi-argument syntax. 1. Defining the multi-argument Lambda. We name our Lambda sum_2. The arguments a and b are separated by a comma before the colon. The expression is simply a plus b. This structure shows that the argument side of the Lambda is just a list of parameters, similar to a regular function's parentheses. 2. Executing the Lambda. We call sum_2 with two arguments, 10 and 5, which are correctly mapped to a and b based on their position. The function returns 15. In the second example, 120 return 120. This confirms that the Lambda correctly handles multiple positional arguments. 3. Lambdas and dynamic typing. Since Lambdas are functions, they also follow Python's dynamic typing. The same addition operator works differently when used with strings, performing concatenation instead of arithmetic addition. This means one Lambda can serve multiple data types. To summarize, Lambdas are versatile. They can take one, two, or many arguments, as long as the entire logic remains a single, returnable expression. Our next lecture 13.05. Using a filter. See you there. Welcome back. We now explore the primary use case for Lambda functions, using them anonymously with Python's built-in higher-order functions. We start with the filter function, which allows you to select elements from an iterable that satisfy a specific condition. 1. Understanding the filter function. The filter function takes two arguments, a function and an iterable like a list. The function must return a Boolean value, true or false. Filter applies this function to every item in the iterable and only keeps the items for which the function returns true. The result is a filter object, which we typically convert to a list. 2. Filtering even numbers with Lambda. Here is our list of numbers. We pass our anonymous Lambda directly as the first argument to filter. The Lambda checks if a number is divisible by 2. Filter then processes the numbers list and even underscore filter only retains the elements where the Lambda returned true. Finally, we convert the result to a list, showing only the even numbers. 3. The benefit of using Lambda. If we had used a regular def function, we would have needed 4 lines of code just to define a simple is_even function. By using an anonymous Lambda, we define the filtering condition right where we need it, keeping the code clean, concise, and localized to a single line. To summarize, combining filter with a Lambda is idiomatic Python for filtering data. The Lambda provides the Boolean logic, and filter handles the iteration. Okay, our next lecture 13.06. Using the map function. See you there. Welcome back. After learning about filter, we now turn to the map function. While filter is used for selecting elements, map is used for transforming or applying an operation to every element in an iterable. This is another core application for our concise Lambda functions. 1. Understanding the map function. Like filter, map takes a function and an iterable. However, instead of checking for true or false, map applies the function to every single item and collects the result of that application. The output is a map object, which we typically convert to a list or another collection. 2. Squaring numbers with Lambda and map. Here is our list of numbers. We pass an anonymous Lambda that returns the square of the input, x. The map function applies this squaring operation to every number in the list. The squared underscore map object stores these results, and converting it to a list shows the new, transformed list 1, 4, 9, 16, and 25. 3. Transforming strings. The Lambda and map combination isn't just for numbers. Here, we use map to transform a list of lowercase names into uppercase names. The Lambda simply calls the upper string method on each name, demonstrating its versatility for applying any single transformation. To summarize, use map and Lambda when you want to change every item in a collection in the same way. It's concise, readable, and often more efficient than writing a traditional for loop. Okay, our next lecture 13.07. Using reduce function. See you there. Welcome back. We've learned filter for selection and map for transformation. Now, we introduce the last of the functional trio, the reduce function. The reduce function applies a function cumulatively to the items of an iterable, reducing the iterable to a single, final value. Unlike filter and map, reduce is not built in and must be imported. 1. Importing and understanding reduce. First, we must import reduce from the functools module. Reduce takes a function which must accept two arguments, an iterable and an optional initializer. It takes the first two items of the iterable and applies the function, then takes the result and the next item, and so on, until only one value remains. 2. Calculating the product with lambda and reduce. Here, our lambda is named product_lambda. It takes two arguments, ACC for accumulator or running result, and item for the current list item. It returns their product. Reduce applies this lambda cumulatively. It calculates 1 times 2, then takes the result, 2, and multiplies it by 3, then takes 6 and multiplies it by 4, resulting in the final product of 24. 3. The internal flow of reduce. Think of reduce as constantly combining the next element of the list with the accumulated result so far. This makes it ideal for aggregation operations like summation, finding the maximum value, or, as we did, calculating the product of all elements. To summarize, reduce is used for combining a list of things into one thing. The lambda must take two arguments for the current accumulation and the next item. With filter, map, and reduce, you have the core functional tools. Okay, our next lecture 13.08, decorators. See you there. Welcome to an advanced Python topic, decorators. Decorators are a key feature used heavily in web frameworks and library code. Simply put, a decorator is a function that takes another function as input, adds some functionality to it, and returns the augmented function, all without explicitly modifying the original function's code. 1. What is a decorator? A decorator is essentially a wrapper. Think of it like adding icing to a cake. The cake, the original function, remains fundamentally the same, but the icing, the decorator, adds new presentation or flavor, which is new functionality like logging, timing, or access control. It follows the pattern. Function A decorates function B. 2. Prerequisites. Nested functions. Decorators rely on two concepts we've already covered: functions inside another function and returning a function. Here, inner_func is defined inside outer_func, and outer_func returns inner_func. Decorators are built upon this exact pattern. The variable f now holds a reference to inner_func. Calling f executes the inner function, demonstrating how a function can be dynamically generated and returned. 3. The decorator mechanism. At a high level, a decorator, let's call it decorator, is simply a function that takes an original_func and returns a decorated_func. This decorated function contains the original function plus the extra logic added by the decorator. The returned function completely replaces the original function reference. To summarize, decorators provide a clean, reusable way to wrap functions and add common functionality without polluting the function itself. Okay, our next lecture 13.09, decorator that doubles the result of a function. See you there. Welcome back. In this lecture, we will build a functional decorator. This decorator, called double_result, will take any function that returns a number and ensure that number is multiplied by 2 before being returned to the caller. This requires 3 layers of nested functions. 1. Defining the decorator structure. Our decorator, double_result, must take one argument, the function it is decorating, referred to as func. Inside, we define the wrapper function. This wrapper uses *args and *quargs to ensure it can accept any arguments intended for the original func. Finally, the decorator returns the wrapper function. 2. Adding the core logic. Inside the wrapper, we call the original func, forwarding all the collected *args and *quargs to it. The result is stored in original_result. Our decorator's unique logic is applied next. We multiply this result by 2 and return the modified value. The caller of the decorated function will now only see this doubled result. 3. Manual decoration and calling. We define a simple add function. To manually decorate it, we pass add to double_result. This returns the wrapper, which we assign back to decorated_add. When we call decorated_add with 3 and 2, the add function returns 5, but the wrapper intercepts this, multiplies 5 by 2, and returns 10. To summarize, we created a decorator that wraps and modifies the output of a target function. This manual method is important for understanding the mechanics. However, Python provides a much cleaner, more elegant way to apply this decoration, which maybe we'll see soon. Okay, our next lecture 13.10. Using @decorator. See you there. Welcome back. In the previous lecture, we built our double_result decorator and applied it manually. That manual assignment is how decorators fundamentally work, but Python provides a cleaner, more readable way to apply them using the @sign or @symbol syntax. 1. Reviewing the manual decoration. Recall that manually applying the decorator requires us to overwrite the original function reference. This is valid Python, but it requires an extra line of code and is less intuitive to read. 2. The @decorator syntax. The @sign syntax is a piece of syntactic sugar. Placing followed by the decorator's name, double_result, directly above the DEF line is exactly equivalent to the manual assignment. The function add is automatically passed to the double_result function, and the returned wrapper function replaces add. 3. Testing the decorated function. When we call add with 3 and 2, it is no longer the original add function. It is the wrapper returned by double_result. This wrapper calls the original add, gets 5, multiplies it by 2, and returns 10. The syntax makes the code extremely clear about what decorator is being applied. To summarize, the syntax is the standard and most Pythonic way to apply decorators. It is concise and visually shows the function's extra behavior. Okay, our next lecture 13.11. Decorating strings. See you there. Welcome back. We've seen decorators modify numbers. Now, let's build a decorator that adds some flair to string outputs. We will create a decorator that wraps the result of any function with a specific character, like asterisks, which is useful for formatting output messages. 1. Defining the star wrapper decorator. We define our decorator, star_wrapper, which takes the function func as input. The inner wrapper calls func, passing all arguments via *args and *quargs, and stores the string result. The decorator's logic then takes the result and prepends and appends 3 asterisks, modifying the string before returning it. 2. Decorating and calling the string function. We use the syntax to apply *_wrapper to get_greeting. When we call get_greeting with Alice, the original function returns hello, Alice, but the decorator wraps it in asterisks, returning **hello, Alice***. This clearly shows that the decorator works seamlessly with string outputs. 3. The flexibility of decorators. This example highlights how versatile decorators are. Whether the function returns a number, as in the previous lecture, or a string, the decorator can add functionality, such as modifying the return value, timing the execution, or adding authentication, without altering the function's internal logic. To summarize, we use the decorator pattern and the syntax to add structural modification to a string result. Since a function is just an object, we can apply as many decorators as we want to it. Okay, our next lecture 13.12. Decorator chaining. See you there. Welcome back. Now that we can apply a single decorator using the @sign syntax, let's explore decorator chaining. This is the process of applying multiple decorators to a single function to combine their functionalities. This is very common in frameworks like Django and Flask for tasks like logging and authentication. 1. Defining multiple decorators. We will reuse our 2 previous decorators, _result, which multiplies the output by 2, and *_wrapper, which converts the output to a string and wraps it in asterisks. Notice that *_wrapper now uses str to handle the numerical output from the first decorator. 2. Applying the decorators. To apply multiple decorators, you simply stack the syntax lines one after the other, directly above the function definition. Here, we apply *_wrapper on top of _result, which decorates the calculate function. 3. The execution order. When chaining, the decorators are applied bottom-up, meaning the one closest to the function, _result, is applied first. This result is then passed to the next decorator up, *_wrapper. The execution order is: calculate runs first, then _result modifies the output, and finally, *_wrapper modifies that output one last time before the final result is returned to the user. To summarize, decorator chaining allows for modular function enhancement. The order matters significantly because the output of one decorator becomes the input of the next. This completes our section on decorators. Okay, our next lecture 13.13. Generators. See you there. Welcome to the section on generators. Generators are a powerful and memory-efficient way to create iterators in Python. Unlike regular functions that return a single result and then terminate, generators can pause their execution, yield a value, and then resume exactly where they left off when the next value is requested. 1. The problem: memory usage. Consider a regular function that creates a large list. When you call create_list with 1,000,000 items, The entire list of 1,000,000 numbers must be created and stored in your computer's memory immediately before the function can return. This uses a lot of memory, which can crash your program if the list is too big. 2. The solution. The yield keyword. Generators solve this problem by replacing the return keyword with yield. When a function contains yield, it becomes a generator function. The yield keyword doesn't stop the function completely. It pauses it, sends a value back, and saves its internal state. The function can then be resumed from where it paused. 3. Lazy evaluation. This pausing and resuming is called lazy evaluation or on-demand generation. The generator only calculates and gives you the next value when you explicitly ask for it, typically by iterating over it in a for loop. This means that even a generator capable of producing 1,000,000,000 numbers will only hold one number in memory at any given time, making it incredibly memory efficient. To summarize, generators are essential for handling large datasets or infinite sequences without running out of memory. The presence of the yield keyword is the defining feature of a generator function. Okay, next lecture 13.14. Create a generator. See you there. Welcome back. Let's get hands-on and create a simple, practical generator function. We will build a generator that produces a sequence of even numbers up to a specified limit. This example will demonstrate the behavior of the yield keyword and the lazy evaluation process. 1. Defining the generator function. We define even underscore number underscore generator, which takes a limit n. Inside, a for loop iterates up to n. The key is the yield keyword inside the if condition. When this line is reached, the function pauses, returns the current even number, and waits until the next value is requested. 2. Creating the generator object. When we call the function even underscore number underscore generator with 10 and assign the result to gen, the code inside the function doesn't execute immediately. Instead, it returns a special object, a generator object. This object is an iterator that controls the function's pause state. 3. Iterating and executing the generator. We can manually pull values out using next. The first next call runs the code until the first yield, returning 0. The second next call resumes the function exactly after the first yield, continues the loop, finds the next even number, 2, yields it, and pauses again. Most of the time, we simply iterate over the generator object using a for loop which automatically handles all the next calls. To summarize, generators are memory superheroes. They generate large sequences on demand, keeping your code efficient. Our next lecture 13.15. Keywords in Python. See you there. Welcome to our final lecture in this section. Since we have learned many advanced topics like Lambda functions, decorators, and generators, let's take a moment to review the fundamental reserved words, the keywords in Python. You cannot use any of these keywords as variable or function names. 1. Basic control flow and data structure keywords. These are the words you've used most often. If, else, and elif manage branching logic. For and while manage loops with break and continue, modifying loop execution. Return exits a function and in, is, not, and, or are for membership testing and logical operations. Maybe these keyword is the keyword, you will not often use it. 2. Function and object keywords. This group includes the foundation of object-oriented programming, def for functions, class for defining custom types, and self for instance methods. We also have the keywords we just covered, lambda for anonymous functions and yield for generators. Global and non-local manage variable scope, and pass is a placeholder for empty code blocks. 3. Exception and module keywords. This group manages error handling, try, except, finally, raise, and assert. Import, from, and as are used to bring in code from other modules, which we'll cover next. And with may be used for resource management, typically with files. 4. Special keywords. Finally, true and false are the Boolean values, and none represents the absence of a value. The keyword del is used to delete references to objects. To summarize, we've learned some of keywords, from simple flow control to advanced functional features like lambda and yield. Knowing these helps you can write code correctly and understand what Python is trying to do. This marks the end of Section 13. The next section focuses on structuring and organizing your code into reusable files using modules. We will learn how to import existing libraries and even our own Python files. Join me in Section 14 and our next lecture 14.01. Introduction. See you there. Welcome to a new section on modules. As your programs grow, you'll need a way to organize your functions, variables, and classes into separate, manageable, and reusable files. In Python, this is achieved using modules. Modules are the fundamental way to structure your code and share functionality. 1. What is a module? Simply put, a module is just a Python file, a file with a py extension containing Python code. This code can be anything: function definitions, class definitions, or variables. Think of it like a toolbox containing specific tools. For example, you might have a module named calculations.py with functions for adding, subtracting, and multiplying. 2. Why use modules? There are two main reasons. The first is organization. Modules prevent your programs from becoming one giant, impossible-to-manage file. They allow you to logically group related code. The second is reusability. Once a function or class is defined in a module, you can easily use it in any other Python program you write without copying and pasting the code. 3. The import statement. To use the functions and variables defined inside a module, you must use the import keyword. When you run import module_name, Python finds that module's file, executes all the code inside it, and makes all its definitions available for use in your current script. To summarize, modules are the building blocks of large Python applications. They allow code to be neatly packaged and shared. Next, we will create our own custom module and practice importing and using the code we define inside it. Let's put the concept of modules into practice by creating a simple Python file and learning how to access its functions from another file. Join me in Lecture 14.02. Create a module and use it. See you there. Welcome back. Let's now put theory into practice by creating our own custom module. We will create two files, one file to hold our reusable code, and a second file to import and use that code. This demonstrates the core principle of modular programming. 1. Creating the module file. First, create a file named calculations.py. Inside this file, we define two simple functions, add and multiply, and a variable, course_name. This entire file, calculations.py, is now our module. 2. Importing the module. Now, in a separate file, say main.py, we use import calculations. This makes everything defined in calculations.py available to us. Crucially, when using the imported elements, we must prefix them with a module name and a like calculations.add or calculations.course_name. This prevents naming conflicts. 3. The output. The output confirms that our main.py file successfully accessed and executed the add and multiply functions, as well as the course_name variable defined in the completely separate calculations.py module. To summarize, we have created and used a module demonstrating a way to organize and reuse code in Python. Our next lecture 14.03. Different ways to import. See you there. Welcome back. While the simple import module_name works, Python offers other ways to import code, allowing you to control exactly what is imported and what name it is given. We will look at 3 common import variations in this lecture. 1. Import all. As we saw, the standard way is import calculations. This brings the entire module object into your script and requires you to use the prefix calculations before calling any function. This is generally the safest way, as it avoids naming conflicts with functions already in your script. 2. Importing specific elements. The from module import element syntax allows you to import only specific functions or variables like add and course_name. Once imported this way, you can call them directly without the calculations.prefix. This is useful when you only need a few items from a large module, but it carries a higher risk of naming conflicts. 3. Importing with an alias. If the module name is too long, you can use the import as syntax to give it a shorter alias. For instance, import calculations as calc. Now you use calc instead of the full name, saving typing while still maintaining the safety of prefixing. 4. Wildcard import. The from module import star syntax imports absolutely everything from the module directly into your current namespace. While convenient, this is generally discouraged because it makes it very difficult to track where functions are defined and significantly increases the chance of accidental name collisions. To summarize, Python provides flexibility in importing. The safest is import module name, the most readable is import as, and the most selective is from import. Our next lecture 14.04. Use math module. See you there. Welcome back. Having learned how to create and import our own modules, let's now start using Python's extensive standard library, a collection of built-in modules ready for use. We begin with the math module, which provides access to common mathematical functions and constants. 1. Importing and using constants. We start by using the standard import math. We can now access the mathematical constant pi as math.py. Here, we use it to calculate the area of a circle. Notice that we use the module name prefix, math., which is a good practice for clarity. 2. Using basic functions. The math module offers many functions. Math.sqrt calculates the square root, and math.pow calculates one number raised to the power of another. You could perform these operations using basic arithmetic operators, but the math module ensures the highest precision and clarity for mathematical intent. 3. Rounding functions. The module also contains specific rounding methods. Math.floor always rounds a number down to the nearest whole number, making 14.7 become 14. Math.ceil always rounds a number up to the nearest whole number, making 14.7 become 15. These are precise tools for specific mathematical requirements. To summarize, the math module is crucial for any scientific or engineering application. We used it with the import statement. Our next lecture 14.05. Use random module. See you there. Welcome back. After the math module, we move on to one of the useful modules for applications that involve chance or simulation, the random module. This module allows us to generate pseudo-random numbers, which are essential for games, creating test data, and adding unpredictability to your programs. 1. Generating random integers. We import random. To get a random whole number, we have two primary functions. Randomd works like the range function. It includes the start but excludes the stop value. Randomd, on the other hand, is generally simpler for ranges because it includes both the start and the stop value in the possible results. Always be mindful of whether the upper limit is inclusive or exclusive. 2. Generating random floats. Random returns a random floating point number between 0, inclusive, and 1, exclusive. This function is often used as a base for scaling random values to any desired range. 3. Random selection. The random module also handles selecting from sequences. Random.choice returns a single, randomly selected element from a list or tuple. Additionally, randomd.shuffle takes a mutable sequence like our colors list and rearranges its elements randomly in place. This may be used for simulating drawing cards or reordering player turns. To summarize, the random module is your tool for adding dynamic and unpredictable elements to your programs. Our next lecture 14.06. Number guessing game. See you there. Welcome to our final project for this section, building a classic number guessing game. This project is a review, bringing together our knowledge of the random, module, loops, and conditional logic to create an interactive program. 1. Setup and generating the secret number. First, we import the random module. We then use randomd to select a secret number between 1 and 20, including both endpoints. We initialize the guess variable to 0, which ensures it is not equal to the secret number at the start. This allows our while loop to begin. 2. The main game loop. The core logic is a while loop that continues as long as the user's guess is not equal to the secret underscore number. Inside the loop, we take the user's input, convert it to an integer using the try and except block to handle errors, and then provide feedback using if, elif, and else. If the guess is too low or too high, the loop continues. 3. Winning the game. When the user correctly guesses the number, the while loop condition becomes false, and the program breaks out of the loop. We place the final congratulatory message outside the loop, as it only executes once the loop has successfully terminated, confirming the win. To summarize, we integrated several Python concepts into a practical and fun application. Our next lecture 15.01. List Comprehensions. See you there. Welcome to Topic List Comprehensions. This is one of Python's powerful and elegant features. A list comprehension provides a concise, single-line way to create a new list based on the values of an existing sequence, often replacing multi-line for loops and append operations. 1. The traditional way. Imagine we want to create a list of squares for numbers from 0 to 4. Using the traditional method, we would first initialize an empty list, then use a for loop to iterate through the range, calculate the square, and finally, use the append method to add the result to the list. This takes 3 lines of code. 2. The list comprehension syntax. A list comprehension achieves the exact same result in a single line. The syntax is expression followed by for item in iterable. It is enclosed in square brackets, just like a list literal. In our example, x times x is the expression, and for x in range 5 is the loop. The result is a new list of squares. This is much more readable and faster to type. 3. Structure of a list comprehension. The structure is key. First, the expression, which is the value you want to place in the new list, such as x times x. Second, the loop, which defines what you are iterating over, such as for item in iterable. You read it in the order the computer executes it. For x in range 5, calculate x times x. To summarize, list comprehensions reduce boilerplate code and make your Python more efficient. Our next lecture 15.02. Cube of numbers in a list. See you there. Welcome back. In this lecture, we will practice our new list comprehension syntax by creating a list containing the cube of every number from an initial list. This is a list transformation task. 1. The traditional for loop method. To cube the numbers in our numbers list, we follow the long method. Initialize an empty list, loop through the source list, calculate number raised to the power of 3, and append the result. This requires 3 distinct lines for the operation itself. 2. Using list comprehension. Now let's use a list comprehension. We write cubes underscore LC equals and open the square brackets. The structure is number raised to the power of 3, which is the expression, followed by the loop structure for number in numbers. This single, compact line handles the initialization, iteration, calculation, and appending all at once. 3. The expression flexibility. Note that the expression part of the list comprehension can contain any valid operation, whether it's cubing, multiplying, calling a function, or formatting a string. As long as it returns a value, that value will be placed into the new list. To summarize, the list comprehension syntax is ideal for transforming every item in an iterable. Our next lecture 15.03. Even numbers in a list. See you there. Welcome back. We've used list comprehensions to transform lists. Now, let's unlock their more power by adding a conditional filter. This allows us to both iterate over a list and select only the elements that meet a specific criteria. We'll start by finding all the even numbers in a sequence. 1. The traditional filtering method. To filter out the even numbers using a for loop, we again start with an empty list. Inside the loop, we check the condition, if the number modulo 2 equals 0. Only if this if statement is true do we append the number to the new list. This requires 4 lines of boilerplate code to achieve simple filtering. 2. Filtering with list comprehension. The list comprehension is much more direct. The syntax for filtering places the if condition at the end after the for loop statement. It reads, for every number in numbers, include number, only if number modulo 2 equals 0. The expression part, number, is only evaluated and included if the trailing if condition is met. This is concise. 3. Structure with filter. The general structure now includes the optional if condition at the very end. The process is always iterate through the iterable, check the condition, and if true, apply the expression and add it to the new list. You may combine this with the transformation technique from the previous lecture, where the expression could be number times 2 instead of just number. To summarize, we've now seen how list comprehensions can handle both transformation and filtering. Our next lecture 15.04. Product of numbers in a list. See you there. Welcome back. We've used list comprehensions for transformation, like cubing numbers, and for filtering, like selecting even numbers. Now, let's combine these two techniques in a single, powerful line of code. We will create a list containing the product of numbers, but only for the numbers that meet a specific condition. 1. The combined operation using a for loop. To perform both steps traditionally, we iterate through the data list. We first check the if condition. If x is greater than 5. Only if that condition is true do we then apply the transformation, which is x times 10, and append it. This still requires 5 lines of code to achieve a simple 2-step operation. 2. Combining transformation and filtering. Using a list comprehension, we achieve the same result in a single line. The transformation, x times 10, is the expression at the beginning. The filtering condition, if x is greater than 5, is placed at the very end. The process is sequential. It iterates, filters, and then transforms. This demonstrates how readable and efficient list comprehensions are for common data processing pipelines. 3. Filter then transform logic. It is important to remember the order when the if condition is placed at the end. The condition acts as a filter on the iteration. Only items that pass the filter are sent forward to be transformed by the expression. The expression is not evaluated for items that fail the filter. To summarize, combining transformation and filtering in a single list comprehension is highly Pythonic and efficient. Our next lecture 15.05. Common elements in a list. See you there. Welcome to our final lesson on list comprehensions. We'll tackle a slightly more complex scenario, finding the common elements between two different lists. We can achieve this elegantly by combining an if condition with a nested loop structure inside a single list comprehension. 1. The traditional nested loop method. Traditionally, to find common items, you would use a nested for loop. The outer loop iterates through list A, the inner loop iterates through list B. You then check if x equals y, and if true, append the common element. This results in a multi-line, potentially slow, block of code. 2. Using list comprehension. In a list comprehension, the nested loops are placed one after the other, in the same order they would appear in traditional code. The expression is x. The loops are for x in list A and for y in list B. The condition if x equals y checks for equality. This single line clearly and concisely expresses the intent to find common elements. Note that the output is still a list containing the common elements 3 and 4. 3. More Pythonic alternative. Although the list comprehension works, an efficient and Pythonic way to find common elements may be to convert the list to sets and use the intersection operator, the ampersand sign. We convert the result back to a list only if required. Set operations may be optimized for finding commonalities and may be much faster than nested loops. To summarize, we have learned list comprehensions, learning how to transform, filter, and even nest loops within this concise syntax. This concludes section 15. Our next lecture 16.01. Introduction. See you there. Welcome to a major turning point in the course, Object-Oriented Programming, or OOP. Until now, we've used procedural programming, focusing on writing functions or procedures that operate on data. OOP is a different and powerful paradigm that structures programs around objects, which are essentially real-world entities. 1. What is object-oriented programming? OOP is a method of designing programs using concepts like classes and objects. Instead of viewing a program as a sequence of steps, we view it as a collection of interacting objects. Think of a car. It's an object with attributes like color and speed, and actions like accelerate and brake. 2. Why is OOP important? The shift to OOP offers several key advantages for large software projects. Firstly, it offers modularity by grouping related data and functions together. Secondly, it provides reusability because we can create new objects from existing classes. Thirdly, it offers maintainability, making code easier to update and debug because changes in one object are less likely to affect others. 3. Procedural versus object-oriented. In procedural code, data and functions are separate. You pass data to a function to operate on it. In OOP, data and the functions that operate on that data are bundled together inside an object. This creates self-contained entities that accurately model real-world concepts. To summarize, OOP is not just a coding style, it's a way of thinking about program architecture. It's essential for working with frameworks and building scalable applications. These 4 principles, encapsulation, abstraction, inheritance, and polymorphism, form the foundation of OOP. Join me in Lecture 16.02, the 4 OOP principles. See you there. Welcome back. To grasp object-oriented programming, we need to understand its 4 foundational pillars. These principles guide how we design our software, making it robust, flexible, and scalable. They are encapsulation, abstraction, inheritance, and polymorphism. 1. Encapsulation. This principle is about bundling data and the methods that operate on that data into a single unit, which is typically a class. It also means restricting direct access to some of the object's components. Think of a smartphone. All its complex components and operations are packaged inside a single case, and you only interact with it through predefined buttons and the screen. Encapsulation protects the data from accidental outside modification. 2. Abstraction. Abstraction focuses on showing only essential information to the user and hiding the complex implementation details. When you drive a car, you use the steering wheel and pedals. You don't need to know the detailed mechanics of the engine to drive. Abstraction simplifies the interface and reduces complexity for the user. 3. Inheritance. This is the mechanism that allows a new class, called a child or subclass, to inherit the attributes and methods of an existing class, called a parent or superclass. For example, a car class and a truck class can both inherit common properties like color and speed from a general vehicle class. This promotes code reuse and establishes a logical hierarchy. 4. Polymorphism. The term means many forms. It refers to the ability of an object to take on many forms, or more practically, the ability of different objects to respond differently to the same method call. If both a dog object and a cat object have a make_sound method, calling make_sound on the dog produces a bark, while calling it on the cat produces a meow. The method is the same, but the behavior is different. To summarize, these 4 principles are the philosophical groundwork of OOP. Our next lecture 16.03. Classes and Objects. See you there. Welcome back. Before we start writing any OOP code, we must define the 2 fundamental concepts, classes and objects. These terms are often used interchangeably, but they represent very distinct parts of the programming process. Understanding their relationship is crucial. 1. What is a class? A class is essentially a blueprint, a template, or a definition for creating objects. It doesn't actually exist in memory. It just defines what properties or attributes and what behaviors or methods an object of that class will have. For example, a dog class defines that all dogs have a color, attribute, and a bark method. 2. What is an object? An object is an instance of a class. It's a real, concrete entity that exists in memory. It holds the actual data specified by the class template. If the dog class is the blueprint, then Fido, a specific dog with brown color, is an object. You can create many different objects from a single class, like Fido, Max, and Daisy, each with its own unique attribute values. 3. Instantiation. Creating an object. The process of creating an object from a class is called instantiation. In Python, you typically instantiate an object by calling the class name as if it were a function, like my_dog equals dog with parentheses. My_dog is now an object or instance of the dog class. The class is the abstract template, and the object is the concrete variable you use in your code. To summarize, class defines, object realizes. Our next lecture 16.04. Create first class. See you there. Welcome back. Now that we understand the concepts of classes and objects, let's start writing our first object-oriented code in Python. We will define a simple class to represent a student, and then create individual student objects from this template. 1. Defining the class. To define a class in Python, we use the class keyword followed by the class name, which should always start with a capital letter and a colon. For our simple example, we use the pass keyword inside the class body. This means the class currently has no attributes or methods defined, but it is a valid blueprint that can be instantiated. 2. Creating objects. We create two objects, S1 and S2, by calling the class name followed by parentheses. This process is called instantiation. Both S1 and S2 are now independent instances of the student class. Printing the type of S1 confirms it is a student object. 3. Assigning and accessing attributes. Since we didn't define any attributes in the class, we can dynamically add them to the individual objects. We use the dot notation, such as S1 name, to set and retrieve attributes. Notice that S1 and S2 have completely independent name and ID attributes, demonstrating that they are distinct objects in memory. To summarize, we've created our first class and objects. However, dynamically assigning attributes like this is messy. We need a way to initialize the objects with data immediately upon creation. This is where constructors come in. Constructors allow us to pass data to an object when we create it, ensuring objects are properly initialized. Our next lecture 16, D05. Use parameterized constructor. See you there. Welcome back. In the previous lecture, we manually assigned attributes to our objects, which is cumbersome and prone to errors. The Pythonic solution is to use a constructor, a special method called automatically when an object is instantiated. We will use a parameterized constructor to initialize our objects with values immediately upon creation. 1. Defining the constructor. In Python, the constructor is defined using the special method name def_init_. This method takes at least one argument, self. Self is a reference to the instance of the class itself, and it must be the first parameter. Any other parameters like name and student_ID are the data we want to pass in. Inside the method, we use self to assign the incoming data to the object's attributes. 2. Instantiating with parameters. Now, when we create an object, we pass the values for name and student_ID directly inside the parentheses. The S1 equals student with parameters call automatically executes the $init_" method, assigning Alice and 101 to the object's name and ID attributes respectively. This eliminates the need for manual assignment after creation and ensures the object is correctly initialized. 3. The role of self. Remember that self is not a keyword but a convention. It represents the instance on which the method is being called. It is necessary to use self inside the class to access or modify attributes belonging to the specific object, such as self name equals name. The self parameter is automatically passed by Python when you call the method. To summarize, the parameterized constructor is the standard way to create OOP objects with meaningful initial data. Our student objects now have data, but they can't do anything yet. Next, we will learn how to define an instance method to add behavior to our objects. Our next lecture 16:06. Define an instance method. See you there.
Welcome back. Our student objects currently hold data thanks to the constructor, but they can't perform any actions. In object-oriented programming, instance methods are the functions defined within a class that give objects their behavior. They allow the object to manipulate its own internal data. 1. Defining an instance method. An instance method looks exactly like a normal function defined within the class. Crucially, like the constructor, it must take self as its first parameter. This self parameter is how the method gains access to the specific object's attributes, like self.name and self.id. We define a method called get_info that returns a formatted string containing the object's data. 2. Calling the instance method. To call the method, we use the object's reference s1, followed by the dot notation s1.get_info with parentheses. When you call it this way, Python automatically passes the s1 object as the self parameter to the method. The method then executes, uses the object's own data, and returns the result. 3. The difference between objects. If we create a second object, s2, and call the same get_info method, it will operate only on s2's data, returning Bob and 102. This highlights the core of OOP. The method is defined once in the class, but its behavior depends entirely on the unique data stored within the object that calls it. To summarize, we've now given our objects both data and behavior. However, accessing attributes directly, like s1.name equals something, breaks the principle of encapsulation. Our next lecture 16.07. Create getter and setter methods. See you there. Welcome back. In previous lectures, we accessed object data directly, like s1.name equals something. While Python allows this, it violates the OOP principle of encapsulation, which states that internal data should be protected. The standard solution is to use getter and setter methods to control how attributes are read and modified. 1. Defining the setter. A setter, or mutator, is a method used to modify an object's attribute. We define set_id, which takes the self-reference and the new _id value. The key advantage is that we can now add validation logic. Here we check if the new _id is a positive integer before actually assigning it to self.id. This protects our object's data integrity. 2. Defining the getter. A getter, or accessor, is a method used to retrieve an object's attribute. We define get_name. This method simply returns self.name. We can also use the getter to perform operations on the data before returning it, such as converting the name to uppercase, providing a layer of abstraction. 3. Using the getter and setter. We create a student object, s1. When we call s1.get_name, we receive the uppercase version demonstrating abstraction. When we call s1.set_id with 999, the assignment is successful. However, when we try to pass a negative number, the validation fails, and the ID remains unchanged. This shows how encapsulation protects the object's state. To summarize, getters and setters are vital for writing robust OOP code. They prevent direct attribute access and allow control over data. Our next lecture 16.08. Define instance methods. See you there. Welcome back. We've learned that instance methods define an object's behavior. In this lecture, we will define more instance methods in our student class to showcase how they can perform calculations, update an object's internal state, and take additional parameters. 1. Defining a calculation method. Instance methods can take parameters beyond self. We define calculate_fee, which takes course_credits. Inside the method, we perform a calculation, multiplying the given credits by a constant rate. Note that this method uses object data indirectly, but primarily relies on the external parameter to return a result. 2. Defining a state modification method. Instance methods are also used to change the object's internal state. We define celebrate_birthday. This method accesses self.age, increments it by 1, and then prints a message. This is a crucial concept. Methods are the gatekeepers that safely modify the object's internal attributes, which is the core of encapsulation. 3. Testing the methods. We create S1 with an initial age of 20. First, we call calculate_fee passing in 12 credits, and it correctly returns 600. Then, we call celebrate_birthday. Notice that after this call, the internal state S1.age has permanently changed from 20 to 21. To summarize, instance methods are essential for building functional objects. We have now learned constructors and instance methods. Constructors build and initialize an object, while methods define its capabilities. Understanding the distinction is vital for writing clean OP code. Join me in Lecture 16.09, Methods versus Constructors. See you there. Welcome back. By now, you've worked with both the __init___ constructor and various instance methods. Although both are defined using def inside a class, their purpose, naming conventions, and execution timing are fundamentally different. Understanding this distinction is key to writing clean and correct object-oriented code. 1. Purpose and execution time. The primary purpose of the constructor is to initialize the object's state, giving it initial values. It runs automatically and only once, when you instantiate the object using student or similar. In contrast, an instance method defines the object's behavior, what it can do. It can be called any number of times manually after the object has been created. 2. Key differences in a table. Here is a table summarizing the key distinctions. Constructors always have the fixed name $_init$_. Methods have user-defined names, like get_info. Constructors are called automatically, while methods are called manually using dot notation. Constructors run only once, while methods can run multiple times. Finally, constructors implicitly return the new object, while methods can return any calculated value or nothing at all. 3. Practical example. In this example, when we execute S1 equals student Eve, the constructor runs immediately to set the name. The method introduced is not called until we explicitly tell the object to do so with s1.introduce. To summarize, the constructor is for setting up the object. Methods are for using the object. This completes our discussion on object-specific methods. Our next lecture 16.10, Define Static Field. See you there. Welcome back. Until now, every attribute we've defined, like the student's name, has been unique to each object. These are called instance variables. But what if we need a piece of data that is shared across all objects of the class? For this, we use a static field, also known as a class variable in Python. 1. Defining the static field. A static field is defined outside of any method, directly within the class body. Here, we define school_name equals Tech University. This variable belongs to the class itself, not any single object. Every student object we create will share this exact same value. The variable name inside the constructor remains an instance variable, unique to each object. 2. Accessing static fields. You can access a static field using either the object, like s1.school_name, or the class name, like student.school_name. Since this data belongs to the class, accessing it directly through the class name is the clear and recommended practice, making it obvious that you are dealing with shared data. 3. Static versus instance variables. When we change the static field using the class name, we see that the change is immediately reflected in all existing objects, S1 and S2. This confirms that they are sharing the exact same piece of memory. In contrast, changing S1.name would only affect S1, leaving S2.name unchanged. To summarize, static fields are used for shared data, like constants or properties relevant to the class as a whole. Next, lecture 16.11. Count the number of objects. See you there. Welcome back. Okay, today we have a practical use for a static field is to keep a running count of how many objects have been created from a particular class. Since the static field is shared by all objects, it acts as a global counter for the entire class. Let's implement this feature in our student class. 1. Initializing the counter. First, we define the static field, object_count, directly in the class body and initialize it to 0. This variable belongs to the class. Next, we need to modify the constructor, the double_init method, to increment this counter every time a new object is created. 2. Incrementing the counter. Inside the constructor, after initializing the instance variables, we increment the static field. Because object_count belongs to the class, we must access it using the class name student.object_count plus equals 1. We also define a simple get_count method to retrieve the total count easily. 3. Testing the counter. As we create 3 separate objects S1, S2, and S3, the constructor runs 3 times. Each time it runs, it increments the shared static field. When we finally print the student.object_count, the output is 3. We can also confirm this by calling the get_count method on any of the objects, as they all share the same counter value. To summarize, we have implemented a shared class counter, which is a key concept in OOP. Our next lecture 16.12. Create an inner class. See you there. Welcome back. We are now moving into more advanced OOP structures. Sometimes, a class is so closely related to another class that it only makes sense to define it inside the outer class. This nested definition is called an inner class. 1. Why use an inner class? Inner classes are used primarily for logical grouping. If a class, like address or engine, is tightly coupled and specific to only one other class, like person or car, it's best to nest it. This improves code organization and readability by keeping related components together. 2. Defining the inner class. We define the laptop class directly inside the student class. The laptop class is completely normal with its own constructor and method. This structure suggests that a laptop is conceptually part of a student record, though technically, the 2 classes remain independent until we link them via instantiation. 3. Accessing and instantiating. To instantiate the inner class laptop from outside the student class, we must use the dot notation, student, laptop, followed by the parentheses and arguments. This creates a separate laptop object, which we store in the laptop_obj variable. We can then call its method show_specs. For linking inner object to outer object. There is a approach is to instantiate the inner class inside the outer class's constructor. The outer constructor takes all necessary parameters and creates the inner object, storing it as an attribute, self.laptop. When calling the constructor inside the outer class, we use self.laptop. To summarize, inner classes help organize related components. This concludes our dedicated coverage of Python's class features. Garbage collection is Python's automatic memory management system that reclaims space used by defunct objects. Join me in Lecture 16.13, Garbage Collection. See you there. Welcome back. As we create objects in Python, we allocate memory. But what happens to that memory when an object is no longer needed? Unlike languages like C, Python handles this automatically using a process called garbage collection. This lecture introduces this fundamental behind-the-scenes memory management system. 1. What is garbage collection? Garbage collection, or GC, is Python's automatic way of reclaiming memory used by objects that are no longer accessible or in use by the program. An object that is no longer referenced is considered garbage. GC sweeps up this garbage, returning the memory space to the system so it can be used for new objects. 2. Python's primary GC mechanism, reference counting. Python's core garbage collection technique is reference counting. Every object in Python has a reference count, which tracks the number of pointers or variables currently pointing to that object. When an object is created, its count is 1. When a variable is assigned to it, the count increases. When a variable goes out of scope or is set to none, the count decreases. 3. How reference counting triggers deletion. Let's look at a quick example. When we define a equals list 10, 20, the reference count is 1. When we set b equals a, the count increases to 2. When a is set to none, the count drops to 1. When b is set to none, the count drops to 0. At this precise moment, the object is considered unreachable, and the Python runtime immediately destroys the object and frees the memory. To summarize, reference counting makes memory management very efficient in most scenarios. However, sometimes we need more control. Our next lecture 16.14, GC methods. See you there. Welcome back. While Python's reference counting is efficient, it has a limitation. It cannot deal with circular references, where two or more objects refer to each other. To handle these rare but important cases, Python uses a secondary generational garbage collector, which we can interact with using the standard library GC module. 1. Importing and enabling GC. To use the garbage collector's methods, we first need to import GC. By default, garbage collection is enabled. You can check its status using gc.isEnabled, while you can manually disable or enable it. 2. Forcing garbage collection. The method gc.collect manually triggers a collection run immediately. It forces Python to look for unreachable objects, primarily those involved in circular references. This method returns the number of objects successfully collected. You may use this function for debugging memory issues or for performance optimization in resource-intensive sections of your code. 3. Inspecting reference count. While not directly in the GC module, The sys.getRefCount function is crucial for understanding how reference counting works. It returns the current number of references to an object. Note that it will always show a count 1 higher than expected, because passing the object to getRefCount temporarily adds 1 reference itself. To summarize, Python's garbage collector usually runs automatically, but the GC module provides manual controls and inspection tools. Before an object is collected, there's one last chance to perform cleanup operations. This is done using a destructor which runs just before the object is destroyed. The destructor, defined by the __del__ method, is the final method called on an object before it is fully destroyed, making it ideal for final cleanup tasks. Join me in Lecture 16.15. Use Destructor. See you there. Welcome back. We've discussed the constructor, which is called when an object is created. Python also provides a mechanism for performing final actions just before an object is destroyed and its memory is reclaimed by the garbage collector. This mechanism is called the destructor, defined by the special method __del__. 1. Defining the destructor. The destructor is defined using the special method name def__del__. It takes only this self argument. We use a class called ResourceHandler to illustrate. In the constructor, we open a file which is a system resource. In the destructor, we safely close that file using self.file.close. This is the place for cleanup tasks like closing database connections or releasing external resources. 2. When the destructor executes, we create an object R1, and the constructor runs immediately. Unlike a regular method, you almost never call the destructor manually. It is automatically called by Python when the object's reference count drops to 0. In this case, we manually use the del keyword to remove the reference R1, causing the object to be garbage collected, and the destructor to run, printing file closed. Object destroyed. 3. The automatic nature of deletion. We can also see the destructor run automatically. Inside the function func, the object R2 is created. When the function finishes executing, the local variable R2 goes out of scope. Its reference count drops to 0, and the destructor runs automatically without the need for the del keyword. To summarize, the destructor gives us one last chance to clean up system resources. With this knowledge, we conclude our learning about individual OP concepts. Okay, our next lecture 16.16. Patient Clinicals Use Case. See you there. Welcome to the final lecture of the OP section. We've learned many individual concepts: classes, objects, constructors, methods, and static fields. Now, let's bring them together to build a practical use case, modeling patient clinicals. 1. Defining the patient class. We start with the patient class. We immediately define a static field, patient_count, initialize to 0, and increment it within the parameterized constructor. The constructor also initializes instance variables for name, weight, and height. This sets up the data and the object counter. 2. Adding instance methods. We add 3 instance methods, all taking self. First, calculate_BMI is a calculation method that uses self.weight and self.height to return the BMI value. Second, update_weight modifies the internal state of the object. Third, display_report aggregates information, internally calling calculate_BMI to generate a comprehensive output. 3. Testing the use case. We instantiate two patient objects, P1 and P2. The static counter correctly shows 2. We call P1.display_report, which shows the initial BMI. Then we call the state modification method, update_weight, which changes P1's internal weight. Finally, calling display_report again shows the updated, higher BMI. This demonstrates the life cycle of an object, from creation and initialization to state modification and behavior execution. To summarize, congratulations! You've built your first end-to-end OP model, applying the fundamental concepts we've learned. Okay, we are going to the next section, Encapsulation, next lecture 17.01. Introduction. See you there. Welcome to the start of a new module, focusing on the 4 pillars of object-oriented programming, beginning with encapsulation. You've already used techniques that support it, like getters and setters, but now we'll formally define the concept and explore Python's unique way of implementing it. 1. Definition of encapsulation. Encapsulation is the mechanism that binds data, attributes, and the method's behaviors that operate on that data together into a single unit, which is the object. More importantly, it hides the internal, sensitive details of the object from the outside world. Think of it as putting both the data and the methods into a protective shell or capsule. 2. The importance of data hiding. Data hiding prevents external code from directly accessing and accidentally corrupting an object's internal state. For instance, if a student object has a GPA attribute, we don't want external code to set the GPA to a negative number or a letter. By hiding the data and forcing access through methods, we can add validation logic, ensuring the object always remains in a valid state. 3. Encapsulation in Python. Unlike many other languages, Python does not have strict keywords like private or public. By default, all attributes are publicly accessible. The example shows a car object created with speed 50, but external code can directly set the speed to -100, which is logically impossible. To prevent this, Python relies on a concept called name mangling to semi-enforce privacy, combined with programming conventions. To summarize, encapsulation is about control and data integrity. Since Python lacks strict privacy controls, we rely on special syntax. Our next lecture 17.02, Private Fields and Name Mangling. See you there. Welcome back. We established that Python does not have strict private keywords. Instead, it offers a mechanism called name mangling to make attributes harder to access externally, thereby supporting encapsulation. This mechanism applies to fields that are intended to be private. 1. Defining private fields. To designate an attribute as private, we prefix its name with double underscores, like self_balance. This is a convention, but it also triggers the name mangling feature. When Python sees this field, it doesn't store it as double_balance. It stores it under a modified name. 2. What is name mangling? Name mangling is the automatic renaming of an attribute by the Python interpreter to prevent accidental overwriting or direct access from outside the class. When you define double underscore balance inside the class bank account, Python secretly changes its name to something like underscore bank account underscore 3. Testing name mangling. We create an object ACC. If we try to access acc.double underscore balance directly, Python throws an error because that name simply doesn't exist on the object. However, if we know the mangled name, which is underscore bank account underscore balance, we can still access it. This shows that name mangling is a strong hint for private data, but it is not a true access restriction. It is merely a renaming trick. 4. The proper way to access. The intended and encapsulated way to interact with double underscore balance is through the method defined in the class get underscore balance. Since this method is defined inside the bank account class, it can use the original field name, self double underscore balance, and Python's interpreter handles the mangling correctly internally. To summarize, name mangling provides a tool to strongly signal that a field should not be accessed directly. Now that we understand how to hide data, the next logical step is to properly implement encapsulation using the getters and setters that we learned earlier. Our next lecture 17.03, Implementing Encapsulation. See you there. Welcome back. We've learned the theory of encapsulation and Python's mechanism for achieving private fields through name mangling. Now, let's put it together to implement the encapsulation principle, using getters and setters to control and validate access to our data. 1. Private field and constructor. We define the intended private field, double underscore price, which is zeroed out as a class variable. In the constructor, instead of assigning the initial price directly to the private field, we call the setter method set underscore price. This ensures that even the initial value passed during object creation is validated. 2. Defining the setter. The setter method set underscore price is the control gate for modifying the price. Here, we implement crucial validation logic. The price must be greater than or equal to 0. If the validation passes, we safely assign the value to the private field, self double underscore price. If it fails, we output an error message, and the internal state remains unchanged. 3. Defining the getter. The getter method, get underscore price, controls read access. It simply returns the value of the private field. Although it's simple here, in a real application, you might use the getter to apply formatting or maybe add tags before exposing the value to the user, providing a layer of abstraction. 4. Testing the encapsulation. We create a product, P1, with price 50. We read the price using the getter. When we call set underscore price with a valid value like 75.5, it succeeds. However, when we try to call it with a negative price, the setter's validation logic catches the error, prints the message, and most importantly, the object's internal state remains at 75.5. This is the goal of encapsulation, protecting data integrity. To summarize, you now know how to effectively implement encapsulation in Python, thereby controlling the quality and integrity of the data stored in your objects. This concludes the first pillar of OOP. Inheritance allows a new class to acquire properties and behaviors from a parent class, avoiding redundant code. Join me in Lecture 18.01, Inheritance. See you there. Welcome to a new module focused on the second pillar of object-oriented programming, inheritance. Inheritance is a powerful concept that allows us to define a new class based on an existing class, reusing its properties and behaviors. This is a crucial tool for achieving code reusability and establishing natural relationships between classes. 1. What is inheritance? Inheritance is a relationship. For example, a dog is an animal, and a savings account is a bank account. When a new class called the child class or subclass inherits from an existing class called the parent class or superclass, the child automatically gains all the attributes and methods of the parent. 2. Benefits of inheritance. The main benefit is code reusability. Instead of copying the common attributes and methods, like a deposit function in every type of bank account, we define them once in the general bank account parent class, and all specialized account types inherit them. This reduces redundancy and makes maintenance much easier. 3. Basic inheritance syntax in Python. The syntax is very simple. To make the dog class inherit from animal, you place the parent class name, animal, inside the parentheses after the child class name, class dog parentheses animal. By doing this, the dog class instantly inherits the eat method from animal, even though we only define the specialized bark method in dog. To summarize, inheritance is foundational to OP design. Our next lecture 18.02, Inheritance in Action. See you there.
Welcome back. In the last section, we learned the basic syntax for inheritance. Now, let's see this powerful principle in action. We will use the animal and dog example to demonstrate that a child class object can execute methods defined in both the parent class and itself. 1. Reviewing the parent and child classes. Let's use a common example, vehicle and car. The vehicle class, our parent, defines the common behavior start_engine. The car class, our child, inherits from vehicle and adds its specialized behavior, drive. Note that the car class definition is very clean because it doesn't need to redefine start_engine. 2. Creating the child object. When we instantiate a car object, my_car, it contains all the attributes and methods of car plus all the attributes and methods of vehicle. We can easily call the child's own specialized method, my_car.drive. 3. Accessing inherited functionality. Now for the core of inheritance. We can call the parent's method, start_engine, directly on the my_car object, even though that method is not physically written in the car class. Python knows to look up the hierarchy to the vehicle class, find the method there, and execute it. This is the essence of code reuse. To summarize, inheritance ensures that common functionalities are defined once and automatically available to all subclasses. Our next lecture 18.03, Inheriting Functionality. See you there. Welcome back. So far, we've focused on inheriting methods. However, inheritance also extends to data. A child class inherits both instance variables and static fields from its parent class, allowing objects to share and reuse data definitions. 1. Inheriting static fields. Our parent class, vehicle, defines a static field, will_count equals 4. Since static fields belong to the class definition itself, any subclass, like truck, automatically inherits them. The truck class does not need to redefine this shared data. 2. Accessing inherited static fields. When we create a truck object, we can access the wheel_count directly from the object or the truck class name. Python traverses the hierarchy, finds the field in vehicle, and returns the value. 3. Inheriting instance variables. Instance variables like name in the animal parent class are initialized inside the parent's constructor. When a child class, like cat, defines its own constructor, it overrides the parent's constructor. This means the parent's constructor is no longer called automatically, and the instance variable name is never initialized. We will fix this initialization issue in the next section using the super keyword. To summarize, inheritance is more than just methods. It includes data. However, for instance variables, we face a conflict when the child defines its own constructor. Method overriding allows a child class to provide a specific implementation for a method that is already provided by its parent class. Join me in Lecture 18.04, Overriding. See you there. Welcome back. While inheritance promotes code reuse, sometimes the general method inherited from the parent class isn't quite right for the child class. In such cases, the child class can provide its own specialized implementation of that method. This process is called method overriding. 1. Definition of overriding. Method overriding means creating a method in the child class with the exact same name and signature as a method in the parent class. When the method is called on the child object, the child's version is executed instead of the parent's inherited version. This allows us to specialize general behavior. 2. Overriding in action. We have a parent class, vehicle, with a general move method. The child class, car, defines its own move method with the exact same name. This new definition overrides the inherited one. 3. The child-first search rule. When we call c.move on the car object, Python follows a child-first search rule. It first checks the car class for a move method. Since it finds one there, it executes the specialized car.move and completely ignores the parent's version. This is the core mechanism of overriding. 4. Overriding the constructor. As we saw in the previous section, the constructor $_init__ is also a method. If the child class defines its own constructor, it overrides the parent's constructor. This means that all the parent's instance variables are not automatically initialized, which can cause errors. We need a way to explicitly call the parent's constructor from the child's constructor to ensure proper initialization. To summarize, overriding allows specialization while keeping the inheritance structure. The super keyword is used to access methods of the immediate parent class, may be used to call the parent's constructor. Join me in Lecture 18.05, Using Super. See you there. Welcome back. In the previous section, we noted that when a child class defines its own constructor, it overrides the parent's constructor, which prevents the initialization of inherited instance variables. The solution to this problem is the built-in function super. 1. What is the super function? The super function provides a way to access methods and properties of the parent class, even if they have been overridden in the child class. Its most common use is within the child's constructor to call the parent's constructor and ensure all inherited instance variables are properly initialized. 2. Calling the parent constructor. Here, the person class initializes name and age. The employee class needs its own constructor because it takes an extra argument, salary, to ensure name and age are initialized correctly. The employee constructor first calls super.double_init_name, age. This delegates the initialization of common attributes to the parent, and then the child handles its own specific attributes like salary. 3. Testing the initialization. When we instantiate the employee object EMP, both the parents and the child's constructors are executed in sequence, thanks to super. We can now access all attributes, name and age initialized by the parent, and salary initialized by the child. The object is completely and correctly initialized. 4. Calling overridden methods. The super function can also be used to call any other overridden method, not just the constructor. If the dog class overrides the animal.speak method, but still wants to execute the parent's general logic before or after its own specialized code, it can call super.speak inside its own speak method. This allows for both specialization and reuse. To summarize, super is your bridge to the parent class, ensuring that you reuse and initialize inherited components correctly. This concludes our module on inheritance. Polymorphism, meaning many forms, allows objects of different classes to be treated as objects of a common type, often facilitated by duck typing. Join me in Lecture 19.01, Introduction. See you there. Welcome to the third pillar of object-oriented programming, polymorphism. This may be the most powerful and often confusing concept, but it is essential for writing flexible, extensible code in any language. The word polymorphism literally means many forms. 1. Definition of polymorphism. In OOP, polymorphism is the ability of an object, variable, or function to take on multiple forms or types. Specifically, it allows a single interface to be used for different underlying data types. This means different objects can respond to the same message or method call in their own, distinct ways. 2. Simple example, the plus operator. The simplest form of polymorphism you've already used is the addition operator, plus. When used with numbers, it performs addition. But when used with strings, it performs concatenation. The plus operator has many forms and its behavior depends on the type of data it operates on. This is an example of operator overloading, which we maybe will see soon. 3. Types of polymorphism. While polymorphism is a broad term, we will focus on 3 main types within Python. First, duck typing, which is Python's dynamic core concept. Second, operator overloading, which we just mentioned. And third, runtime polymorphism, achieved through method overriding and inheritance, which you already have some experience with. 4. Introduction to duck typing. Python's flexibility means we don't care about the object's formal class type. We only care about whether it can perform the action we need. The famous saying is, if it walks like a duck and it quacks like a duck, then it must be a duck. This principle is known as duck typing, and it is the foundation of polymorphism in Python. To summarize, polymorphism is essential for interchangeable components. Duck typing means if it has the method I need, I can use it, regardless of its class hierarchy. Join me in Lecture 19.02, Duck Typing. See you there. Welcome back. In Python, the concept of duck typing is central to polymorphism. It means that the type or class of an object is less important than the methods it defines. This flexible approach allows you to write generic code that can work with any object, provided that object has the required behavior. 1. The duck typing principle. The principle states, if it walks like a duck and it quacks like a duck, then it must be a duck. In programming terms, if an object has the method we are looking for, we treat it as if it belongs to the expected type. We don't need to check its inheritance hierarchy or its formal type. We just check for the method. 2. Defining unrelated classes. Let's define 3 completely unrelated classes: cat, dog, and politician. They do not share a common parent class. However, all 3 classes implement a method with the same name: speak. 3. Creating a generic function. Now we create a generic function, make_it_sp, that accepts any object we call entity. Inside, it simply calls entity.speak. This function does not care if entity is a cat, a dog, or a politician. It only cares that the object has a speak method. 4. Testing duck typing. We create objects of all 3 classes and pass them one by one to the same generic function. Each object executes its own specialized speak method. This demonstrates polymorphism via duck typing. The function treats all 3 objects the same way because they all quack with a speak method, regardless of their actual class type. To summarize, duck typing is Python's way of encouraging flexible code design. Our next lecture 19.03, Duck Typing for Dependency Injection. See you there. Welcome back. We've seen how duck typing allows different objects to be used interchangeably. This principle is fundamental to a powerful design technique called dependency injection, often shortened to DI. This technique is used extensively in large frameworks to manage complexity and improve testability. 1. What is dependency injection? Dependency injection is a design pattern where an object receives the other objects it depends on. Instead of creating its own dependencies internally, these dependencies are injected, typically through the constructor or a method parameter. This drastically reduces the coupling between components. 2. Defining interchangeable components. We define 2 separate classes, email service and SMS service. Critically, both classes implement the same interface method, send. Since they both send a message, duck typing considers them interchangeable for any function that needs a send capability. 3. The client class. The notification manager is our client class. Notice that in its constructor, it accepts a service object as a dependency. It doesn't check if that service is an email or SMS object. It simply stores it and later calls service.send. The manager is decoupled. Its logic never changes, regardless of the dependency type. 4. Swapping dependencies. This is where the power of duck typing shines. We create an email_manager, injecting the email service. The message is sent via email. Then, we create an SMS_manager, injecting the SMS service. The exact same notify_user method is called, but the output changes because the underlying dependency was swapped. The core notification manager code remains untouched. Only the injected dependency changed. To summarize, dependency injection powered by duck typing is key to creating modular, testable, and highly flexible applications. Our next lecture 19.04, Operator Overloading, See you there. Welcome back. Until now, we have used operators like plus or minus with built-in types like integers and strings. But in Python, you can extend this functionality to your own custom objects. This process is called operator overloading. It allows you to define exactly how an operator behaves when applied to your custom classes. 1. What is operator overloading? It is a specific type of polymorphism where different operators have different implementations depending on their arguments. To achieve this in Python, we use special predefined methods known as magic methods or dunder methods because they start and end with double underscores. 2. Common operator mapping. This table shows how Python maps familiar operators to their corresponding dunder methods. For instance, when you use the plus operator between two objects, Python internally tries to call the _add _ method. If we implement these methods in our class, we can define our own custom logic for these operations. 3. Implementing custom addition. Let's create a point class representing coordinates. By implementing the _add _ method, we define that adding 2 points results in a new point object where the x and y values are the sums of the original points. The other parameter refers to the object on the right side of the plus sign. 4. Testing overloaded operators. Now, when we define P1 and P2 and write P1 plus P2, Python automatically calls our custom method. Without this method, Python would throw a type error because it wouldn't know how to add 2-point objects. This makes our custom classes feel like built-in Python types. To summarize, operator overloading is a high-level feature that provides intuitive interfaces for your classes. You may use this to perform coordinate math, combine bank accounts, or merge data structures. In our final lecture on polymorphism, we will explore runtime polymorphism, where the exact method executed is determined while the program is running. Our next lecture 19.05, Runtime Polymorphism. See you there. Welcome to the final section on polymorphism, runtime polymorphism. Unlike duck typing and operator overloading, which are unique to Python, runtime polymorphism is a standard OP concept found in all object-oriented languages. It relies on inheritance and method overriding to determine which version of a method to execute at the moment the program runs. 1. The mechanism inheritance and overriding. Runtime polymorphism is achieved when a parent class defines a general method, and one or more child classes override that method to provide specific implementations. When a generic reference variable points to a specific child object at runtime, the correct specialized method is executed. 2. Setting up the hierarchy. We define a parent class, shape, with a general calculate_area method. The two child classes, circle and rectangle, both inherit from shape and override this method, providing their own specialized area calculations. The shape method is never intended to be run. It's just a placeholder. 3. The polymorphic function. We create a generic function, print_area, which accepts an object named shape. It calls shape.calculate_area without knowing if shape is a circle or a rectangle. The actual version of the calculate_area method executed is decided at runtime based on the object's actual type. 4. Testing runtime behavior. We call the same generic function with two different objects. When we pass circle, the circle.calculate_area is executed. When we pass rect, the rectangle.calculate_area is executed. The method call is polymorphic because its exact behavior changes based on the object's type, and this choice is made by the Python interpreter during execution. To summarize, runtime polymorphism is essential for building flexible systems where specialized objects share a common interface. This concludes the module on polymorphism. Our next lecture 20.01, Abstract Classes and Interfaces. See you there. Welcome to the final pillar of object-oriented programming, abstraction. Abstraction is often considered the most important design principle. It is about simplifying complexity by showing only the necessary features to the user and hiding the complex, internal implementation details. You already practice abstraction every time you use a library function without needing to know how it works internally. 1. Definition of abstraction. Think of a car. You interact with the steering wheel, pedals, and gear selector, the essential interface. You don't need to know how the engine manages fuel injection or piston timing, the complex details. Abstraction separates the interface from the implementation. In Python, the primary goal is to define common interfaces and enforce that subclasses implement them. 2. Abstract classes in Python. Python uses a concept called abstract base classes, or ABCS, to implement abstraction. An abstract class is a class that contains one or more abstract methods. An abstract method is declared but does not contain any implementation. It only defines the required method signature. You cannot create an object directly from an abstract class. You must inherit from it. 3. The role of abstract methods. The purpose of an abstract class is to act as a blueprint or template. It defines a set of methods that all concrete subclasses must implement. For example, a shape abstract class might define an abstract method, calculate_area. Any subclass, like circle or rectangle, is then forced to implement its own specific calculation logic for that method. 4. Interfaces, protocols. While abstract classes can have both abstract and concrete, implemented, methods, an interface is a class where all methods are abstract. It defines a protocol or a contract. If a class implements an interface, it must implement all methods defined in that interface. We already saw this with duck typing, but now we will use Python's tools to formally enforce these contracts. To summarize, abstraction enforces structure and ensures specialized classes adhere to a standard interface. Our next lecture 20.02, Create an Abstract Class. See you there. Welcome back. To formally enforce abstraction in Python, we use the built-in ABC module, which stands for Abstract Base Classes. This module provides the necessary tools to declare a class as abstract and mark certain methods as abstract, thereby creating a contract that all subclasses must fulfill. 1. Defining the abstract base class. First, we import ABC and abstract method from the ABC module. To make a class abstract, it must inherit from ABC. We define a concrete method, load_date, which has an implementation. But we also define an abstract method, process underscore data, decorated with at abstract method. This method has no logic and serves as a placeholder, enforcing that all children must define their own processing logic. 2. Rule 1. Cannot instantiate abstract class. The most fundamental rule of an abstract class is that you cannot create an object directly from it. If you try to instantiate data processor, Python immediately raises a type error. This ensures that the class remains a blueprint and forces developers to use only the complete, implemented subclasses. 3. Creating the concrete subclass. To use the blueprint, we create a concrete subclass, CSV processor, that inherits from data processor. To be a valid instantiable class, CSV processor must implement or override the abstract method process underscore data. 4. Rule 2. Testing the implementation and inheritance. We can successfully create an object of CSV processor. This object has both the inherited load underscore data method from the parent and its own specialized process underscore data method. This shows how abstract classes ensure a common structure while allowing for specialized implementation. To summarize, abstract classes provide a mix of common implementation and enforced specialization. Our next lecture 20.03, Create an Interface. See you there. Welcome back. In the last lecture, we created an abstract class that had both concrete and abstract methods. Today, we focus on a special case, creating an interface. In Python, an interface is simply an abstract base class where every method is abstract. It defines a contract that forces all implementing classes to provide their own specialized functionality. 1. Defining the payment interface. We import the necessary modules and define payment processor as our interface. Notice that both methods, process underscore payment and check underscore status, are decorated with at abstract method and have no implementation body. This class is purely a contract. Any class that uses this interface promises to implement both of these methods. 2. Implementing the interface. We create a concrete implementation, credit card processor, which inherits from our interface. It provides the specific internal logic for process underscore payment and check underscore status. By implementing all abstract methods, this class fulfills the contract and can now be instantiated and used. 3. The enforcement of the contract. If we create another processor like PayPal processor and forget to implement the check underscore status method, Python prevents us from creating an object of that class. The interpreter raises a type error at the moment of instantiation, warning us that the class is still abstract. The interface successfully enforced its contract. To summarize, interfaces define standard behaviors without dictating implementation, which is crucial for building large, flexible systems where many components need to be interchangeable. This completes our discussion of the 4 pillars of OOP. Okay, next we are going to the next section, section 21, our next lecture 21.01. Introduction. See you there. Welcome to the final module of our OOP journey. We've learned the 4 pillars: encapsulation, inheritance, polymorphism, and abstraction. Now, it's time to solidify that knowledge by applying these concepts to a real-world use case, building a simple library management system. 1. Project overview. Our system will manage books. We need 2 main classes. First, the booked class, which holds individual book data, and second, the library class, which manages the collection of books and handles operations like adding, listing, and searching. 2. Applying the 4 OP pillars. How will we use the 4 pillars? We will use encapsulation in the book class by making attributes like title and author protected or private, and providing getter and setter methods to manage access and control data validity. We will use inheritance by creating specialized subclasses of book, like ebook or audiobook, which inherit common properties from book but add their own specific attributes. We will use polymorphism by designing a method, maybe get_details, that behaves differently based on whether it is called on a regular book, an ebook, or an audiobook object. We will use abstraction to define a common interface for all types of books, ensuring they all implement necessary methods, regardless of their specific type. To summarize, this use case will be a powerful final exercise, showing you how to structure complex, object-oriented applications. We'll start immediately by designing the core data class. Join me as we create the book class. Our next lecture, 21.02, Create Book Class. See you there. Welcome back. Our first task in building the library management system is to define the core data structure, the book class. We will use this class to demonstrate encapsulation by making our attributes protected and controlling access to them using property decorators. 1. Defining the protected attributes. We start by initializing the core attributes, title, author, and ISBN. We are using the Python convention of a single underscore prefix, like _title, to mark them as protected. We also add _is_available to track the book status, defaulting to true. This is the data hiding part of encapsulation. 2. Implementing the getter for title. To provide read-only access to the protected _title, we define a method called title and decorate it with @property. This allows external code to access the title as if it were a regular attribute, but internally it calls this method. 3. Implementing the setter for author. For attributes we want to allow modification for, like author, we define a standard getter using @property and then a corresponding setter method using the @author.setter decorator. Crucially, the setter allows us to add validation logic, ensuring the new _author is not empty. This control is the core benefit of encapsulation. 4. Utility method. Finally, we add a simple utility method, get_details, to easily retrieve a formatted string of the book's information. Notice how we use the public properties self.title and self.author when available and directly access the protected _ISBN and _is_available from within the class. To summarize, we have a robust book class ready. Our next lecture, 21.03, Create Library Class. See you there. Welcome back. We've created the book class and ensured its data is encapsulated. Now we'll build the centerpiece of our system, the library class. This class will be responsible for managing a collection of book objects and providing the main functionalities of the system, such as adding and listing books. We will again use encapsulation to protect the book list. 1. Initializing the book collection. The library class starts with a constructor that takes a name. Crucially, we initialize a protected instance variable _book as an empty list. This list holds all our book objects. Marking it as protected enforces that external users should interact with the collection only through the public methods we define, not by directly manipulating the list. 2. Adding books to the collection. The add_book method is our controlled interface for modifying the _books collection. Here, we can add validation, checking if the provided item is actually an instance of the book class. If validation passes, we safely append it to our protected list. This prevents rogue data from corrupting our system. 3. Listing the collection contents. The list_books method provides a clean, abstract way to view the contents. This method internally iterates over the protected _books list and uses the get_details method we defined in the book class. This is an example of strong cooperation between our encapsulated classes. 4. Method for borrowing. We define a placeholder method, borrow_book. The user only needs to know the interface. Pass the title and the system handles the complexity of searching, checking availability, and updating the book status. The implementation details are hidden, perfectly illustrating abstraction, which we maybe will implement later. To summarize, we now have two robust, encapsulated classes, book and library. Our next lecture 21.04, test. See you there. Welcome back. Before moving on to inheritance, we need to ensure our foundational classes, book and library, are working correctly. In this lecture, we will test the encapsulation we built into the book class and verify the core functionality of the library class. 1. Creating library and book objects. Let's start by creating an instance of our library called my_library and two instances of our book class. These objects are now ready to be managed by the system we built. 2. Testing encapsulation. We test the encapsulated access. When we print book1.title, the property getter is automatically called, giving us the value. When we update the author, the property setter is called, which runs our validation logic, successfully updating the protected _author attribute. If we attempted to set an empty string, the setter would raise an error, proving our data control works. 3. Testing library functionality. We add our valid book objects to the library. The add_book method runs successfully. More importantly, we test the encapsulation logic in add_book by attempting to add an integer. The method correctly detects that it's not a book object and rejects it, preventing corruption of the _books list. 4. Listing the final collection. Finally, we call my_library.list_books. This method accesses the protected list, iterates through the valid books, and calls each book's get_details method, presenting a clean output. Our foundational design, based on encapsulation, is now fully verified. To summarize, our core system is stable. Our next lecture 21.05, Inheritance and Polymorphism in Action. See you there. Welcome back for the final lecture of our library management use case. We've established a stable foundation using encapsulation. Now, we will introduce inheritance to create specialized book types and use polymorphism to treat them all uniformly within our system. 1. Defining the ebook subclass. We create the ebook class, which inherits from book. In its constructor, it accepts an extra attribute, file_format. We use super.double_init_, to initialize the inherited attributes, title, author, and ISBN. This is inheritance in action. Then we demonstrate polymorphism by overriding the get_details method. We call the parent's implementation using super.get_details and simply append the new, specialized detail. 2. Defining the audiobook subclass. We follow the same pattern for audiobook. It inherits common data from book, but adds duration_minutes. It also overrides get_details to include its specific duration information. The inheritance ensures code reuse, and the overriding ensures specialization. 3. Testing polymorphism in the library. We instantiate our specialized books. Now watch how the my_library.add_book method, which was designed only to accept book objects, accepts both the ebook and audiobook. This is possible because of inheritance. They are both considered types of book. 4. Polymorphic output. When we call my_library.list_book, the library iterates over its list. For each book, when it calls the get_details method, it automatically executes the correct, specialized version, whether that's the base book method, the ebook method, or the audiobook method. This is runtime polymorphism, allowing the generic library code to handle diverse, specialized objects seamlessly. To summarize, the library management system demonstrates the practical power of all 4 OOP pillars working together to build flexible, maintainable code. This brings us to the end of the OOP section. Next, we are going to a new section, Section 22, and our next lecture is 22.01. Introduction. See you there. Welcome to a crucial module on building robust applications, exception handling, assertions, and logging. No matter how well you write your code, things will eventually go wrong. A file might be missing, a user might enter unexpected data, or a network connection might drop. This module teaches you how to handle these failures gracefully without crashing your program. 1. The need for error management. When a runtime error occurs, Python raises an exception. If this exception is not caught and dealt with, the program terminates immediately, leaving the user with a confusing traceback message and potentially leaving resources like open files unclosed. Handling exceptions is key to user experience and resource cleanup. 2. The 3 tools of robustness. We will focus on 3 tools: exception handling, logging, and assertions. We use try, except, else, and finally blocks to intercept errors at runtime, prevent crashes, and provide a controlled response, such as retrying an operation or alerting the user. We use the logging module to record events that happen in your application, not just errors, but also warnings, informational messages, and debug data. Logging is crucial for understanding what went wrong in a deployed application. We use assert statements to confirm assumptions about the state of the program, particularly during development. If an assumption is false, the program halts immediately with an assertion error, which helps catch internal logic bugs quickly. To summarize, mastering these techniques separates reliable, production-ready code from simple scripts. Our next lecture, 22.02, Exception Class Hierarchy. See you there. Welcome back. Before we start handling exceptions, we must understand how Python organizes them. Exceptions are organized in a hierarchy, just like classes in OOP, allowing us to catch errors at different levels of generality. 1. The root of all errors, base exception. At the very top of the hierarchy is base exception. All system exit messages and exceptions inherit from this. Generally, you should never catch base exception because it includes events like system exit and keyboard interrupt, which are usually meant to terminate the program. 2. The main branch exception. The most important branch is exception, which inherits from base exception. This is the base class for all non-fatal exceptions, the ones you should usually handle with your try-except blocks. If you write except exception, you catch nearly all common runtime errors. 3. Common runtime exceptions. Many common errors you encounter inherit directly or indirectly from exceptions. Let's look at a few common examples and how they relate. For example, zero division error inherits from arithmetic error. Similarly, trying to access a non-existent dictionary key raises a key error, which inherits from lookup error. Catching the base class, like lookup error, means you can handle both key error and index error with one block. These are very frequent. Value error occurs when an operation receives an argument of the correct type but an inappropriate value, such as converting the string hello to an integer. Type error occurs when an operation is applied to an object of an inappropriate type, like adding a string to an integer. 4. Why the hierarchy matters. Understanding the hierarchy allows for specific error handling. When an exception is raised, Python searches for a matching except block. If it doesn't find a direct match, it looks for an ancestor class in the hierarchy. This means that if you catch lookup error, you automatically catch any specific error that descends from it, like key error or index error. To summarize, knowing the hierarchy allows us to write concise yet comprehensive error handlers. Our next lecture, 22.03, Handling Exceptions. See you there. Welcome back. Now that we know what exceptions are and how they are structured, let's learn the fundamental way to manage them, the try-except block. This structure allows us to wrap dangerous code in a try block and provide recovery logic in the except block. 1. The basic try-except structure. The try block contains the code that could fail. If an exception occurs during execution of the try block, the program immediately stops running the try block and jumps to the corresponding except block. Here, the except zero division error block specifically catches a division by zero error, prints a friendly message, and allows the program to continue execution instead of crashing. 2. Catching multiple specific exceptions. You can chain multiple except blocks to handle different types of exceptions. Python checks them sequentially. If the input is not a valid number, value error is caught. If the input is zero, zero division error is caught. It's best practice to be as specific as possible to provide accurate error handling and feedback. 3. Catching exceptions by type tuple. If you want the same recovery logic for several different exceptions, you may list them in a tuple inside a single except statement. This makes your code cleaner and avoids repetition, though the error message here is less specific. 4. Accessing the exception object. We can capture the actual exception instance using the keyword as. This assigns the error object to a variable, usually eq. This allows us to print the specific error message provided by Python, which is useful for debugging and detailed logging. To summarize, handling exceptions is essential for reliable code. Our next lecture 22.04, using finally. See you there. Welcome back. When dealing with resources like files or network connections, it's crucial to ensure they are properly closed, regardless of whether the main operation succeeded or failed. This is the primary purpose of the finally block in Python's exception handling structure. 1. The role of the finally block. The code inside the finally block is always executed before the try-except statement finishes. This makes it ideal for cleanup tasks, ensuring system integrity and preventing resource leaks. 2. Example, file handling with finally. In this example, we attempt to open a file. If the file is found, the try block executes successfully. If the file is missing, the file not found error is caught. But whether the file is read successfully or the exception is caught, the code in the finally block runs, guaranteeing the file, if opened, is safely closed. This prevents the file from remaining locked by the system. 3. Execution flow demonstration. Let's trace the flow in two scenarios. If the file exists, the order is try block runs completely, then the finally block runs. If the file is missing, the order is try block fails immediately, the except block runs, and then the finally block runs. The cleanup is guaranteed. To summarize, always use finally for resource management. Our next lecture 22.05. Else. See you there. Welcome back. We've covered try, except, and finally. Now let's look at the often overlooked but very useful component, the else block. This block helps you write cleaner code by clearly separating the code that depends on the try block succeeding from the main try logic. 1. The condition for else. The else block is executed only if the try block runs completely without raising any exceptions. This makes it an ideal place for code that processes the successful result of the try block, but does not need exception handling itself. 2. Example, successful calculation. In this example, if the division in the try block succeeds, Python skips the except block and executes the else block, printing the result. This separates the error-prone step, division, from the success processing step, printing the result, making the code easier to read and maintain. 3. Example, handling failure. Now, if we introduce a zero division error, the try block fails. Python immediately jumps to the except block. The else block is completely skipped, confirming that the success-dependent code is never executed when an error occurs. 4. Relationship with finally. It's important to remember that if the else block is present and runs successfully, the finally block runs immediately after it. If an exception is caught, the except block runs and then the finally block runs. The finally block always executes last. To summarize, We've now covered the complete structure. Try except else finally. Our next lecture 22.06. Create and raise custom exceptions. See you there. Welcome back. While Python provides many built-in exceptions like value error or type error, sometimes you need an error type that is specific to your application's logic. In this section, we'll learn how to create and trigger our own custom exceptions, providing clearer feedback to users and developers. 1. Creating the custom exception class. Creating a custom exception is simple. Define a new class that inherits from the base exception class. We call ours insufficient funds error. By inheriting from exception, it becomes a fully recognized exception in the hierarchy. We override the constructor to accept specific data, like the current balance and the attempted amount, and we override the _str_ method to provide a detailed, readable error message. 2. Raising the custom exception. To trigger the custom exception when a business rule is violated here, when the withdrawal amount exceeds the balance, we use the raise keyword followed by an instance of our exception class. When raise is executed, the function immediately stops, and Python begins searching up the call stack for a matching except block. 3. Catching the custom exception. Finally, we use a standard try except block to test the functionality. Because our function violates the rule, it raises insufficient funds error. The except block specifically catches this custom error, and we use the exception object, e, to print the detailed, custom error message we defined earlier. To summarize, custom exceptions make your code much more professional, reliable, and easier for others to debug. Next, we will solidify this concept by working through a few more comprehensive examples of creating and managing custom exceptions in different scenarios. Our next lecture 22.07. More programs custom exceptions. See you there. Welcome back. To solidify our understanding of custom exceptions, we will work through a more comprehensive example using a data processing scenario. This program will require us to define a small hierarchy of custom exceptions to handle different types of data validation errors. 1. Defining an exception hierarchy. It's often helpful to create a base custom exception, like data validation error, that inherits from the main exception. Then we create more specific exceptions that inherit from our base class, such as missing field and invalid value. This structure allows us to catch all data errors generically or handle specific errors individually. 2. Function with multiple validation checks. Our process_record function now uses these exceptions. It checks for a missing name, then a missing age. Crucially, it then checks if the age is a valid positive integer. If any of these business rules are violated, we use the raise keyword to interrupt execution and signal the precise error condition using the appropriate custom exception. 3. Catching the hierarchy. We test two scenarios. In the first example, we catch the specific missing field exception. In a larger try except block, you may catch the generic data validation error to handle all derived errors with a single handler. This flexibility, enabled by the exception hierarchy, is extremely valuable for complex systems. Remember, always catch the most specific exceptions first. To summarize, we've now learned creating, raising, and handling specific custom exceptions. But what happens to the errors we catch? We need a system to record them. Our next lecture 22.08, Logging in Action. See you there. Welcome back. We've learned how to gracefully handle immediate errors using try-except. Now we shift our focus to professional application monitoring, logging. Instead of using simple print statements, the logging module allows us to record events with crucial context, timestamps, and severity levels. 1. Why use logging? Unlike print, logging allows you to control which messages appear based on severity, directs messages to various destinations like files or network servers, and automatically includes metadata such as the timestamp, log level, and the file that generated the event. 2. The 5 log levels. Python defines 5 standard severity levels, from least critical to most critical. Understanding these is essential for configuring your application. The levels are debug, info, warning, error, and critical. Debug logs are for internal deep dives, info logs for normal operations, warning for minor issues, and error or critical for failures. 3. Logging to the console. To get started, we import the logging module. Notice that when we run this code, by default, we only see warning, error, and critical messages. Info and debug messages are silently ignored. This is because the default threshold for Python's logging system is set to warning. 4. Default output format. The basic output format includes the level, the logger name which is root by default, and the message itself. This already gives us more context than a simple print statement. To summarize, we've begun using the logging module and identified the default behavior. Our next lecture 22.09, Logging Configuration. See you there. Welcome back. In the previous section, we saw that Python's logging defaults to the warning level, ignoring debug, and info messages. To make logging truly useful for development, we need to configure it. We do this using the logging.basicconfig function. 1. Setting the log level. By passing level equals logging.debug to basicconfig, we lower the threshold. This tells the logger to process all messages at the debug level and above. Now, when we run the code, the previously hidden debug and info messages appear in the console. 2. Formatting the log output. The default output format is basic. We can customize it using the format argument. To do this, we use specific log record attributes, which are placeholders that Python replaces with actual data, such as the time or the log level. In this example, we define a format string. %AskTime s inserts the time, %LevelName s inserts the severity, and %message s inserts your text. This structure makes logs much easier to read and analyze. 3. Logging to a file. In production, you rarely watch the console. You need logs saved to a file. We achieve this by adding the file name argument. We also set file mode to W to overwrite the file each time the program runs, or to append to the existing file. Once this is set, logs will go to the file and will not appear on the screen. To summarize, Proper configuration turns logging from a simple tool into a powerful monitoring system. Our next lecture 22.10. Log Exceptions. See you there. Welcome back. When your application crashes in production, a simple error message like "File not found" may be not enough. You need the full story, the traceback, which tells you exactly where and why the code failed. Today, we will learn how to configure the logger to capture this vital debugging information automatically. 1. The problem: missing context. If we use a standard logging.error call inside an except block, it only logs the text string we provide. The crucial information, the stack trace showing that line 4 caused a 0 division error, is completely lost. This makes debugging difficult. 2. Solution 1. Using exe_info equals true. To include the traceback, we add the argument exe_info equals true to our logging call. Now, the logger automatically looks up the current exception information and appends the full stack trace to the log message. 3. Solution 2. Using logging.exception. Python provides a shortcut method specifically for this purpose, logging.exception. This method logs a message with the level error and automatically sets exe_info to true. It is the preferred, cleaner way to log errors inside an exception handler. To summarize, always capture tracebacks when logging errors. It turns a mysterious failure into an obvious fix. We have learned exception handling and logging. The final tool in our robustness toolkit is Assertions, a powerful way to perform sanity checks during development. Our next lecture 22.11. Using Assertions. See you there. Welcome to the final section of our module on robust programming. We have covered runtime errors with exceptions and historical logging. Now, we introduce a tool for debugging internal programming logic during development. Assertions. Assertions are sanity checks. They test if an assumption you made about the code state is true. 1. The assert syntax. The assert statement takes a condition and an optional message. If the condition is true, nothing happens, and execution continues. If the condition is false, Python raises an assertion error, immediately stopping the program and displaying the optional message. The failure of an assertion indicates an internal bug that needs fixing, not an expected runtime event. 2. Assertions versus exceptions. This is a critical distinction. Assertions are for programmers and should only check for conditions that should never happen if your logic is correct, such as checking if a variable is not none after an operation guaranteed to return a value. Exceptions are for users and handle expected runtime failures, like a file being missing or bad user input. 3. The dangers of assertions. Assertions can be globally disabled when Python is run with the optimization flag -o. When disabled, Python completely ignores the assertion statement, including any side effects. Therefore, you must never include essential code inside an assertion condition, such as calling a function that performs a critical calculation or I/O. To summarize, use Jassert to catch bugs in your own logic quickly. Okay. You have now learned exception handling, logging, and assertions, the core tools for writing robust Python applications. Okay, we are going to the next section, section 23. Our next lecture is 23.01. Introduction. See you there. Welcome to a new module focused on a fundamental programming skill, file input and output, or file I/O. Up until now, our data only existed in memory while the program was running. If the program stopped, the data vanished. This module teaches you how to save and load data persistently to your hard drive. 1. Why persistence matters. Maybe almost every real-world application, from web servers to desktop tools, needs persistence. This means saving state, user settings, game scores, or large datasets so that the information remains available even after the program has terminated or the computer has rebooted. Files are the most basic and universal method for achieving this. 2. The key function, open parenthesis. In Python, all file operations begin with the built-in opened function. This function returns a file object, which acts as a bridge between your program and the physical file on disk. It takes two main arguments, the file name and the mode, which specifies whether you intend to read, write, or append data. 3. File operation modes. There are three primary modes we will focus on for text files. Are for reading, W for writing, and for appending. We must be careful with the W mode, as it will destroy the existing contents of a file if it already exists. 4. The golden rule, always close. After you finish reading or writing, you must call the close method on the file object. Failure to close a file can lead to resource leaks, and, critically, on many systems, data written to a file is only guaranteed to be saved to disk once close is called. To summarize, understanding these basics sets the stage for file mastery. Our next lecture, 23.02, Write string to a file. See you there. Welcome back. Let's get hands-on with file I/O by performing the simplest operation, writing a single string to a file. We will use the write method in the W or write mode. 1. Using the open parenthesis and write parenthesis methods. First, we call open with the file name greeting.txt and the mode W to create the file object file_out. Then we use the write method on this object, passing the string we want to save. The write method returns the number of characters, or bytes, it successfully wrote. Finally, and most importantly, we call close to ensure the data is flushed from the buffer onto the disk. 2. Overwriting danger of W mode. Remember the critical feature of the W mode. If the file greeting.txt already exists, opening it in W mode will completely erase or truncate all its previous content. We demonstrate this by writing a second, shorter string to the same file. The original content is gone, replaced entirely by new message. 3. The with statement. Relying on manually calling close can be risky, especially if an exception occurs. The preferred, robust way is to use the with statement, which is a context manager. When Python exits the with block, it automatically ensures the file's close method is called, guaranteeing cleanup. This is much safer, and we recommend using it for all I/O operations. To summarize, you can now save simple strings. Our next lecture 23.03, read from a file. See you there. Welcome back. In the previous section, we successfully wrote data to a file. Now, we perform the inverse operation, reading that data back into our Python program. We will use the R, or read, mode and explore 3 different reading methods. 1. Set up the sample file. For demonstration, let's assume we have a file named sample_data.txt containing 3 lines of text. We will use the recommended with statement for all our reading operations to ensure the file is closed correctly. 2. Reading the entire file with read parenthesis. The simplest way is using the read method without arguments. This method reads the entire content of the file from the current file pointer position into a single Python string. If the file is very large, be cautious, as this may consume a lot of memory. 3. Reading line by line with readLine parenthesis. The readLine method reads only the next single line from the file. Each call advances the file pointer. A key detail, the new line character, \n, is included at the end of the return string. We use the representing function here to show you those hidden characters clearly. 4. Reading all lines with readLines parenthesis. Finally, the readLines method reads the entire file, but instead of returning a single string, it returns a list of strings, where each element in the list is one line from the file, including the new line characters. This is often the most convenient way to process structured text data line by line. To summarize, you now know the 3 main ways to pull data out of a file. Our next lecture 23.04, write multiple strings. See you there. Welcome back. In the real world, you rarely write a single fixed string. Instead, you typically deal with collections of data such as a list of usernames or scores. Today, we will explore the best ways to efficiently write multiple strings from a list into a file, ensuring each string appears on its own line. 1. Writing multiple strings via iteration. There is an approach is to iterate over your list using a for loop and call the write method for each item. Crucially, the write method does not automatically add a new line character. Therefore, you must manually concatenate the new line, \n, to the end of each string to ensure they appear on separate lines in the output file. 2. Using the writeLines parenthesis method. Python provides a more direct method called writeLines. This method accepts any iterable, like a list, and writes all of its string elements to the file in one operation. However, just like writeLines does not add new lines automatically. You must ensure that the new line characters are already part of the strings within the list before calling writeLines. 3. Writing lines without new lines. This example serves as a warning. If you call writeLines on a list whose elements do not contain the new line character, all the strings will be joined together in the output file without any separation. Always verify your input list or manually add the new lines during iteration. To summarize, you can now handle bulk writing operations. We've been assuming the file exists for reading, but that's not always true. Our next lecture 23.05. Check if the file exists. See you there. Welcome back. When reading files, a common problem is trying to open a file that doesn't exist, which immediately raises a file not found error. To write robust code, we need to check the status of a file on the disk before we try to open it. We use the built-in OS module for this. 1. The os.path module. To interact with the operating system's file system, we must import the OS module. We then access the path submodule, which provides several useful functions. The most crucial for this task is os.path.exists, parenthesis, which takes a file path or name and returns true or false. We can wrap our entire reading or writing logic inside an if block using this check. 2. Safe reading implementation. This demonstrates the correct pattern for safe file reading. We check if grades.txt exists first. If it does, and only then, we proceed to open it with the with statement in read mode. If it doesn't exist, we skip the open call entirely, preventing the file not found error and allowing the program to continue gracefully. 3. Checking for files versus directories. While os.path.exists is a general check, the os.path module also offers more specific checks. You may use os.path.isFile to ensure the path points to an actual file, not a directory, and os.path.isdir to check specifically for a folder. Using the most specific check for your task is usually best practice. To summarize, always check before reading or modifying, especially in critical applications. We have focused on reading and writing simple text strings so far. Our next lecture 23.06. Pickle. See you there. Welcome back. So far, we've only saved simple strings to files. But what if you have a complex Python object, like a nested list or a custom class instance, and you need to save its entire structure to a file? Manually converting it to text is difficult. The solution is pickling, which is Python's term for serialization. 1. What is pickling? Pickling is the process of converting a Python object hierarchy into a byte stream, which can then be written to a file. This byte stream represents the object state in a way that Python can later use to perfectly reconstruct the original object in memory. 2. Using pickle.dump parenthesis to save objects. We first import the pickle module. When pickling, you must always open the file in binary write mode, specified by WB. The B is crucial because pickle data is raw bytes, not readable text. We call pickle.dump, passing the Python object, our dictionary data underscore object, and the file object. The entire dictionary structure is immediately converted and written to the file. 3. Binary versus text files. If you try to open the resulting user_data.pkl file in a text editor, you would see a stream of unreadable characters. This is the difference between text files, which use readable characters, and binary files, which store raw bytes optimized for machine processing. Pickled files are binary. To summarize, you can now save any list, dictionary, or instance of a custom class instantly. Our next lecture 23.07. Unpickle. See you there. Welcome back. In the previous section, we successfully serialized, or pickled, a complex Python object into a binary file. Today, we complete the cycle by learning how to retrieve that object and restore it perfectly in memory using unpickling. 1. The pickle.load parenthesis function. To unpickle an object, we must first open the file in binary read mode, specified by RB. We then call pickle.load parenthesis, passing the file object. This function reads the entire binary data stream, converts it back into the original Python data type, whether it was a dictionary, a list, or a custom class instance, and returns it. Notice that the type of the loaded object is exactly the same as the original object we saved. 2. Using the loaded object. The most powerful aspect of unpickling is that the loaded variable is a fully functional Python object, complete with its original methods and data structure. Because our saved object was a dictionary, we can immediately access its keys and use Python functions like max parenthesis on its values, just as if we had defined the dictionary within the current script. 3. The security warning. While powerful, pickling comes with a major security risk. The pickle protocol is designed to execute arbitrary code during deserialization. Therefore, you must never unpickle data received from an untrusted source, as it could lead to remote code execution. Only load data that your own application has securely saved. To summarize, pickling and unpickling provide a seamless way to save and restore complex Python objects. We've learned the basics of text and binary I/O. Our next lecture 23.08. More about red. See you there. Welcome back. In our earlier section on reading files, we used methods like read to load everything at once or readlines to get a list. Today, we focus on more efficient and nuanced reading techniques, particularly for large files, by understanding the file cursor and iterative reading. 1. The file cursor. Think of the file object as having a cursor or pointer that tracks your current location in the file. Every time you read from the file, this cursor advances by the amount of data read. For example, if you read 10 characters, the cursor moves 10 positions forward. The next reading operation starts from that new position. 2. Efficient iterative reading. For very large files, the most memory-efficient way to read is to use the file object directly in a for loop. When you iterate over the file object f, Python automatically reads one line at a time, keeping only that line in memory. This is superior to readlines, which loads the entire file into a list at once. We use strip here to remove the trailing new line character, \n. 3. Reading a specific byte count with readEnd parenthesis. You can pass an integer argument, end, to the read method to specify exactly how many characters or bytes to read. This is useful for processing files in fixed-size chunks, common when dealing with structured data formats. Notice how the second read operation starts exactly where the first one left off, thanks to the advancing file cursor. To summarize, you now have tools for reading files of any size efficiently. Our next lecture 23.09. Right? See you there. Welcome back. We've already used the write mode, W, but it's crucial to fully understand its power and its potential dangers before moving on to other modes. This section reinforces the concept of writing to a file and emphasizes the destructive nature of the W mode. 1. The purpose of W mode. The W mode is used when you want to start a file from a blank slate. Its behavior is simple. It opens the specified file and places the file cursor at the very beginning. If the file does not exist, it is automatically created. If it does exist, it is truncated, meaning its entire content is deleted, ready for the new data. 2. Example, file truncation. Let's see the truncation in action. If log.txt already has content, opening it in W mode instantly wipes out that data. When we call write, the new text is placed at the start of the now empty file. This behavior makes W mode suitable for tasks like saving configuration files or generating fresh reports. 3. The write parenthesis method return value. As a quick review, remember that the write method returns an integer representing the number of characters, or bytes, that were successfully written to the file. This can be useful for debugging and tracking data volume, but for the most part, you can safely ignore the return value and rely on the operation completing successfully within the with block. To summarize, use W mode with caution. Now, what if you want to keep the old data and just add new data to the end? That is the job of the append mode, which we will learn next. We will explore the mode and confirm that it adds new data to the end of the file without erasing the original content. Join me in lecture 23.10. Append. See you there. Welcome back. While the W mode is useful for creating new files or overwriting data, it is disastrous if you need to preserve existing content, like in a running log file. For this purpose, we use the append mode, represented by the letter A. 1. The purpose and behavior of a mode. When you open a file in append mode, Python automatically places the file cursor at the end of the existing content. Any data written using the write method will be added after the previous data. Just like W mode, if the file does not exist, the mode will create it for you. 2. Example, appending data. Let's look at the result. If notes.txt contains first note, opening it in a mode preserves that line. When we call write twice, the new lines are simply added to the end. Since we are adding multiple entries, it is vital to remember to manually add the new line character, \n, at the end of each string to ensure proper line separation in the file. 3. The difference between W and A. The difference is crucial. When comparing W mode and a mode, their behaviors when the file exists are opposite. W mode truncates or deletes the content. A mode preserves and adds to the content. Both modes will create the file if it doesn't exist. To summarize, append mode is your go-to for log files and continuous data collection. We have covered all the fundamental file operations. To wrap up this module, let's learn a practical file processing example, counting the lines in a file efficiently. Our next lecture 23.11. Count lines. See you there. Welcome to the final lecture of our File I/O module. We've learned reading, writing, and appending. Now, let's put our knowledge of efficient reading to a practical use case. Reliably and quickly counting the total number of lines in any text file, regardless of how large it is. 1. The inefficient approach. You might initially think to use the readlines method and then count the elements in the resulting list. While this works for small files, it is highly inefficient for large files. Why? Because readlines loads the entire content of the file into your computer's memory at once. If you have a gigabyte file, your program consumes a gigabyte of RAM just to count the lines. 2. The efficient approach. The most memory-efficient solution is to iterate directly over the file object, f. As we learned in section 23.08, this process reads only one line at a time, discarding it before loading the next. We simply use a counter variable, line_count, which we increment in each iteration. This method uses a constant, tiny amount of memory, regardless of the file size. 3. Creating a reusable function. We can package the sufficient logic into a reusable function, count_line, which also includes error handling for files that don't exist. For maximum performance, Python programmers often use a generator expression. There's someone for line in fpart, which is highly optimized for this specific task. Notice we also wrapped the file operation in a try except block to gracefully handle the file not found error. To summarize, iteration is the golden rule for large file processing. You have now completed the entire files section. Our next module transitions to a completely new and powerful topic: regular expressions, the language for pattern matching in text. Okay, we will go to the next section, section 24. Next, join me in lecture 24.01, Introduction. See you there. Welcome to a brand new module, regular expressions, often abbreviated as regex or regex. This is a powerful and valuable topic in programming. Regular expressions provide a concise language for specifying patterns in text, allowing you to find, replace, or extract complex data in a robust way. 1. Why use regular expressions? Imagine you need to validate if a string is a valid email address, find all phone numbers in a 1,000-page document, or extract all href links from a web page. Doing this with standard Python string methods like find or split is complicated and error-prone. Regular expressions handle these complex pattern searches with a single specialized pattern string. 2. Python's real module. Python implements regular expressions using the built-in RE module. We must import this module to gain access to its powerful functions. The 4 core functions we will focus on are search, find all, match, and sub or substitute. Each of these functions allows you to apply a pattern to a string in a different way. 3. The raw string prefix, r. Regular expressions rely heavily on the backslash for special meaning. In Python, the backslash itself is also an escape character. This causes annoying conflicts. To solve this, always use the raw string prefix, r, before your pattern string, like r:\d3. This tells Python to treat backslashes literally, ensuring your regex patterns are interpreted correctly. To summarize, regex is essential for text processing. Our next lecture 24.02, Sequence Characters. See you there. Welcome back. To write any effective regular expression, you need to know the fundamental building blocks, the sequence characters. These are special escape sequences that let you match entire categories of characters, like all digits or all whitespace, without listing every single character explicitly. 1. Digits, \d and \D. The character \D matches any digit, which is the numbers 0 through 9. This is much shorter than writing 0 pipe 1 pipe 2 and so on. Conversely, the uppercase \D matches any character that is not a digit. 2. Word characters, \W and \W. The sequence \W matches any word character. This includes lowercase letters, uppercase letters, digits, and the underscore character. It's often used when matching names or identifiers. \W, the uppercase version, matches any character that is not a word character, which includes punctuation and special symbols. 3. Whitespace, \S and \S. The sequence \S matches any whitespace character. This includes the standard space, tabs, and new line characters. This is extremely useful for matching structured or formatted data. \S matches any character that is not whitespace, such as letters, numbers, or punctuation. To summarize, these sequence characters are your basic vocabulary for regex. Now that we know how to define simple patterns, let's learn the primary function used to test those patterns, the re.search parenthesis function. We will use re.search to find the very first instance of a pattern within a string and understand the match object that it returns. Join me in lecture 24.03, Search. See you there. Welcome back. Now that we know the basic sequence characters, let's look at the most common function for finding a pattern anywhere in a string, re.search parenthesis. This function scans the entire string from start to finish and returns the very first match it finds. 1. Using re.search parenthesis. The search function takes the pattern first, followed by the string you are searching within. In our example, the pattern \D looks for any two consecutive digits. The function finds 10 from 100, as it's the first occurrence. The result of a successful search is a match object. If no match is found, it returns none. 2. The match object. The match object is an essential structure that holds information about the match. To get the actual string that matched the pattern, you call the group parenthesis method on the object. You can also use the expand parenthesis method to find the starting and ending indices where the match occurred in the original string. This object is what you use to process the extracted data. 3. Handling no match. Since re.search returns none when it fails to find a pattern, the match object itself is truthy when a match is found, and none is falsy when it fails. Therefore, you may simply use an if match : statement to check for success. Attempting to call methods like group on none will result in an error, so always check for a match first. To summarize, re.search is great for finding the first instance. Our next lecture 24.04, Find All and Match. See you there. Welcome back. While re.search parenthesis is great for finding the first pattern, often you need to find all occurrences, or you need to strictly check if the string begins with a specific pattern. Today, we cover two other critical functions, our e.findAll parenthesis and our e.match parenthesis. 1. Our e.findAll parenthesis, finding all matches. If your goal is to extract every single piece of data that matches your pattern, findAll is the function to use. Unlike search, which returns only the first match object, findAll returns a simple Python list of strings containing all non-overlapping matches found in the entire string. This makes it perfect for data extraction tasks. 2. Our e.match parenthesis, matching only at the start. The match function behaves like search, returning a match object or none, but with one critical difference. It only attempts to match the pattern at the very beginning of the string. If the pattern is found elsewhere, match will fail, returning none. This makes it ideal for strict validation, such as checking if a file name starts with a specific prefix. 3. Summary of core functions. To summarize the three search functions. To summarize, know your goal, search for the first, find all, or check the start. Our next lecture 24.05. Substitute. See you there. Welcome back. Regular expressions are not just for searching and extracting. They are also incredibly powerful for manipulating and cleaning text data. Today, we will explore the last of the four core functions, our e.sub parenthesis, which is Python's highly versatile substitution function. 1. Using our e.sub parenthesis for replacement. The re.sub function is the equivalent of find and replace all. It takes three arguments, the pattern to find, the replacement string, and the string to search within. Sub scans the entire string, finds every instance of the pattern. In our case, error followed by 3 digits, and replaces them with the string alert. 2. Controlling the number of substitutions. By default, our e.sub replaces all occurrences. However, you may use the optional keyword argument count to limit the number of replacements. If you set count equal to 1, as shown here, only the very first matching pattern will be replaced. This provides fine-grained control over your text manipulation. 3. Practical use case, data cleanup. One of the most common applications of our e.sub is cleaning up user-entered data or extracted web content. By using the pattern /s+, which we haven't formally covered but means one or more whitespace characters, we can replace all occurrences of multiple spaces, tabs, and new lines with a single space, standardizing the format. This is extremely useful in real-world projects. To summarize, our e.sub is the tool for automated text transformation. Our next lecture 24.06. Split. See you there. Welcome back. You may already be familiar with the standard string split method, which is limited to splitting a string based on a fixed delimiter like a comma or a space. The RE module offers a far more powerful alternative, our e.split parenthesis, which uses a regular expression pattern to define complex delimiters. 1. using our e.split parenthesis with multiple delimiters. Standard split can only use one delimiter at a time. Our e.split can use a pattern that matches several different characters. Here, the pattern, our bracket, semicolon, comma, bracket, means split on either a semicolon or a comma. This is incredibly helpful when dealing with inconsistent data formats where separators vary. 2. Handling inconsistent spacing. This is another classic use case. If you have data where a comma might be followed by 0, 1, or several spaces, a standard split on just the comma would leave leading spaces in your output. By using the pattern our comma space star, which we will formally cover soon and means a comma followed by 0 or more spaces, we can remove the comma and all subsequent spaces in a single split operation, resulting in clean substrings. 3. Limiting the split. Similar to other string methods, our e.split supports the optional max split argument. This lets you specify the maximum number of times the split should occur. In this example, setting max split to 1 ensures the string is split only at the first colon, leaving the rest of the string intact as the final element in the resulting list. This is useful for splitting headers from bodies, for example. To summarize, you now know the 4 core functions of the RE module: search, find all, substitute, and split. Our next lecture 24.07, Quantifiers. See you there. Welcome back. So far, our patterns have only matched characters one by one. For example, \d only matches exactly 2 digits. To match phone numbers, words of varying lengths, or any sequence that repeats, we need quantifiers. These tell the regex engine how many times the preceding character or group should occur. 1. The plus sign, which means 1 or more. When the plus sign follows a character or a sequence, it instructs the engine to match 1 or more continuous occurrences of that element. For instance, the pattern \d+ will match any string of digits, such as 1, 12, or 12,345. It is non-optional. At least one match is required. 2. The star sign, which means 0 or more. The star sign is similar to the plus sign, but it makes the preceding element optional. \d* will match any string of digits, but it will also match an empty string, or where there are no digits at all. It is widely used when optional whitespace might be present. 3. The question mark, which means 0 or 1. This makes the preceding element strictly optional. It means match it if it's there, but don't worry if it's not. The question mark is useful for matching singular or plural forms, or prefixes that may or may not be present in the data. 4. Curly braces, n, m curly brace, which means specific range. The curly braces allow you to define an exact number or a range of repetitions. You can specify an exact number, like curly brace 4 curly brace, to match exactly 4 digits. You can specify a minimum n comma, or a maximum comma m, or a range n comma m to match n to m times. This is perfect for fixed-length data like postal codes. To summarize, quantifiers enable you to move beyond single-character matching. Our next lecture 24.08, Using Quantifiers. See you there. Welcome back. In the last section, we defined the four main quantifiers. Now, it's time to combine them with our sequence characters to build practical, real-world patterns. Understanding how quantifiers control repetition is the key to matching complex data structures. 1. Matching variable length numbers. If we want to find all prices preceded by a $sign, we can't use a fixed number of digits because prices vary. We use the pattern $$D+. The plus sign here, plus sign, ensures that our pattern matches numbers with 1, 2, 3, or any number of digits, but only if at least one digit is present. Notice that the $sign itself must be escaped with a backslash because it is a special character in regex, which we maybe will discuss later. 2. Matching words and spaces. To extract individual words, we combine the word character sequence \w with the plus sign. The pattern \w plus matches any sequence of word characters, effectively grabbing each word. If you wanted to match multiple spaces, you may use \s plus, matching \s one or more times, which is essential for data cleaning, as we saw with our e.sub parenthesis. 3. Matching fixed-length data, like phone numbers. For data that follows a strict format, the curly brace range quantifier is the best tool. The pattern \d curly brace 3 curly brace hyphen back /d curly brace 3 curly brace hyphen back /d curly brace 4 curly brace is precise. It says exactly 3 digits followed by a hyphen, then 3 more digits, then a hyphen, then exactly 4 digits. This strictness is critical for validation and structured extraction. To summarize, you can now build powerful patterns for common text structures. Our next lecture 24.09, Matching Dates. See you there. Welcome back. Matching dates is a quintessential regular expression problem because dates often appear in many different formats. Slashes, hyphens, for digit years, 2-digit years, and so on. This lecture shows you how to combine sequence characters and quantifiers to create flexible and accurate date patterns. 1. Matching a simple fixed format. For a strictly formatted date like month/day/year/year, we use the fixed-length quantifier curly brace n curly brace and the digit sequence \d. The pattern \d curly brace 2 curly brace /d curly brace 2 curly brace /d curly brace 4 curly brace exactly specifies 2 digits, followed by a slash, then 2 more digits, and so on. This is precise but lacks flexibility. 2. Matching multiple delimiters and year lengths. When the format is inconsistent, we need flexibility. We introduce the character set inside square brackets /hyphen square bracket, which means match either a slash or a hyphen. We also use the range quantifier curly brace 1, 2 curly brace for the month and day, allowing 1 or 2 digits. Finally, the year allows for either 2 or 4 digits using curly brace 2, 4 curly brace. This significantly increases the pattern's versatility. 3. The greedy nature of quantifiers. A key principle in regex is that quantifiers like plus sign, star sign, and the range quantifier are greedy by default. This means they match as much text as possible while still allowing the entire pattern to succeed. For example, \d+ will match all 5 digits in 10000, not just the first one, because matching 5 digits satisfies the one or more condition while consuming the maximum number of characters. To summarize, you can now build sophisticated patterns using the tools we've covered. Our next lecture 24.10, Special Characters. See you there. Welcome back. So far, we've used sequence characters like \d and quantifiers like +. Now, let's look at the remaining special characters that control character choices and define boundaries, allowing you to create truly sophisticated patterns for validation and extraction. 1. Character sets, square brackets, square brackets. Any character placed inside square brackets means match any single character within this set. We saw this when matching dates with slashes or hyphens. You can also define ranges. For example, square bracket (-z) square bracket matches any single lowercase letter. If you place a caret sign, immediately after the opening bracket, it means match any single character that is not in this set. 2. Or operator and any character. The pipe sign, acts as the logical or operator, allowing you to match one complete pattern or another complete pattern. This is different from character sets which match single characters. The dot sign, matches any single character except the newline character by default. This is often used as a placeholder. 3. Anchors, $sign and $sign. These characters are called anchors because they do not match actual characters but instead match a position. The caret sign, matches the position at the start of the string. The $sign, matches the position at the end of the string. Using both caret sign pattern $sign is the definitive way to validate that an entire string conforms to the pattern, not just a part of it. To summarize, these special characters give you surgical precision over your matches. Our next lecture 24.11, Using Special Characters. See you there. Welcome back. In the last lecture, we defined the special characters that form the structure of advanced regular expressions. Now we will combine anchors, character sets, and the OR operator to build a robust pattern for a common validation task, checking for a simple email address. 1. Building the username part or local part. The first part of an email address before the @ sign typically consists of letters, numbers, and maybe some punctuation like dots or underscores. We use a character set, square brackets, to define the allowed characters, -z, 0-9, and the dot, and underscore. Then we apply the +sign quantifier to ensure that this local part has one or more of these characters. 2. Building the domain name part. After the @ sign, we have the domain name, like gmail.com. This is similar to the local part but often separated by dots. The pattern we use, square bracket (-z0-9+), ensures one or more allowed characters for the main domain. This is followed by a literal dot, \dot, which is required because the plain dot is a special character, and then another set of one or more allowed characters for the top-level domain, like com. 3. The complete validation pattern. We combine the local part and the domain part with a literal @ sign. Crucially, we wrap the whole expression in the anchor characters, the caret sign, at the beginning, and the $sign, at the end. This ensures that the pattern matches the entire string, not just a small piece of text within a larger invalid string. This is the difference between extraction and strict validation. To summarize, you now know the key components of regular expressions. Our next lecture, 24.12, Web Scraping Demo. See you there. Welcome to the final lecture of our regular expressions section. To conclude, we will tackle one of the most practical applications of regex: extracting data from unstructured text, specifically HTML, a process often called web scraping. We will see how to use the components we've learned to pull out links and titles. 1. Defining the target data. Let's assume we have a simple block of HTML containing a few anchor tags, href tags. Our goal is to extract the href value, which is the link target, and the text between the opening and closing tags, which is the link title. We will use one powerful pattern to extract both pieces of information simultaneously. 2. The extraction pattern. This pattern may look intimidating, but it's just a combination of concepts we've learned. The parentheses, around the link value and the title text create capturing groups. When you use our e.findAll parenthesis with capturing groups, it returns a list of tuples, where each tuple contains the strings matched by those groups. 3. Executing the extraction. When we run our e.findAll parenthesis on the HTML using our pattern, it successfully extracts a list of tuples. The first element of each tuple is the href link, and the second is the text title. This shows the power of combining quantifiers, character sets, and capturing groups for complex data extraction like web scraping. To summarize, you've mastered regular expressions, a highly valuable tool for text processing. Our next module shifts focus entirely to managing and manipulating time, which is critical for logging, scheduling, and performance measurement. Our next lecture, 25.01, Date and Time. See you there. Welcome to a new section, Date and Time. Many programs need to handle time, whether it's logging when an event occurred, scheduling future tasks, or measuring performance. Python handles these concepts primarily through its built-in datetime module. 1. The datetime module classes. The datetime module contains several classes. The three most important are the date class, which holds year, month, and day information, the time class, which holds hour, minute, second, and microsecond information, and the composite datetime class, which holds all of this information combined. We must import the module before we can use any of these classes. 2. Creating a date object. To create a specific date, you call the datetime.date constructor, passing the year, month, and day as arguments, all of which must be integers. Once created, the resulting date object has attributes like .year and .month that allow you to easily access the component parts of the date. 3. The datetime object. The datetime.datetime class is the most comprehensive, combining all the components. To create one, you pass the year, month, and day, followed by the hour, minute, second, and optionally microsecond. Just like the date object, you may access the individual components using attributes like .hour or .minute. To summarize, the datetime module gives us structured ways to handle time. Our next lecture 25.02, Time since Epoch. See you there. Welcome back. To truly understand how computers handle time, you must know the concept of epoch time, often called Unix time or POSIX time. This system allows computers to compare and store timestamps as simple, universally comparable numbers. 1. What is the epoch? The epoch is a fixed point in time, January 1st, 1970, at midnight Coordinated Universal Time. The epoch timestamp is simply the total number of seconds that have passed since that exact moment. Computers prefer this because a single integer or floating point number is easy to store, transfer, and sort globally, without dealing with time zones or daylight saving rules. 2. Getting the epoch timestamp with .timestamp parenthesis. Any datetime object has a useful method called .timestamp parenthesis. When you call this method, it returns the time in seconds since the epoch as a floating point number. This is what you would use to convert a human-readable time into the machine's numerical time format for storage in databases or system logs. 3. Reversing the conversion with .fromTimestamp parenthesis. The datetime.datetime class also provides a class method called .fromTimestamp parenthesis. You pass it an epoch value, a float or an integer representing seconds, and it returns a full datetime object. This is how you convert machine time back into a format people can read. The ability to switch seamlessly between these two representations is fundamental to working with time. To summarize, epoch time is the numerical backbone of timekeeping. Our next lecture 25.03, Finding the Current Date and Time. See you there. Welcome back. The frequent task when dealing with time may be simply getting the current date and time, for logging, timestamps, or display. Python's datetime module makes this extremely easy using two primary class methods, .now parenthesis and .today parenthesis. 1. Getting current date and time with .now parenthesis. The static method datetime.datetime.now parenthesis returns a new datetime object representing the exact current moment according to your system's clock. It is the most precise way to timestamp an event, as it includes the microsecond information. The object returned is, of course, a datetime object, meaning it contains all date and time components. 2. Getting current date with .today parenthesis. If you only need the current date, the year, month, and day, you may use datetime.date.today parenthesis. This method returns a date object, not a datetime object. It's often cleaner to use this when the time component is irrelevant, such as recording someone's birth date or the current business day. 3. Extracting components and timestamping. Once you have a current datetime object using .now parenthesis, you can apply everything we learned previously. You may use the attributes like .month or .day to get specific components, and you can easily convert the current moment into its numerical epoch timestamp using the .timestamp parenthesis method. To summarize, getting the current time is simple with .now and .today. Our next lecture 25.04, Combining Date and Time. See you there. Welcome back. In real-world data, you may encounter dates and time stored in separate fields, perhaps one column for the date and another for the time. To perform time-based calculations or conversions, you must merge these into a single date-time object. This section shows you how to use the datetime.combine parenthesis class method. 1. Using datetime.datetime.combine parenthesis. This is a class method that takes exactly two arguments, a date object and a time object. It then returns a new single datetime object with the components of the first object and the time components of the second. This is a simple way to merge date and time components in Python. 2. Modifying components with .replace parenthesis. Once you have a datetime object, you may need to adjust only a few components, perhaps setting the time to midnight or correcting the year. The .replaced parenthesis instance method allows you to create a new datetime object based on the original, substituting only the fields you specify. The original object is unchanged, and the remaining components are carried over to the new object. 3. Extracting and combining components. A scenario is taking the current date and setting the time to exactly midnight. You can do this by first calling the .date parenthesis method on the .now parenthesis object to get the current date part, and then combining that date part with a new, manually created time object representing midnight. This shows the flexibility of combining methods for precise time manipulation. To summarize, you can now build and modify datetime objects from different pieces. Our next lecture 25.05, Sorting Dates. See you there. Welcome back. When dealing with data like system logs, transaction records, or scheduled events, you often need to organize them chronologically. Fortunately, datetime objects in Python are natively comparable, meaning you can use standard sorting functions directly on lists of these objects. 1. Comparing datetime objects. Python makes time comparison intuitive. You can use standard comparison operators like less than sign or greater than sign directly between any two datetime objects. The comparison is based on the absolute point in time. If one object is chronologically earlier than another, the comparison will reflect that. This is the foundation of sorting. 2. Sorting in ascending order. Because datetime objects are comparable, you may simply pass a list of them to Python's built-in sorted parenthesis function. By default, it will sort the list chronologically from the earliest time to the latest time, known as ascending order. The output here clearly shows the January date comes first, followed by March and then May. 3. Sorting in descending order. If you need to see the most recent events first, a common requirement for log displays or news feeds, you may use the optional keyword argument reverse set to true. This sorts the list in descending order, meaning the latest date and time will appear first in the resulting list. To summarize, sorting time is straightforward in Python because the datetime objects handle the complexity. Our next lecture 25.06, Sleep. See you there. Welcome back. While the datetime module is great for manipulating dates, a separate module called time contains functionality for system-level time control. You may pause your program's execution using the time.sleep parenthesis function. This is essential for controlling resource usage or adhering to rate limits when interacting with external systems. 1. Importing the time module. Unlike the datetime module, which contains the datetime class, the sleep function belongs to the separate, lower-level time module. To use it, you must import time. The time.sleep parenthesis function takes a single argument, the number of seconds, as a float or an integer, for which the program should pause. During this pause, the program consumes minimal CPU resources. 2. Practical example, simple countdown. A demonstration is a countdown timer. By placing time.sleep parenthesis inside a loop, we can control the pace of execution. In this example, the program prints the countdown number and then pauses for exactly 1 second before iterating to the next number. This demonstrates precise, controlled delays. 3. Pausing for sub-second durations. Since time.sleep parenthesis accepts a float, you can pause for less than a second, such as half a second. This is useful for very precise rate limiting or creating smooth, though basic, text-based animations. Just remember that the operating system guarantees a minimum pause, but the actual pause may be slightly longer due to system overhead. To summarize, time.sleep parenthesis is your tool for scheduled inaction. Our next lecture 25.07, Knowing the Execution Time of a Program. See you there. Welcome back. Measuring the execution time of a function or a block of code is a fundamental skill in optimization and debugging. It helps you identify performance bottlenecks. We can achieve this easily by using the datetime.now parenthesis method twice and then calculating the difference, which introduces a new concept, the time delta object. 1. The measurement principle. The method is straightforward. First, you capture a start time snapshot using datetime.now parenthesis before the code runs. Second, you capture an end time snapshot immediately after the code finishes. Finally, you subtract the start time from the end time. The difference is the exact time elapsed during the execution. 2. Calculating elapsed time. In this example, we use time.sleep parenthesis to simulate a long task. When we subtract start time from end time, Python creates a new type of object called a time delta object. This object represents a duration, or the difference between two datetime objects. The output shows the difference in hours, minutes, seconds, and microseconds. 3. Extracting total seconds. While the default time delta representation is human-readable, for performance analysis or precise calculations, you often want a single floating point number representing the total duration in seconds. The time delta object provides the .total seconds parenthesis method for this exact purpose. This gives you a high precision number that you can use for comparisons, benchmarks, or logging. To summarize, you can now easily benchmark your own code. Our next lecture 25.08, Validate Credit Card Use Case. See you there. Welcome back. In this lecture, we apply our knowledge of the DateTime module to a critical real-world problem, validating if a credit card is expired. This involves parsing a date string and comparing it against the current date. 1. Understanding credit card expiry. A credit card expiration date, typically presented as month/year, is valid until the very last day of that month. For example, a card expiring in 12/25 is valid until midnight on December 31st, 2025. Our challenge is to convert the input date into a DateTime object representing the first moment after the card expires, and then compare it to today. 2. Parsing the expiration date string. We use the powerful datetime.datetime.strptime class method, which means string parse time. It takes the date string and a format code string. The format code %m/%y tells Python to expect a 2-digit month, a slash, and a 2-digit year. Since the input only provides month and year, strptime defaults the day to the first of the month. We then use .date parenthesis to get only the date part. 3. The validation logic. The key trick is to compare today against the first day of the month following the expiration month. If the card expires in November, we check if today is greater than or equal to December 1st. If it is, the card is expired. If it's earlier, the card is still valid. Image illustrating credit card expiry validation logic. If today is greater than or equal to first day of next month, then expired. This simple comparison leverages the native comparability of date objects we saw earlier. To summarize, you can use strptime and date comparison logic to validate expiry dates, making your application secure. Our next lecture 25.09, Project Management Use Case. See you there. Welcome to the final lecture of our date and time section. We will now apply our knowledge of DateTime objects and time delta to a project management scenario, calculating future deadlines and determining the remaining time for a task. 1. Creating a time delta object. The time delta class, which we encountered when measuring execution time, is primarily used to represent a duration, a difference in time, not an absolute point in time. You create one by passing keywords like days, hours, minutes, or seconds. Here, we define a project duration of 30 days and 8 hours. 2. Calculating a future deadline using addition. The magic of time delta is that you may add it directly to a DateTime object. When you add a duration to a DateTime object, Python handles the complexity of calendar math, like rolling over months and years, and returns a new DateTime object representing the date and time in the future. This is perfect for setting project deadlines. 3. Calculating time remaining using subtraction. To find the time remaining until a deadline, you subtract the earlier DateTime from the later one. The result is, once again, a time delta object, which tells you the duration between those 2 points. You may then access the .days attribute to get the whole days remaining, or use .total seconds parenthesis for a more granular view. To summarize, you now have a complete toolkit for handling dates, times, durations, and system time, covering everything from logging to project management. Our next lecture 26.01, Introduction. See you there. Welcome to a powerful new module, Threads. Up until now, our code has executed sequentially one instruction after the other. But modern applications must handle multiple tasks simultaneously, like responding to a user interface while downloading a file in the background. This concurrency is achieved through threads. 1. Process versus thread. To understand a thread, you must first know a process. A process is an independent instance of a running program, such as your Python interpreter or a web browser. Processes are isolated. They do not share memory. A thread is the smallest unit of execution within a process. Multiple threads within the same process share the same memory and resources, making communication and coordination much faster. 2. What is multithreading? Multithreading is the ability of a single program to manage and execute multiple threads concurrently. This concurrency is crucial for tasks where one part of the program is waiting for an external operation to complete, like network input or disk access. While one thread waits, the operating system may switch control to another thread, keeping the CPU busy and the application responsive. 3. The Python threading module. Python provides the threading module to create and manage threads. We will use the main thread class from this module, along with methods like .start parenthesis to kick off the thread's execution. We will also explore functions to identify which thread is currently running the code, which may be useful for debugging. To summarize, threads enable concurrency by sharing resources within a single process. Our next lecture 26.02, Main Thread. See you there. Welcome back. Every Python script you have ever executed has run within a thread. When a Python program starts, the operating system creates a process, and that process automatically creates one default thread to execute your code. This is called the main thread. 1. Role of the main thread. The main thread is responsible for executing all sequential code in your script. It is also the thread that, when it completes its execution, signals the operating system that the Python program should shut down. All user-created threads run concurrently with, and are managed by, this main thread. 2. Identifying the current thread. To verify the existence and identity of the main thread, we use threading.currentName parenthesis. This function returns a reference to the thread object that is currently running the code. We may then access its .name attribute. For the default thread running your script, this name is always main thread, and its daemon status is always false. 3. The execution flow. Any line of code you write outside a function or a custom thread is executed sequentially by the main thread. From the first line to the last, the entire script runs under the main thread identity. We will use this knowledge as a baseline when we start creating new threads in the next section to clearly distinguish between the default execution flow and the concurrent flow. To summarize, all Python code runs in the main thread. Our next lecture 26.03, Thread using a function. See you there. Welcome back. I have a way to create a new thread in Python is to pass a target function to the threading.thread class constructor. The new thread's job will be to execute that function concurrently with the main program. 1. Defining the thread's task. First, we define a regular function, here named task function, which represents the independent work we want to run concurrently. Inside this function, we identify the thread executing it, which, for a new thread, will not be the main thread. This function will be the entry point for our new thread. 2. Creating and starting the thread. To create the thread, we instantiate threading.thread. We must pass our task function to the target argument. If the function accepts arguments, we pass them as a tuple to the args argument. Notice the comma after the single string argument to ensure Python recognizes it as a tuple. Importantly, creating the thread does not start it. You must explicitly call newThread.start parenthesis to instruct the operating system to begin executing the target function in a new, concurrent thread. 3. Execution order or concurrency. The key takeaway here is that once .start parenthesis is called, the main thread immediately continues to the next line of code. It does not wait for the task function to finish. The task function now executes concurrently, meaning its output may interleave with or appear after the main thread's output. This is the essence of multithreading. To summarize, creating a thread from a function is simple using target and args. Our next lecture 26.04, Printing Thread Names. See you there. Welcome back. When debugging or logging a multi-threaded application, knowing which thread executed a specific piece of code is essential. Python automatically names new threads, but using descriptive, custom names makes tracking concurrency much easier. This section focuses on naming threads. 1. Default thread naming. When you create new threads without specifying a name, the threading module assigns a default name sequentially, thread-1, thread-2, and so on. This mechanism helps distinguish them from the main thread, but these generic names are not very informative about the thread's actual purpose. 2. Assigning custom names. To assign a meaningful name, you simply pass the desired string to the name argument in the thread constructor. Here, we create one thread explicitly named downloader thread and another named data processor. When these threads run the worker function, the output will clearly indicate which thread is performing the task, greatly simplifying debugging. 3. Retrieving the name, which is a practice. To access the thread's name inside the function it is running, you must use threading.currentThread.name. This practice ensures that all logging and error messages automatically contain the context of which thread generated them, which is absolutely vital in multi-threaded programming. To summarize, always name your threads for clarity. Our next lecture 26.05, Thread Extending the Thread Class. See you there. Welcome back. While passing a function to the target argument works well for simple tasks, the object-oriented approach is often cleaner for complex threads that need to maintain internal state or properties. This involves creating a custom class that extends the base threading.thread class. 1. Defining the custom thread class. To extend the class, we define class workerThread, parenthesis, inheriting from threading.thread. Crucially, we must override the special .run parenthesis method. This .run parenthesis method is the equivalent of the target function. When the thread starts, this is the method that executes. Any initialization, like setting the thread name or internal data, is done in the constructor, remembering to always call the parent's constructor using super.init parenthesis. 2. Instantiating and starting the class thread. To run the custom thread, the steps are familiar. First, instantiate the class just like any other Python object, passing any arguments defined in your custom constructor like the thread name and task count. Second, call the .start parenthesis method on the instance. Just like with the function approach, the .start parenthesis method is what triggers the operating system to begin concurrent execution of the thread's .run parenthesis method. 3. The .start parenthesis versus .run parenthesis distinction. It is a critical distinction that you must always call .start parenthesis, not .run parenthesis. Calling .start parenthesis correctly registers the thread with the operating system and invokes .run parenthesis in a separate, concurrent thread. If you mistakenly call .run parenthesis directly, the code will execute, but it will run in the main thread, completely defeating the purpose of multithreading. To summarize, subclassing is the OOP way to create complex threads. Our next lecture 26.06, Thread Using a Class. See you there. Welcome back. In the previous lecture, we extended the threading.thread class. However, sometimes you want to run a method from a class that already exists and cannot inherit from thread. This technique, where you pass an instance method of a normal class as the target to the thread constructor, is a flexible approach. 1. Defining a regular class task. Here we define a simple class, file manager, which does not inherit from threading.thread. It holds data like file name and has a method, process file, which we want to run in a separate thread. This method accepts an argument, mode. This class is decoupled from the threading logic, which is an advantage for clean architecture. 2. Running the method as a thread target. The key step here is creating the thread instance. Instead of passing a standalone function, we pass the instance method, FileManager.ProcessFile, to the target argument. When Python sees this, it correctly binds the method to the object instance. The arguments for the method, in this case, read-only, are passed to the args tuple as usual. When .start parenthesis is called, the process file method is executed concurrently. 3. Advantages of this approach. This method is often preferred because it separates the business logic, which is the file manager class, from the concurrency logic, which is handled by threading.thread. The file manager remains a regular class that can be used in both threaded and non-threaded contexts, making the code more modular and reusable. This is a powerful technique for integrating existing classes into a multi-threaded design. To summarize, you now know 2 ways to create a thread using classes. Our next lecture 26.07, Multithreading in Action. See you there. Welcome back. We have learned how to create individual threads. Now it is time to unleash the full power of concurrency by launching multiple threads to perform different tasks at the same time. This section demonstrates true multi-threaded operation and introduces the essential .join parenthesis method. 1. Defining the concurrent tasks. We define a simple worker function, print numbers, that takes a range and prints the numbers along with the thread's name. We will use this same function as the target for several different threads, each working on its own separate range. The interleaving output will confirm they are running concurrently. 2. Launching multiple threads. We create 3 separate thread objects, named A, B, and C, each targeting print numbers, but with distinct ranges. We store them in a list for easy management. We then loop through the list and call .start parenthesis on each one. Once all 3 are started, they are all running concurrently alongside the main thread, competing for the CPU's time. 3. The importance of thread.joined parenthesis. When the main thread finishes, the entire program exits, even if the worker threads are still running. If the main thread needs the results of the worker threads before continuing, it must wait. The .join parenthesis method forces the calling thread, in this case the main thread, to wait until the thread it is called on completes its execution. We loop again and call .join parenthesis on each worker thread, guaranteeing that the final print statement only executes after all workers are done. To summarize, you can now launch multiple threads and control when they finish using .join parenthesis. Our next lecture 26.08, Using Sleep. See you there. Welcome back. In our previous lecture, we learned that time.sleep parenthesis pauses the execution of a program. In a multi-threaded application, time.sleep parenthesis only pauses the thread that calls it, not the entire process. This is a crucial distinction and a great way to visually demonstrate concurrency. 1. Defining the sleeping task. We modify our worker function to accept a delay argument and use time.sleep parenthesis with that value. When a thread executes this line, it temporarily yields control of the CPU. This pause, however, does not stop the other threads, which remain active and may continue their own execution in the meantime. 2. Observing concurrency with uneven delays. We create 2 threads, worker-A and worker-B, giving them 2 different delay times, 2 seconds and 1 second, respectively. When we start them, both begin their tasks. However, when they reach the time.sleep parenthesis call, worker-B will finish its pause and print, finish sleeping 1 second before worker-A, which is still waiting. This clearly illustrates that the threads operate independently. 3. The concurrency challenge. While this is great for allowing threads to perform background tasks without blocking the main thread, it highlights the lack of control over execution order. If both threads were accessing and modifying the same shared resource like a variable or a list, the unpredictable order caused by these natural or artificial delays like time.sleep parenthesis would quickly lead to race conditions and corrupted data. This challenge leads us directly into our next set of topics. To summarize, time.sleep parenthesis is thread-specific. Our next lecture 26.09, the ticket booking use case. See you there. Welcome back. In this lecture, we tackle a classic multithreading problem that demonstrates why uncontrolled concurrency can be disastrous. The ticket booking use case. We will simulate 2 users simultaneously trying to book the last available ticket. 1. The shared resource and task. We define a global variable, available ticket, and initialize it to 1, representing the last ticket. Our book ticket function represents a user trying to book. The critical part of this transaction involves two sequential steps. First, checking if tickets are available, and second, decrementing the count if they are. The problem arises if two threads execute the first step before either one can execute the second. 2. Creating the race condition. Inside the if condition, we simulate a small delay using time.sleep parenthesis. This pause is the key. While the first thread, say, user1, pauses after checking that available tickets is greater than 0, the operating system may switch execution to the second thread, user2. User2 also sees that the ticket count is 1, enters the if block, and pauses. When both threads eventually finish their pauses, they both successfully decrement the ticket count, resulting in a negative number which is logically impossible. This is known as a race condition. 3. Launching the competing threads. We launch two threads, user-1 and user-2, and then wait for them to finish with .join parenthesis. When you run this code, you may consistently see an incorrect final ticket count, likely -1, even though only one ticket was available. This severe bug in shared data integrity is precisely why we need the next topic, thread synchronization. To summarize, the ticket booking problem proves that sharing data between threads without strict control is unsafe. Our next lecture, 26.10, Thread Synchronization. See you there. Welcome back. The ticket booking use case exposed a severe problem, the race condition, where multiple threads corrupt shared data. The solution is thread synchronization, which means coordinating the execution of multiple threads to ensure that when one thread is accessing a critical piece of data, no other thread may interfere. 1. The critical section. A critical section is any part of the code where shared resources, like variables or data structures, are accessed or modified. In the ticket use case, the critical section was the if block where we checked the ticket count and then decrement it. To prevent race conditions, we must ensure that only one thread can be inside this critical section at any given moment. This is called mutual exclusion. 2. Introducing the lock object. We have a simple synchronization primitive is the lock object from the threading module. A lock starts in an unlocked state. When a thread wants to enter a critical section, it calls lock.acquire parenthesis. If the lock is unlocked, the thread immediately enters and the lock becomes locked. If the lock is already locked by another thread, the calling thread is forced to wait until the lock is released. 3. Using the lock manually. The pattern for using a lock involves three parts. First, call lock.acquire parenthesis before the critical section. Second, execute the critical code. Third, call lock.release parenthesis after the critical code. It is a practice to wrap the critical section in a finally block. The finally block ensures that lock.release parenthesis is always called, even if an exception occurs inside the critical section, preventing a potential deadlock. To summarize, locks prevent race conditions by forcing threads to wait their turn. Our next lecture, 26.11, Add More Logic. See you there. Welcome back. We are now going to fix the critical bug in our ticket booking use case. The negative ticket count was caused by both threads entering the critical section simultaneously. We will now integrate the lock object to ensure that only one thread can check and modify the available tickets variable at a time. 1. Initializing the lock. Just as available tickets is a shared resource, the ticket lock must also be created once and shared among all threads that need to access that resource. We create one instance of threading.lock parenthesis at the global level, and this single lock instance will now be used by both of our competing threads. 2. Protecting the critical section. We insert ticket lock.acquire parenthesis at the entry of the critical section. Now, when user 1 calls this, it acquires the lock and proceeds. When user 2 calls it immediately afterward, it finds the lock held and is forced to wait indefinitely at this line until the lock is released. This enforces mutual exclusion. We ensure ticket lock.release parenthesis is called an A finally block to prevent a deadlock if an error occurs within the protected code. 3. Verifying the fixed logic. When you run the synchronized code, you will observe the output confirming that one thread acquires the lock first. The other thread is seen waiting. The first thread successfully books the ticket and decrements the count to 0. When the second thread finally acquires the lock, it finds that available tickets is no longer greater than 0, and it is correctly denied the ticket. The final ticket count is consistently 0, confirming that our race condition has been successfully fixed. To summarize, locks are the foundation of safe multithreading. Our next lecture 26.12, Synchronization using lock. See you there. Welcome back. In the previous lecture, we successfully used lock.acquire parenthesis and lock.release parenthesis to solve the race condition. However, using a try finally block for every critical section can be repetitive. Fortunately, Python's lock object is also a context manager, offering a cleaner and safer syntax. 1. The context manager pattern. A context manager is an object that defines the runtime context for a block of code, automatically handling resource setup and teardown. You have seen this with file handling, with open parenthesis file, name comma mode parenthesis as f colon. For a lock, the with statement automatically calls .acquire parenthesis upon entering the block and guarantees that release parenthesis is called upon exiting the block, even if an error occurs. This eliminates the need for manual try. Finally, 2. Refactoring the booking logic with look at how cleaner the code becomes. We simply use with ticket lock colon to wrap the critical section. The lock is acquired when execution enters the with block and automatically released when execution leaves the block, whether it exits normally or due to an exception. This is the recommended way to use locks in Python for mutual exclusion. 3. The advantage of clean code. The primary advantages of using the with statement are simplicity and safety. It prevents accidental deadlocks caused by forgetting to call .release parenthesis, as Python guarantees the release mechanism. This leads to code that is not only shorter but is also more robust and easier for other developers to read and understand. To summarize, use the with statement for all critical sections protected by a lock. Our next lecture 26.13, Synchronization using semaphore. See you there. Welcome back. While the lock object enforces strict mutual exclusion, allowing only one thread at a time, there are scenarios where you need to allow a specific, limited number of threads to access a resource concurrently. For this, we use the semaphore. 1. What is a semaphore? A semaphore is a synchronization primitive that maintains a counter. This counter is initialized to a specific value, representing the number of available permits. When a thread calls .acquire parenthesis, the counter is decrement. If the counter is greater than 0, the thread proceeds. If the counter is 0, the thread blocks until another thread calls .release parenthesis, incrementing the counter and freeing a permit. 2. Initialization and usage. We initialize the semaphore with 3, meaning only 3 threads can enter the database connection critical section at any one time. We use the convenient with statement just like with a lock. Threads will execute the connect to dbeep function. The first 3 will proceed immediately, but the 4th thread will be blocked at the with statement until one of the first 3 threads calls .release parenthesis by exiting the block. 3. Running the semaphore simulation. We launch 5 threads to simulate 5 clients trying to connect to a database that only allows 3 simultaneous connections. You will observe that 3 threads acquire the connection immediately, while the remaining 2 are forced to wait for 2 seconds. As soon as one of the active threads finishes its work and releases its permit, one of the waiting threads immediately grabs it and continues. The final output confirms that only 3 threads were active at any given moment, successfully managing the limited resource. To summarize, locks are for mutual exclusion, semaphores are for boundary control. We have learned synchronization. Our next lecture 26.14, Thread Communication. See you there. Welcome back. We have successfully synchronized threads to protect shared data. The next critical topic is thread communication. How do we enable one thread to inform another thread about a change in state, a completion of a task, or that new data is available? 1. Why communicate? Synchronization prevents simultaneous access, but it doesn't help threads coordinate their actions. For instance, an uploader thread needs to tell a processor thread when a large file is ready, or a main thread might need to signal an indefinitely running worker thread to shut down. Coordination between tasks is the essence of effective multithreading. 2. Using a shared Boolean flag. The most basic form of communication is a shared variable, typically a Boolean, used as a flag. One thread, the main control thread, sets the shutdown flag to true to signal a state change. The worker thread continuously checks this flag inside its main processing loop. This constant checking is called polling. 3. The downside of polling. While simple, polling is inefficient. The worker thread spends valuable CPU cycles repeatedly checking the shared flag, even when the flag hasn't changed. If the task is long, the shutdown will be delayed until the task finishes. If the check is too frequent, it wastes resources. If it is too infrequent, the thread responds slowly to the signal. To summarize, Boolean flags are easy, but polling is inefficient. Our next lecture 26.15, Using a Boolean flag. See you there. Welcome back. We established that using a shared Boolean flag with polling is the simplest method for inter-thread communication. In this lecture, we will implement this pattern to control the shutdown of a long-running worker thread from the main thread. 1. Defining the flag and the worker task. We define stop_flag and, importantly, a flag lock. Even for a simple Boolean, it is best practice to protect it with a lock to avoid race conditions if two threads try to modify it simultaneously. The worker task runs an infinite while true loop. In each iteration, it acquires the lock, checks the flag, and breaks the loop if the flag is set. Then, it releases the lock and executes its simulated work for half a second. 2. The signaling mechanism. We define a separate function, signalStop, which runs in its own thread. After a 2-second delay, this signaling thread acquires the lock, sets the stop_flag to true, and releases the lock. The next time the worker task thread checks the flag, it will see the change, exit its loop, and terminate gracefully. 3. Launching and observing shutdown. We launch both the worker and the signaler threads, and the main thread waits for both to complete using .join parenthesis. The output will show the worker processing for about 2 seconds before the signaler sets the flag. Immediately after the signaler sets the flag, the worker's next check causes it to break its loop and exit. This confirms successful controlled communication. To summarize, the Boolean flag works, but the polling wastes CPU resources. Our next lecture 26.16. Run and summarize. See you there. Welcome back. We just implemented a thread shutdown mechanism using a Boolean flag. Let us now run this code, observe the exact behavior you may see, and critically analyze the efficiency of this polling approach. 1. Execution review with correct output. When we run the script, we see the worker thread start immediately and print working. The signaler thread prints its intent to wait 2 seconds. The worker continues printing working several times while the signaler is delayed. This concurrent activity is expected. Once the signaler sets the flag, the worker's next check causes it to break its loop and terminate. Functionally, the shutdown is successful and controlled. 2. The problem polling, also known as busy waiting. Although the worker thread uses time.sleep parenthesis to simulate work, it is still consuming CPU time on every half-second iteration just to check the flag. If the worker's task was short, say a few milliseconds, it would be checking the flag thousands of times per second. Polling is like constantly looking at your clock while waiting for the next minute to start. It is an inefficient use of resources because the thread is active but not performing meaningful work until the flag changes. 3. The solution, event-driven communication. The goal should be for the waiting thread to consume 0 CPU resources until the event happens. Instead of polling, we use a mechanism where the thread can explicitly go to sleep and be woken up only when another thread signals the event. This is the wait and notify pattern, which maybe we will see next. To summarize, we must transition from busy waiting to blocking communication. Our next lecture 26.17. Thread communication using wait and notify. See you there. Welcome back. We have seen that polling causes busy waiting, which wastes CPU cycles. To solve this, we need a way for threads to sleep when they have nothing to do and wake up only when necessary. Python provides the condition object for exactly this purpose. 1. The condition object. A condition variable is always associated with a lock. When you create a threading.condition parenthesis object, it creates a lock internally. This object allows one or more threads to wait until they are notified by another thread. It serves as both a synchronization primitive like a lock and a communication channel. 2. The wait method. This is the consumer side. When a thread calls condition.wait parenthesis, three things happen atomically. First, it releases the underlying lock. Second, it blocks execution and goes to sleep, consuming no CPU. Third, when it is eventually woken up, it automatically reacquires the lock before continuing. This is much more efficient than polling. 3. The notify method. This is the producer side. When a thread has performed a task or changed a state that the waiting thread cares about, it calls condition.notify parenthesis. This sends a signal to wake up one of the threads waiting on this condition. Note that notify does not release the lock immediately. The notifying thread must exit with block or explicitly release the lock before the woken thread can proceed. To summarize, use wait to sleep and notify to wake up. This is the standard pattern for efficient thread communication. Our next lecture 26.18. Use wait and notify. See you there. Welcome back. We are now upgrading our thread communication mechanism. We will replace the inefficient polling method with the elegant and CPU-friendly wait and notify mechanism using the condition object. 1. Set up the shared condition. We define a new Boolean flag, data_ready, and, crucially, a shared threading.condition parenthesis object. The condition object inherently contains its own lock, which we will acquire using the with statement before accessing the shared data_ready flag. 2. The waiting consumer thread. The consumer task acquires the condition's lock. It then uses a while loop to check the state of data_ready. Since it starts as false, the consumer calls condition.wait parenthesis. The consumer thread immediately releases the lock and goes into a blocked state, consuming no CPU. It will remain asleep until another thread calls .notify parenthesis. 3. The notifying producer thread. The producer task runs for 3 seconds. Once ready, it enters the critical section using the with condition : block. It sets data_ready to true and then calls condition.notify parenthesis. This wakes up the waiting consumer thread. The consumer then waits for the producer to exit the with block and release the lock before it can reacquire the lock and continue its execution. To summarize, the wait and notify mechanism is far superior to polling. Our next lecture 26.19. Queues and thread communication. See you there. Welcome back. We have seen how to synchronize shared variables with locks and coordinate threads with wait and notify. However, the most robust Pythonic way to handle both synchronization and communication is by using the queue data structure. 1. Why use queues? Thread communication often involves passing data, not just signals. Queues combine data transfer with blocking synchronization. In essence, when a thread puts an item into a queue, it automatically notifies any waiting threads. When a thread tries to get an item from an empty queue, it automatically waits until an item is available. This makes the queue module a perfect, all-in-one solution for multithreading coordination. 2. Thread safety and FIFO. The queue.queue object is explicitly designed to be thread safe. It uses internal locks and condition variables to manage access, meaning you never need to manually apply a lock when using its methods. A standard queue follows the first in, first out, or FIFO principle. The first item put into the queue is the first item that comes out. 3. The primary methods. To add data, we use .put parenthesis. To retrieve data, we use .get parenthesis. By default, both methods are blocking, which is the key to efficiency. If a thread calls .get parenthesis on an empty queue, it blocks and sleeps until another thread calls put parenthesis. Similarly, if you define a limited size queue, .put parenthesis will block if the queue is full. This elegantly handles the wait and notify communication necessary for passing data. To summarize, queues simplify complex synchronization and communication needs. Our next lecture 26.20, Producer-Consumer Pattern. See you there. Welcome back. The producer-consumer pattern is a powerful model in multithreading. It uses a shared queue to decouple the task generator, the producer, from the task executor, the consumer. 1. Defining the shared queue. We start by creating a shared work_queue instance from the queue module. We set a max size of 5 to create a bounded buffer. This means the producer thread will automatically block if it tries to put an item into a queue that already contains 5 items. This is a built-in synchronization control. 2. The producer thread using .put parenthesis. The producer generates items, in this case, task number 1 through 10, and calls work_queue.put parenthesis. Since the queue is thread safe, we don't need locks. Notice the critical last step, putting a special value, none, into the queue. This is a common way to signal to the consumer that no more tasks will be produced, allowing the consumer to shut down gracefully. 3. The consumer thread using .get parenthesis. The consumer runs an infinite loop and calls work_queue.get parenthesis. This call automatically blocks and sleeps if the queue is empty, efficiently eliminating polling. The consumer processes the item and then, if it receives the none signal, it breaks the loop but also puts none back into the queue to signal any other waiting consumers, ensuring a cascade shutdown. To summarize, the queue is the primary tool for clean data exchange between threads. Our next lecture 26.21, 3 types of queues. See you there. Welcome back. We've established that the queue is the ultimate tool for inter-thread communication. While we used the default queue in the producer-consumer pattern, the queue module provides 3 different classes based on how tasks should be ordered. 1. Standard queue using the queue class. This is the default and most common type we used. It implements the FIFO principle, first in, first out. Tasks are processed in the exact order they were submitted. You use this when the order of arrival is important, such as processing user requests or logs in sequential order. 2. LIFO queue using the LIFO queue class. This implements the LIFO principle, last in, first out. This structure behaves like a stack. The last item added to the queue is the first one retrieved by the consumer. You may use this in scenarios where you want the latest changes or revisions to be processed immediately, like in an undo history stack or processing newer requests first. 3. Priority queue using the priority queue class. This type processes items based on their assigned priority, regardless of when they were added. When using this queue, the items must be tuples where the first element is the priority number. The lowest number means the highest priority. You would use this for mission-critical applications where error reporting must happen before processing standard tasks, or when managing different service tiers. To summarize, these queues give you flexibility in how you manage tasks in a concurrent environment. Our next lecture 26.22, Types of Queues. See you there. Welcome back for the final lecture on threads. We have covered the 3 main thread-safe queue types. Now, let us summarize them in a handy comparison table to help you choose the right tool for your specific concurrency needs. 1. Queue comparison table. This table summarizes the key characteristics of the 3 queue types. The standard queue uses FIFO, where the item that went in first is the item that comes out first, ideal for processing tasks in order. The LIFO queue uses LIFO, which retrieves the newest item first. Finally, the priority queue retrieves items based on the priority value assigned to them, with the lowest number signifying the highest priority. Two. Conclusion threading. Congratulations! You have completed the section on threads. We started with the basics of thread creation, understood the critical need for synchronization using locks and semaphores to protect shared data, and finally mastered communication using the wait and notify pattern and the highly effective thread-safe queues. These are the fundamental tools for building robust, high-performance concurrent applications in Python. Looking ahead, networking. Now that we know how to run tasks concurrently, we will move to our next major topic, networking. We will learn how to make our programs communicate with the outside world, covering everything from simple HTTP requests to building our own custom network servers using sockets. This opens up entirely new possibilities for your applications. We will begin section 27 by exploring the basics of retrieving data from the internet, starting with downloading a simple HTML page. Join me in lecture 27.01. Introduction. See you there. Welcome to a brand new section, networking. This topic is about enabling your Python programs to communicate with other computers, whether that's downloading data from a website, sending an email, or even creating your own custom client-server applications. 1. What is networking? In simple terms, networking is the process of exchanging data between different devices across a network, typically the internet. Every time you open a web page or send a message, you are using networking protocols like HTTP or TCP/IP. Our goal is to make Python the client or the server in these exchanges. 2. High-level networking. URL-lib.request. Python provides several easy-to-use modules for common tasks like downloading files and web pages. The standard library module URL-lib.request is one such high-level tool. It handles all the complex protocol details for you, letting you fetch data with just a few lines of code. We will use this module first to quickly grab content from the web. 3. Low-level networking socket. For building custom servers, real-time client applications, or simply gaining deep control over the network connection, we turn to the socket module. Sockets provide the foundational mechanism for network communication. Learning sockets lets you define how data is transmitted, giving you the power to create almost any type of network application. Networking in Python involves two main approaches: high-level tools like URL-lib.request for simple web tasks, and low-level tools like Socket for building custom client-server applications. Our next lecture 27.02, Downloading a HTML. See you there. Welcome back. Our first practical exercise in networking is downloading the raw HTML source code of a web page. We will use the built-in URL-lib.request module, which is the standard Python library for opening URLs. 1. Importing and defining the URL. We import the necessary module and define the URL variable. For this example, we will download the HTML of the W3 Schools homepage. 2. Opening the URL. We wrap our network call in a try except block to handle connection errors. We call URL-lib request URL opened parenthesis, which performs the HTTP request and returns a response object. From this object, we can get the HTTP status code. 200 code means the request was successful. If so, we call response.read parenthesis, which downloads the entire content as raw bytes. 3. Decoding the bytes. Since all network data is transmitted as binary bytes, we must convert these HTML_bytes into a readable Python string using the .decode parenthesis method, specifying the UTF-8 encoding, which is standard for web content. Finally, we print the first 500 characters of the string, which will show the raw HTML source code. To summarize, we successfully fetched text data from the internet. Our next lecture 27.03, Downloading an image. See you there. Welcome back. We successfully downloaded HTML, which is text data that needs decoding. Now, let us tackle binary data by downloading an image file from the internet and saving it to our local system. The key difference lies in how we handle the file content. 1. Defining URL and local file. We define the image_URL. I'm using a placeholder URL that serves a random image, but it could be any direct link to a JPG or PNG. We also define the desired output file name, local_file name. 2. Downloading the binary content. We use the with statement to open the URL and ensure the connection is automatically closed. We call response.read parenthesis, which returns the image content as raw binary bytes. Since it's binary, we do not call .decode parenthesis, which would corrupt the image data. 3. Saving the bytes to a file. This step is crucial. We open a local file using the file name we defined, but notice the mode, WB. The W stands for write, and the B stands for binary mode. This tells Python not to perform any text encoding and to write the raw bytes directly to the disk. We then call file.write parenthesis, passing the raw image underscore bytes, completing the download and save operation. To summarize, we have seen how to handle both text and binary data using high-level networking tools. Our next lecture 27.04, Socket Programming. See you there. Welcome back. While high-level functions like URLLIB are convenient, they hide the true complexity of networking. To build custom applications like chat systems or file servers, we must use the low-level foundation, socket programming. 1. What is a socket? Think of a socket as the endpoint of a two-way communication link between two programs running on a network. It is what allows the operating system to send and receive data. Every connection you make, from a web browser to an email client, uses sockets under the hood. In Python, we use the socket module to access this fundamental mechanism. 2. Creating a socket object. To create a socket, we need two main parameters. The first is the address family, and we use AF_INET for standard IP version for networking. The second is the socket type. We use sock_stream for TCP, or Transmission Control Protocol, which is connection-oriented and reliable. This combination is the standard for almost all Internet applications like HTTP and FTP. 3. TCP versus UDP. When choosing the socket type, you choose between TCP and UDP. TCP, or sock_stream, is reliable. It ensures data is delivered in order and without errors, making it suitable for file transfers and web browsing. UDP, or sock_DGRAM, is faster but unreliable, suitable for video streaming or gaming, where losing a packet is acceptable for speed. To summarize, we now know the components needed to create a socket. Our next lecture 27.05, Create a Server. See you there. Welcome back. We are now ready to build our first custom network application. To handle incoming connections from clients, we must create a server. A TCP server follows a specific sequence of steps: socket, bind, listen, and accept. 1. Setup and socket creation. We import the socket module. For local testing, we are explicitly setting our host to the local loopback address 127.0.0.1. This ensures the server is only reachable from our own machine. We choose a port number above 1023, as ports below that are reserved. Then we create our TCP socket S. 2. Bind and listen. The server must be bound to a specific network interface, the host, IP, and a port. The s.bind parenthesis method assigns this address to the socket. Next, s.listened parenthesis puts the server into listening mode. The argument 5 is the backlog, which means the maximum number of pending connections the operating system will hold before refusing new clients. 3. Accept connections. The server then enters an infinite loop. The s.accept parenthesis method is blocking. It halts execution until a client connects. Once a client connects, it returns two values: a new socket object, CONN, used only for communicating with that client, and the client's address, ADDR. For simplicity now, we immediately close the connection, but this is where the real data exchange would happen. To summarize, our server is listening. Now we need a program that can initiate a connection to this server. Our next lecture 27.06. Create a client. See you there. Welcome back. We have our server listening patiently. Now we need the other half of the conversation, the client. Creating a client is much simpler than creating a server, as its primary job is just to initiate and maintain the connection. 1. Client setup and connection. The client must know the server's address, so we use the same host and port values. We create the socket S using the standard TCP settings. Crucially, we use the with statement to ensure the socket is automatically closed, even if errors occur. The s.connect parenthesis method initiates the connection handshake with the server, which is the only step required before sending data. 2. Sending and receiving data. All data sent over a socket must be in bytes. We take our string message, hello, server, and use .encode parenthesis to convert it to bytes. We use s.sendAll parenthesis to ensure all bytes are sent. To receive data, we use s.recv parenthesis, specifying the maximum buffer size, usually 1024 or 4096 bytes. The received data, which is in bytes, is converted back to a string using .decode parenthesis. 3. Updating the server for communication. For this client to work, we need to modify the server code we wrote previously. Instead of immediately closing the connection, the server must now receive the data using conn.recv parenthesis. It then processes the data, here converting it to uppercase bytes, and sends the reply using conn.sendall parenthesis. The server's work is finished, and the connection socket, conn, is automatically closed when it exits the with conn end block. To summarize, we have a fully functional TCP client-server model. Our next lecture 27.07. File server. See you there. Welcome back. We are upgrading our simple client-server model to handle the transfer of a large asset, a file. Our goal here is to create a robust file server that can read a file in chunks and send it through the socket connection. 1. Server setup and initialization. We define the host and port as before. We introduce file underscore to underscore sen, which is the name of the file we want to transfer, and buffer underscore size, which defines how many bytes we will send at a time. Using a small buffer size is crucial for large transfers, as it prevents memory overload and ensures data is sent reliably over the network. 2. Handling the client connection. Inside our handle client function, after accepting the client connection, we open the file in binary read mode, RB. We then enter a while true loop. In each iteration, we use file.read parenthesis with the buffer underscore size to read a data chunk. When file.read returns an empty chunk, it signifies the end of the file and we break the loop. Crucially, we use conn.sendall parenthesis to transmit the raw binary data_chunk to the client. 3. The main server loop. The main server logic remains the same. Create, bind, and listen. The while true loop accepts the incoming connection and then calls our handle client function with the new connection socket. Note: in a production application, you may use a thread here to allow the server to handle multiple clients concurrently, which we learned in the previous section. To summarize, our server is ready to stream the file. Our next lecture 27.08, File Client. See you there. Welcome back. Our file server is ready to stream content. Now we must implement the file client to connect, receive the incoming binary chunks, and correctly stitch them back together into a local file. The core difference here is that the client must continuously receive data until the server closes the connection. 1. Client setup and connection. We match the servers, host, and port. We define the output_file name, which is where the received data will be saved. The buffer_size must also match or be larger than the server's sending chunk size to ensure we can capture all data efficiently. 2. Receiving and saving the file. After connecting, we open our local file in the critical binary write mode, WB. We enter a while true loop. In each loop, s.recv parenthesis attempts to read up to buffer_size bytes. When the server finishes sending the file and closes its connection socket, s.recv parenthesis returns an empty bytes object, which is not bytes_received is true, and we break the loop. For every chunk received, we use file.write parenthesis to append the raw binary data to our output file. To summarize, you now know how to build a client-server application that can reliably transfer binary files. This is the foundation of many powerful tools. Our next lecture 27.09, Sending Emails. See you there. Welcome back. In this part of the networking section, we tackle one of the most common automation tasks, sending emails directly from a Python script. We will use two powerful modules from the standard library, SMTPLIB for the network connection and email for message formatting. 1. The SMTP protocol. To send an email, your Python script acts as a client, connecting to a mail server like Gmail or Outlook using the SMTP or Simple Mail Transfer Protocol. This protocol requires you to authenticate with your email credentials and specify the sender, receiver, and message content. 2. Module 1, SMTPLIB for connection. This module is the client-side implementation of the SMTP protocol. We create an SMTPLIB.SMTP object, providing the server address and the port, which is 587 for TLS encryption. Since modern servers require a secure connection, we must call SMTP_server.start TLS, parenthesis to upgrade the connection to TLS, or transport layer security, before authenticating. 3. Module 2, Email for formatting. While SMTPLIB handles the transmission, The email module structures the message correctly using standards like MIME. We import MIME text to create a new message object, MSG. We then use dictionary-like access to set the header fields, like subject, from, and to. These headers are mandatory for a valid email, and email ensures they are formatted correctly for SMTP. Sending emails requires the SMTP protocol. We use SMTP-LIB for the network connection and secure transmission, start TLS, and the email module, e.g., MIME text, to format the message headers and body. Our next lecture 27.10. Generate Gmail app password. See you there. Welcome back. Before we write the final email client, we must address a security measure enforced by modern email providers like Gmail. You typically cannot use your main account password to log in via SMTP anymore. Instead, you need a specialized app password. 1. Why an app password? Gmail requires this step for security, especially if two-factor authentication or 2FA is enabled, which it should be. The app password is a unique, one-time generated password that grants limited access only to the specified application, making it much safer than using your primary login credential. 2. Prerequisites, two-step verification. You must have Gmail's two-step verification turned on to generate an app password. If you do not have it enabled, pause the video and turn it on now. 3. The generation process. Access the following URL: https://myaccount.google.com/app-passwords. You may be required to enter your password and blah blah. Then you see this appearance. You may name the app SMTP client, then click on Create. Then you see a 16-character password, which is your app password. 4. Save the app password. Crucially, copy and save this password immediately. This 16-character string is the password you will use in our Python script in place of your main account password. To send emails via SMTP with Gmail, you must have two-step verification enabled and generate a unique app password, a 16-character string. This password replaces your account password in the Python script. Our next lecture 27.11. Email client. See you there. Welcome back. Having set up the app password, we are ready to write the core logic for our email client. This function will use SMTP-LIB to handle the network session and email to structure the message, completing the SMTP process. 1. Imports and connection details. We import the necessary classes. We define the Gmail SMTP server and the TLS port 587. Note the variables for sender_email and app_password. You must replace these placeholder values with your own Gmail address and the 16-character app password you generated in the previous lecture. 2. The send email function. Our function takes the recipient, subject, and body. First, we format the message using MIME text. Second, we establish the connection using SMTP-LIB.SMTP and immediately call start TLS parenthesis for security. Third, we authenticate using server.login parenthesis, passing the sender email and the app password. Finally, we use server.send email parenthesis, which takes the sender, recipient, and the message converted to a string using msg as underscore string parenthesis. The with block ensures the server connection is closed when done. To summarize, we have consolidated all the email logic into one robust function. Our next lecture 27.12. Run Mail Client. See you there. Welcome to the final lecture of our networking section. We have built our send email function using SMTPLIB and email. Now we will execute it to confirm that our automated mail client successfully connects to the Gmail SMTP server and delivers the message. 1. Review of client code setup. Before running, ensure that you have correctly substituted your actual Gmail address for sender_email and the unique app password you generated for app_password. 2. Defining test parameters. We set up the actual variables to pass to the function. For recipient_email, you may use your own email address to confirm delivery. We set a clear subject and body so that we can easily identify this message when it arrives in the inbox. 3. Running the client. We execute the send email function with our defined test parameters. If the connection, authentication, and sending process are successful, the program should print the confirmation message, email successfully sent to. To summarize, you have learned key networking tasks, web downloading, low-level socket programming for custom client-server communication, and high-level SMTP protocol for email automation. Our next lecture 28.01. Introduction. See you there. Welcome to a brand new section, Database Operations. This section will teach you how to integrate Python with a powerful external database system to store data. 1. Why databases? Files are great for small amounts of data, but a database management system like MySQL offers speed, reliability, and structured organization for large, complex data. It is the core component for everything from web applications to accounting software. 2. Introducing MySQL. MySQL is one of the world's most popular open-source relational database management systems, or RDBMS. It stores data in structured tables with defined relationships, ensuring data integrity. It uses the language SQL, or structured query language, to manage and manipulate that data. 3. The CRUD operations. All database operations can be broken down into 4 essential functions, commonly known as CRUD: create, read, update, and delete. In this section, we will cover how to perform the most important operations, namely read, create, and delete, using Python code interacting with a MySQL database. 4. Section Roadmap. This section will guide you from setup to execution. We start by installing the MySQL server and its graphical client, MySQL Workbench. Then we install the Python connector, set up a database, and perform all the core operations covering read, create, and delete. To summarize, we are ready to begin integrating Python with the world of databases. The first step is getting the MySQL server installed on your system. Our next lecture 28.02, Install MySQL. See you there. Welcome back. Our journey into database operations begins with installing the engine that powers it all, the MySQL server. This is the software that runs in the background to store, retrieve, and manage your data. 1. Downloading the installer. First, access this web page. Two. Setting the root password. Next, you must set the password for the root user. The root user is the super administrator of your MySQL server. Choose a secure password and write it down. We will need this password later to connect our Python script to the database. To summarize, your MySQL server is now running. However, managing it via the command line is difficult. In the next lecture, we install a friendly graphical tool for managing our database, MySQL Workbench. Our next lecture 28.03, Install MySQL Workbench. See you there. Welcome back. While the MySQL server is the engine, we need a friendly tool to interact with it. That tool is MySQL Workbench. This is a graphical interface that makes running SQL queries, creating tables, and viewing data much easier. 1. Installing Workbench. First, you access this page. Two. Launching Workbench and connecting. Once installed, launch MySQL Workbench. Here, I see an entry under MySQL Connections. Its name is Local Instance 3306. This connection is pre-configured to point to the server you just installed. Click this connection. 3. Root password. When you click the connection, a window will pop up asking for the password for the root user. Enter the root password that you set during the MySQL server installation. Four. The Workbench interface. Once connected, the main SQL editor will open. This is where we will write our SQL commands. You will see a panel on the left that lists all the schemas, which is the MySQL term for databases. To summarize, we have the server and the graphical client ready. Our next lecture 28.04. Install MySQL connector. See you there. Welcome back. We have the MySQL server running and the Workbench GUI installed. The final setup piece is the MySQL connector. This is the specialized Python library that allows our code to talk directly to the database server. 1. Using pip3 to install the connector. This step is simple. Open your terminal and use pip3, our package installer, to get the connector library. The package name is mysql-connector-python. 2. Installation command. Type the command pip3 install mysql-connector-python. After running this, pip3 will download the library and install it into your Python environment. 3. Verifying the installation in Python. To quickly check that the library is correctly installed, try to import the module. Import mysql.connector. If the command runs without an error and prints the success message, you are ready to proceed to the next step. To summarize, we are fully equipped now. Server, GUI client, and Python connector. Our next lecture 28.05. Set up the database. See you there. Welcome back. The MySQL ecosystem is complete. Now we use MySQL Workbench to create the structured environment our Python script will interact with. We need to define a database and a table to hold our data. 1. Creating the database. Open MySQL Workbench and connect to your local instance. A database is essentially a container for tables. In the SQL editor, we run the command to create our new database, which we will name PythonDB. After running this SQL command, refresh the schemas panel on the left, and you should see the new database appear. Now, we must tell MySQL that all subsequent commands should be executed within this database using the used command. Two, creating the users table. Within the PythonDB database, we create a table named users to store records. Every table needs columns with defined data types. Our table will have 4 columns: ID, name, email, and age. The ID column is set as primary key and auto_increment, meaning MySQL automatically manages a unique identifier for each user. Varchar is a common type for variable length strings, and int is for integers. Not null ensures a value must always be provided for that column. To summarize, the database is set up and ready to hold our data. Our next lecture 28.06. Connect to the DB from Python. See you there. Welcome back. The database is structured, the server is running, and the connector is installed. This lecture is about making the crucial link, establishing a persistent connection from our Python script to the MySQL database. 1. Importing and defining credentials. We import MySQL.connector. We then define the necessary connection variables. The host is localhost since the server is on our own machine. The user is the MySQL root user. You must replace the password with the secure root password you set during the MySQL installation. Finally, we specify the database we created in the last lecture, PythonDB. 2. Establishing the connection. We wrap the connection attempt in a try except block to catch potential errors, like wrong passwords or a server not running. We call mysql.connector.connect parenthesis, passing our defined variables as keyword arguments. If successful, this returns the CONN object, which is the communication line to the database. We check CONN.is_connected parenthesis to confirm the status. 3. Creating a cursor object. Every operation, whether reading or writing data, requires a cursor. We get the cursor by calling conn.cursor parenthesis. The cursor is the object responsible for executing SQL commands and fetching the results. Finally, always ensure you close the cursor and the connection when your work is done to free up resources. To summarize, we can now talk to MySQL. Our next lecture 28.07. Read. See you there. Welcome back. With our database connection established, we start the CRUD operations with read. To read data, we must first ensure there is data to read. We will temporarily insert a test user using MySQL Workbench, and then fetch that data using Python. 1. Inserting sample data. Switch over to MySQL Workbench. Run this SQL command to insert one test user into our users table. Notice we skip the ID field because it is auto_increment. Two. Preparing the Python script. Back in Python, after connecting and creating the cursor object, we define our SQL query string. We use select asterisk from users to retrieve all columns from the table. Limit 1 is added to ensure we only get a single row, which is useful for testing. 3. Executing the query and fetching data. First, we use cursor.execute parenthesis to send the SQL query to the database server. Second, we call cursor.fetch1 parenthesis. This method retrieves the next result row from the executed query and returns it as a tuple. If no more rows are available, it returns none. We then print the resulting user_record. To summarize, we successfully executed our first read operation and retrieved a single record. Our next lecture 28.08. Read fetch all. See you there. Welcome back. In the previous lecture, we learned to retrieve a single row using fetch1. But most database operations require fetching an entire result set. This lesson focuses on the fetch all method, which is essential for working with multiple records. 1. Inserting multiple sample records. To ensure our fetch all command works correctly, let us quickly insert a few more records into the users table using MySQL Workbench. 2. Executing the full select query. Back in Python, we used the select asterisk from users query, this time without the limit 1 clause, to retrieve all available records. The cursor.execute parenthesis command sends this query to the server. 3. Retrieving all results with fetch all parenthesis. The cursor.fetchAll parenthesis method retrieves all remaining rows from the query's result set and returns them as a list of tuples. Each tuple in the list represents one row of data. We can then easily iterate through the all_records list to process each user individually. To summarize, you can now read, retrieving single records or entire datasets. Our next lecture 28.09. Create. See you there. Welcome back. We have learned reading data. Now, let's tackle the next essential CRUD operation. Create, or inserting new records into the database. We will learn how to safely pass Python variables into our SQL query. 1. Defining the insert query with placeholders. The SQL command for insertion is insert into. Crucially, instead of embedding the data directly into the query string, we use placeholders, which are %s symbols in MySQL connector. This practice prevents SQL injection attacks, a major security risk. We define the actual values for the new user as a Python tuple, new_user_data. 2. Executing the insert query. When calling cursor.execute parenthesis, we pass the SQL string as the first argument and the Python data tuple new_user_data as the second. The connector securely substitutes the tuple values for the %s placeholders in the SQL query before sending it to the server. 3. Committing the transaction. This is the most critical step for any write operation. Unlike select, which only reads, and insert, update, or delete, command only stages the changes until you explicitly call conn.commit parenthesis. The commit makes the changes permanent in the database. After a successful insert, we can use cursor.lastRowID to retrieve the automatically generated ID of the new record. To summarize, you can now add new data securely. Our next lecture 28.10. Delete. See you there. Welcome back. In our final CRUD operation for this section, we cover delete, or how to remove records from a table. Just like the create operation, this is a write operation that requires the commit command to finalize the change. 1. The delete query structure. The SQL command is delete from followed by the table name. The most important part is the where clause. This clause acts as a filter, specifying exactly which rows should be deleted. If you forget the where clause, the command will delete every single row in the table. 2. Preparing the Python delete script. We use the safe, parameterized query method again. Our SQL string specifies that we want to delete a user where the ID column matches the placeholder %s. We define the target ID as a tuple user _ID_ to _delete, even though it contains only one value. The comma after the number 4 is important to ensure Python recognizes it as a tuple. 3. Executing and committing the deletion. We execute the query, passing the ID tuple as the second argument. Once executed, we must call conn.commit parenthesis to permanently remove the record from the database. The cursor.rowCount attribute tells us how many rows were affected by the last executed query, which should be 1 in this case. To summarize, congratulations! You now know how to connect to a MySQL database and perform the fundamental CRUD operations: create, read, and delete. This wraps up our section on MySQL. Our next lecture 29.01. Introduction. See you there. Welcome to the next section. Using PostgreSQL. While MySQL is popular, PostgreSQL is another powerful enterprise-level relational database often preferred for its robustness, advanced features, and strict adherence to SQL standards. We will quickly demonstrate that the core process for connecting and performing CRUD operations from Python is highly consistent, regardless of the database you use. 1. Why PostgreSQL? PostgreSQL, often simply called Postgres, is known for handling complex queries, massive amounts of data, and providing exceptional reliability. It is widely used in mission-critical applications. Understanding how to connect to both MySQL and PostgreSQL makes you much more versatile as a developer. 2. The consistent Python workflow. Regardless of whether you use MySQL, PostgreSQL, or another database, the Python workflow follows the same steps. 1. Install the appropriate connector library. 2. Establish a connection object. 3. Create a cursor object. 4. Execute SQL via the cursor. 5. Commit write operations. We will simply replace the MySQL.connector library with the PostgreSQL connector. PSYCOPG2. 3. Section roadmap. We will set up the PostgreSQL server and its graphical client, pgadmin. We then install the specialized Python connector, PSYCOPG2, set up a database, and perform the essential connect, insert, and fetch operations to prove the concept. To summarize, we are ready to work with another database. The first step is to get the PostgreSQL server installed on your machine. Our next lecture 29.02, Install PostgreSQL Server. See you there. Welcome back. We have the PostgreSQL server installed and the pgadmin client ready. The next crucial step is installing the official Python library that allows our code to communicate with the PostgreSQL database, PostgreSQL. 1. Introducing PostgreSQL. This library is the most popular PostgreSQL adapter for the Python programming language. It is a robust and widely used connector that implements the Python DB API, or Database API, standard. This means that once you learn how to connect and use a cursor with one database, you already know the general process for all others. 2. Installation command. Open your terminal. We will use the pip3 install command. Note that we are using the PostgreSQL-binary package. This version is precompiled and easier to install across different operating systems, avoiding potential compilation errors you may encounter with the regular PostgreSQL package. 3. Verifying the installation. To ensure the library is correctly installed, run a test script and try to import the module. Import PostgreSQL. If the import statement executes without raising an error, you are good to go. This confirms the bridge between Python and PostgreSQL is ready. To summarize, all our tools are in place. Our next lecture 29.05, set up the database. See you there. Welcome back. Now that our PostgreSQL server and the PostgreSQL connector are ready, we use the pgadmin graphical tool to structure our environment. We need to create a new database and a simple table. 1. Creating the database. Open pgadmin and connect to your local server. Right-click on the Databases node in the Object Explorer and select Create, then Database. Name your new database PythonDB. This action saves us from running a create database query manually. 2. Accessing the SQL editor. Once the database is created, click on it, and then click the Query tool icon. often represented by a sheet of paper with a magnifying glass or a tiny SQL icon. This opens the SQL editor, ready for us to define our table. 3. Creating the products table. We will create a table named products to store a few items. The SQL syntax is very similar to MySQL. Note the PostgreSQL specific data type, serial. This handles the auto-incrementing integer key automatically, equivalent to auto_increment in MySQL. We define ID as serial primary key, name as varchar, and price as numeric for accurate currency storage. To summarize, our PostgreSQL database is structured and ready. The final step is switching back to Python to connect and insert our first record using the PostgreSQL connector. Our next lecture 29.06, Connect and Insert. See you there. Welcome back. The database is set up, the connector is installed. Let us now connect to PostgreSQL using PostgreSQL and perform our first CRUD operation, create or inserting new data. 1. Connecting to PostgreSQL. We import PostgreSQL. Notice that the connection parameters are almost identical to MySQL, just with different names: DB name, the default Postgres user, and the default port 5432. We use the PostgreSQL.connect parenthesis function to establish the connection, which gives us the CONN object. We immediately create the cursor object from it, which we will use for execution. 2. Inserting data with placeholders. The SQL query syntax is standard insert into. Just like in MySQL, we use the %s placeholder for safe parameterized queries. We define our data as a tuple, product_data, ensuring the price is a float or integer that matches the expected numeric type in the table. We execute the query by passing the SQL string and the data tuple to cursor.execute parenthesis. 3. Committing the change. As an insert operation, the change is only staged until we call conn.commit parenthesis. This is standard database behavior and applies equally to PostgreSQL. After committing, the new record is permanently stored in the products table. To summarize, you have successfully connected to and inserted data into PostgreSQL from Python. Our next lecture 29.07, Fetch Data. See you there. Welcome back. In our last lesson, we successfully connected to PostgreSQL and inserted a record. Now, we complete the demonstration by performing the read operation, fetching the data back to Python. You will see that the logic is exactly the same as with MySQL. 1. Inserting more sample data. To make the fetch operation meaningful, let's insert a couple more records using pgadmin or by rerunning the code from the previous lecture with different data. This ensures we have a few rows for fetch all to retrieve. 2. Executing the select query. Back in Python, assuming the connection and cursor are open, we define a standard select query. We use order by IDASC to ensure the records are returned in the order they were inserted. We send the query to PostgreSQL using cursor.execute parenthesis. 3. Retrieving and processing data. We use cursor.fetch all parenthesis, which, identical to MySQL, returns the result set as a list of tuples. Each tuple represents a row from the products table. We iterate through the list and print each record. Finally, we must close the cursor and connection, concluding our operations with PostgreSQL. To summarize, you now have experience connecting to and manipulating data in two major relational database systems, MySQL and PostgreSQL. In the next section, we shift gears dramatically to the world of NoSQL with MongoDB, where we will work with flexible JSON-like documents instead of rigid tables. Our next lecture 30.01, Mongo Introduction. See you there.